ये हो जाएगा, अब मैं बोल सकता हूँ। हाँ।
Jobish, shall we start?
Hello, sir.
Yeah.
Sir, only thing which I noticed is that the technical team, probably they will say we can start. The thing is,
Okay.
the inaugural session is still going on.
Okay.
And all other participants, actually what you see here are not the participants, either professors or those who have been given this link. So
Yeah.
participants are maybe still attending the inaugural session.
Okay. Okay. We'll wait. All right. Fine. Okay.
But still we should not delay much because we should still, these are parallel sessions.
If there are no audience, then what is the point? Dr. Dikshit's talk will not be heard by anybody except us. Hi, Dikshit sir.
Hi. Sharma ji and Joseph Saab.
Good morning,
Yeah.
good morning.
Good morning.
And K.R. Singh sir also is there. He has joined.
Okay.
Saying good morning.
Good morning, Sharma ji. Good morning.
Good morning.
Yeah.
No, Professor Kher Singh is also here. Professor Kher Singh ji, good morning, sir.
Yeah. Good.
Good morning, K.R. Singh.
Yes, sir. Yes, sir.
We can hear. There's some breaking, but it's okay. Yeah.
Yeah. So maybe the inaugural session may be
We'll just
going
wait
on.
for another 5 minutes or so.
Yeah.
Let's see.
Sure, sure.
I think the technical team should tell us.
Yeah.
We'll go ahead, I think. Yeah.
Because they may then open it to others. I don't know which way it goes.
Yeah. No, they will. You see, unless the inaugural session is over, the audience will
right.
not be in parallel sessions. Yeah.
No, better to wait for that.
Yeah.
Because
Let's wait. Yeah. Okay.
Because I tried to enter the site through the link which is given to the other participants. I could not come here.
Okay. So they're still there. All right. So we'll wait for some time. Yeah. Okay.
Sure.
We'll come back after.
Yeah,
Maybe you can just announce.
Just 5 minutes. I'll be here.
Yeah. I'm also here, but I'm just mute it, for the time.
Sir, we will go live now. Now the session is ended.
Hello, Andasarma sir. I think they have said go ahead.
Okay. But I don't see much participants. Or
But
is
you
it
cannot see
YouTube?
participants here, sir. Participants cannot be seen by us.
Start now.
Okay.
Yeah, we can see only those like link which have been given to professors and organizers only. Participants
Okay.
cannot be seen from here.
All right. So we can go ahead. Yeah?
Yeah. So I will just start it and then you can go.
Yeah.
Yeah, welcome everybody to this Icee 2020 conference. This is the 5th conference. Currently, this is held in IIT Delhi. Before this was held 2 times in IIT Bombay and 2 times in IIC Bangalore. And first time this conference, as everybody expects, this is the online conference for the first time. And I do not know the total number. I expect, I understand from Professor Neeraj Khare, who is the organizer or the host of this conference, that the total number of participants may be of the order of 2,000 or so. And they are online attending from everywhere. So I will just introduce Professor Andash Sharma, who will be chairing this session. And Professor Andash Sharma, as everybody knows, is a professor of physics at Delhi. And he has been well known for almost all of us in India and abroad who works in optics, photonics, and fiber optics. And he has contributed tremendously to the department's growth and IIT Delhi's growth through various administrative positions as our HOD, then Dean Academics, Dean of Students, and took care of when new IIT started, IIT Roper, IIT Jammu, all that. He was fully involved in all those activities, apart from his scientific achievements, as he is a fellow of almost all the national academies of India in and Nasi, etc. And he is a recipient of Shanti Swarup Bhatnagar Award, Meghna Saha Award, S.K. Mitra Memorial Award, and so on. So, without spending much time, I will hand over the mic to Professor Andash Sharma so that he can introduce the session and the invited speakers. Yes, sir, please.
Okay. Let me just come online. Yeah. Okay, good morning to all of you. It is my pleasure to chair this session. Thank you, Joby, for those kind words that you said. And this session, I mean, the entire session, this vertical is on photonics and plasmonics, and there's no names given to individual sessions that I see. So there are 3 invited talks in this session and 2 oral talks. The first invited talk is by Dr. S.K. Dikshit from RR-CAT Indore, and it's my pleasure to introduce Dr. Dikshit. He's going to speak on fiber optic sensors research to development or deployment rather. Dr. S.K. Srivastava joined the laser program of RR-CAT in 1987 after completing his 30th batch of BARC training school at Mumbai. And he has contributed tremendously in lasers on optics, nonlinear optics, fiber optics, optical fiber sensors, and laser spectroscopy. He did his PhD from Devi Ahilya Vishwavidyalaya in Indore in 1996. Did postdoctoral work at Oxford University, visited many laser and accelerator facilities all over the world, and he has been very active in research and development at RR-CAT. He has published nearly 200 publications in journals, conferences, book chapters, been an editor of a book, and currently he's heading fiber sensors and optical spectroscopy division at RR-CAT, and he's also a professor at the Homi Bhabha National Institute, Mumbai, which is associated with the DAE. So, good morning, Dr. Dikshit, and welcome to this session. Please go ahead with your lecture. You have about 25 minutes. I'll try to give you a hint 2-3 minutes in advance. Okay? Yeah.
Okay. Thank you, Professor Sharma and Professor Joseph. And it is my honor to speak at the conference. And I will share my slide now.
Yes, it is coming. It is coming.
It is coming. Okay. So first of all, I am happy to receive such an invitation, and I thank Anuj Dhawan and for such thing, and I also thank Session Chair Anurag Sharma and Jubil. Today I'm going to speak on fiber optic sensor research to deployment, and I'm going to tell about most of the things work being carried out at our center, Raja Ramanna Center for Advanced Technology. Now, as you know that in any research work or any industry or like that, there are many parameters which need to be measured and can list it endless, but I've listed some of things: temperature, strain, force, vibration, load, flow, rotation, like that. Now, for measuring each and everything, there are dedicated sensors are there. But the thing is, can we think about a common platform? Because these other sensors are based on different methodologies and different applicabilities. We think about a common platform with suitable variation to measure the listed parameters. The answer is yes. And platform can be an optical fiber. It means that optical fiber can measure these parameters. Of course, not all the parameters at the same time, but with different variation, optical fiber can be utilized to measure these parameters, and it has offer certain advantages. Now, in the beginning, I am just cautioning because I am not claiming that optical fiber sensors can replace all the existing sensors, but the thing is that there are numerous situations where fiber sensor offer distinct advantage over existing sensor in terms of convenience, installation, sensitivity, and workability. Those who are working in fiber optic sensor, they know the highlights of fiber optic sensor: small size, lightweight, allows access into normally inaccessible areas because fibers small, 250 micron diameter. Core is very small, but with cladding and all jackets, etc., about 250 micron. Immune to radio frequency, microwave, lightning, other EMI interferences. High resistance to ionizing radiation, distributed sensing with good spatial resolution, can work in harsh environment, fast response, high accuracy, interface with data communication system, secure data transmission, remote operation. These are the advantages of using any sensor based on optical fiber. Fiber sensor can be classified in various ways, and one of the categories that fiber break gratings inscribed in optical fiber. Another category can be long period gratings inscribed in optical fiber. I will come to that. And coatings, metal or other on optical fiber, with or without grating, or Raman scattering based, or maybe Brilua and Rayleigh scattering based also can be utilized for sensing the things using fiber. And all these fiber sensor activities are being pursued at RRCAT. This encompasses research, technology development, qualification, and field deployment. And I'm going to describe mostly the work carried out in our center at RRCAT. Now, let's see about the FBG activity, fiber braketing activity at RRCAT. Now, just an introduction slide that fiber break grating is basically a periodic modulation of refractive index inscribed in the core of optical fiber. And this is usually done with ultraviolet radiation because that is because the photo fiber they absorb this radiation. And I'm showing you the typical schematic. And what happens that a broadband source if you put inside, you get a reflected transmitted spectrum and reflected spectrum, and they are made use in while we are doing any sensing because ultimately the wavelength or intensity of these peaks transmitted or reflected will shift, and that will sense the parameters. Now, what is the prerequisite if you want to make a fiber break in a lab? Because this is what our focal point also. So basically, you need a highly photosensitive fiber. It means that is the optical fiber whose core is doped with say 10 to 30% germanium, and a suitable UV source in range of 240 to 260 nanometers, an interferometer or a phase mask to make the fringes which you can inscribe the reflective index modulation, and a broadband light source and an optical spectrum analyzer or integrator to monitor FBG signal either in reflection or transmission mode. In addition, in a lab, you also need a hydrogen loading setup. This is optional because those fibers which are highly photosensitive, you don't need that. But for those fibers which are less photosensitive, normal telecom fiber, which only 3% germanium content, you have to soak that fiber into the hydrogen for 2 days or something for little high 150 degrees centigrade temperature, so that photosensitivity is increased. So then sometimes this is needed. So this has to be there in lab. Now, this is the technology which we developed at RRCAT. You are seeing the first upper this thing schematic. Basically, we use a paper laser. This laser we developed as part of some other program in Department of Atomic Energy. But then, as a spin-off, we are using now this developed laser to inscribe the fiber braketing. Basically, what we do, we have a copper ripple laser. It's a high repetition rate source, 5 kilowatt repetition rate, 5 to 10 kilowatt repetition rate, 90-second pulses. And this give visible light, green light, 510 nanometer. But you have to convert down to UV because for photosensitivity, UV light is this thing. So then we do second harmonic and we get 255 nanometer light. That is the thing you are seeing in the top schematic. And bottom thing you are seeing the actual system. You have a copper vapor laser. You are seeing the second harmonic generation setup, and then you are seeing the FBG writing, FBG or long bit getting writing setup. So this is the kind of system which exists in our lab. And if any one of you are interested in visiting that, you are most welcome. Now, then I'm going to tell you the various types of grating which we have using this system. And this system advantage because this is a high repetition rate, 5 kilohertz. So gratings are made, a typical grating, say type 1 grating. There are various types of gratings. I'm not going to detail of that, but there are various types. Type 1, which is initially made, that is only in 1 minute or sometimes less than about 30 seconds you can make this grating because the laser, copper vapor laser, very high repetition rate. So typical type 1 FPGs we routinely make in a few minutes, and operating value, of course, we operate in C band because of the C bands are most popular and low losses in the fiber. And peak reflectivity, which we measure in terms of transmission spectra, which one of the transmission spectra you're seeing at the top, and we make up to 40 dB, that is up to 99.99% reflectivity. Bandwidth anywhere depends on the photosensitive, what is germanium content and what is the exposure time. So it varies from 0.1 to 1 nanometer, it's quite sharp. And gauge length is again 5 to 10 millimeter. Now, the bottom curve, bottom photograph is the hydrogen loading setup which we developed, because sometimes you have to soak the fiber at higher temperature for a longer time. So this the setup which we ourselves have made. It is not a difficult thing to make. So that was a type 1, earlier was a type 1, and another type is type A FBGs. Basically, what happens that when you start making or grating, initially type 1 grating is formed, and as you keep on continually exposing it for longer time, it means you are increasing the fluence, then this grating is erased, and finally, and then after eraser, this grating again builds up. But this grating which again builds up is a different grating and different this thing, like because the stresses are released now while the grating is erased. So now this grating has a certain advantages as far as temperature sensing concerned, because it can measure now higher temperatures. So you are seeing on the top this thing, the transmission spectra, like as I'm increasing the fluence of UV light, means as I'm increasing the time, you are seeing that peak is coming, and then after certain time, the peak is reducing, and the getting got erased, and then again builds up. In the lower graph, you can see I am showing you the graph. The reflectivity say 100% for very long time, and then it start reducing, come to very close to zero, and then again builds up. So these are very special grating, especially if you want to measure high temperatures, say up to 500, 600, or 700 centigrade, because the glass has transformed, because the grating has erased and the stresses are released, the glass has transformed into another phase. So that is these are type 2A grating which we are making, and the reflectivity is here about 50%, 60%, and fabrication become larger. It is not 1 or 3 minutes because it is continuous exposure. So this another type of grating is that instead of doing regeneration with say continuous UV exposure, one can also do by continuous heating the grating. Like suppose you make a type 1 grating and put it in an oven for say time up to say 24 something with certain predetermined schedule, temperature schedule, higher temperature schedule. Then the again type 1 grating is erased, and again new grating is formed. This is another like just like we did in UV, we can do with temperature with slight more variation. And here fabrication time is little larger. We take about 2 days to make a grating, and so you are seeing that a seed FBG, typical seed FBG we have written, and this is the region. And again, the same thing as the earlier slide, that grating was erased and new grating is formed. Another grating, type of grating which you are making for this system is chirped grating. Chirped grating, you know, this they're the planes, refractive index planes inside the upper core, they are not uniformly spaced. They are given chirped, like they are given different spacing. And the advantage is that you can get a larger bandwidth grating here in this thing, and they are very useful for many applications for dispersion compensation, etc. So this is the grating also we are making. You can see here bandwidth which we have made is about 7 nanometer, and earlier I would talk about 0.1, 0.2, or zero point 0.3 nanometer, and we can go even larger than that depending upon the situation. Another grating is, in fact, the fiber break grating has come into the prominence because you can do distributed sensing. This means that in a single fiber, you can write several gratings, 10, 20, 30, 40, and then you have a distributed sensor. And this is a unique advantage of FBG based sensors, because otherwise, if you say want to measure temperature, you have to put 30 thermocouples, while a single fiber can measure and location and the strength etc. in your control. And this is actually what we do in our setup. We have to give a little tilt to the face mask, and the face matching condition is changed. You can see in the bottom thing, we have written set on 20 gratings of different wavelengths. So basically, this has become a fiber getting based distributed sensor. So this is which I'll show the example later on. Another grating is tilted grating, where your planes inside the fiber core are not 90-degree, they are tilted, and they have a very unique property that once you have tilted grating, then certain modes will become sensitive to the outside environment. So you are seeing this, the typical setup in the top, and then, sorry, then the tilted gating, like you have a core mode, ghost mode, and these are the cladding modes. So offer advantage of many sensing situations. So this is also a grating which we are making. And then another variation which we are doing is east grating. Like what happens that if you want to use fiber grating for chemical sensing, for sensing refractive index or any chemical or any thing, normally it will not, because normally the evanescent field is very, very weak outside the fiber cladding. So it will not interact with the outside medium. But then if you itch that, like if you itch the fiber clad by say hydrofluoric acid, then as you keep on itching that, the evanescent wave have in a position to interact with the outside medium. And then you can in principle use those gratings for chemical sensing for various situations. So this is the another grating which we are making that, and top one graph you are showing the itching. Once you itch the grating, how the pattern, how the break valence shift. When the itching is so much that the core is getting exposed to the outside environment, you see a sudden change in the wavelength, in the Bragg wavelength. And in the last, this thing, three slots we have given a typical qualification setup that if you want to, then in each grating, if you use air or ethanol or ethylene glycol, and then you see how the peaks shift. So in principle, this is a qualification graphs, and for various types of gratings, whether they are regenerated or whether they are normal type 1 or whether they are type 2, the itching patterns and the sensing patterns are different. So this is just to give an example that one has to be careful while which grating you are using, but definitely you can do chemical sensing with each grating. Then there is a long period grating, and what happened that in fiber break grating, the spacing between plane is only 0.5 micron. But in long period gating, you can go up to spacing up to 300 micron, 200 micron to 1 mm. And this getting an advantage that cladding modes are now present. Earlier, what happened fiber gating, it is only core mode because the spacing up between plane is such that no other mode exists or there's sort of cancelled out. But here in when the spacing between the planes is quite large, then you have a lot of modes, and it is the interference between the co-propagating core mode and cladding mode which finally decides performance. So wherever there is a resonance, there is a loss, and correspondingly, you will know this value will be missing in the transmission spectra. But this gating you cannot use in reflection mode. This gating has to be used in transmission mode because reflection doesn't this thing. So this is also grating which is lot of applications. In fact, it is more sensitive the fiber break grating for many parameters for temperature, etc. The only thing, it can only be used in the transmission mode, and it is very sensitive because if we slightly bend it, then the peaks will change. So very precautions are needed, but this is also a very good sensor for many specific applications. Now the second, the first part of talk was the fabrication of grating. I hope I told you that many gratings we are making. Now utilization. Now if you want to use this as a grating sensor, the typical range I have given. Type 1 300 degrees centigrade, type 2 700, and type 3 1000 degrees centigrade. And this is the qualification setup which we have, like you see oven and all these things. We have to qualify our sensor. So this is the kind of qualification setup which we have in our lab for functioning, utilizing them as a temperature. And this is the thing you are seeing in the slide, that we can measure temperature from liquid nitrogen, minus 196 to 1000 degrees centigrade with all sort of grating. And one of the gratings continuous, like we have told, degenerate grating from 30 degree to 1000 degree, 1100 degrees centigrade. And these are in the lower this thing, there are graphs, how the break valence shift. You see certain non-linearity because when you change temperature, not only the refractive index changes, slight variation in the spacing in plane is also there, depends on the stretching or fibers compressed. But this has to be taken care of while we are putting our data in the computer, and that takes care, and ultimately you will get a final temperature with the accuracy of plus minus 1 degree centigrade. And these are typical packaged sensors, which in various situations, if you want to use high temperature, you pack in ceramic or you pack in SS tube, and these bottom this see integrator, which we can see the numbers are displayed on the sensor. And this is our qualification for gamma ray. We have put our grating for gamma ray studies up to 1 mega gray, and you can see still top one is the grating before gamma ray, and after is 1 mega gray gamma ray, and you can see a peak is still there. It means you can use this sensor up to 1 mega gray, and this is a very huge dose. So this is what we are aiming that sensor should be used somewhere in nuclear reactor. Then this is the long period getting typical qualification experiment we did for temperature as well for radiation dose. This is a gamma radiation dose, and you can see significant shifts are there. So this generate possibility that fiber back gating or long period gating can be used in various situations. Now, come to the second part, deployment, because once you have developed, once you have qualified, then we have start deploying our sensor in various situations. You know, there's RRCAT, we have a synchrotron radiation source and a 2.5 GeV electron accelerator. The electrons are rotating in 172-meter ring, and you know when energy is so high, electron energy is so high, then temperature need to be measured all along the this circumference, because sometimes beam may hit the somewhere and it may open the vacuum chamber line something. So you are in the bottom thing, you are seeing one of the section of the Indus 2 ring here, where we have put 20 gratings, and this is a distributed sensor being put there. And it is lower thing is representative graph where you're seeing how the temperature of each and every grating, it means each and every location is changing with time as the signal radiation source is put on after a shutdown. You can see how the temperature variation is faithfully being recorded with time. It is online recording and it is data is stored there. So this helps in operation of the Indus 2. This is another deployment which we did in monitoring the waste product, that this nuclear waste product, and always giving gamma radiation. And you can see that one sensor we installed there at September 2007 in BRC Tarapur unit, and it is working so for all night. And you can see the thermocouple versus FBG sensor temperature. And thermocouple, you know, nuclear radiation thermocouple do not work for a long time because ultimately they transmute and they stop giving signal. So then, and there's another situation where for nuclear fuel recycling chamber, we have put our gratings for some purposes where microwave radiation was there, nuclear radiation was there, and chemical things were also there. And then we have put sensor for operation. This is another project which we are doing, that the RPGs can be put for railway safety. Like if you want to measure, suppose train is running and you want to measure online how actual temperature is varying, or suppose you put the grating on the railway track, then you can know the what load is passing through that track. It means suppose the wagon train is there, you can actually know what kind of loads it is filled with, and if there is certain non-uniformity in load, the train may get toppled. That is why this is an important study. And the last result you are seeing, we have tested this getting at Bangalore City Station Yard. 100 express, 17 coaches, one engine, total 74 wheels. As you are seeing, these wheels are passing. Each wheel is giving one signal, and then and the signal depends on the what is the load on the this thing. This three you are seeing is the engine part, and two you are seeing is the normal this coaches, 17 coaches. So this is the very interesting application which is now RCAT is contributing, and this is being done in collaboration with Icee Bangalore. So at various other places we have put our grating like in inside laser where high EMI is there, high temperature is there. So one of the examples are there that these there. Another lower one you can see that in transformer oil, high voltage capacitors are there, and temperature being displayed. So I'm just trying to tell you the examples, where typical examples. There are an endless list, but this is a typical example where these sensor, where normally if you want to use say thermocouple here, I don't think it will be a sensible idea. But for many places where thermocouples are cheaply available, it will be okay. Now, another work which we're doing, I have already told you that fiber grating, we have tested up to 1 megagray radiation dose. So now, requirement that in reactor coolant channels, you have to measure temperature for safe operation of reactor. So this is the thing which we are developing a distributed FPG-based temperature sensor. And this is a mock-up setup, which is in our lab to convince the people that, okay, this is the work. And this is the photograph of that. Now, this is a prototype. I've told you that each grating you can use for chemical sensing, and this is a prototype which we are making. We have tested our each grating with or without graphene oxide coating. Now, graphene oxide has the advantage that it can specifically absorb certain particular chemicals. And you are seeing that the first one graph is that peak shift as the blending of ethanol is being tested in petrol. Whatever commercial level petrol is there, sometimes because more ethanol is blended than allowed. Where there is a test we have tested putting more ethanol, we can see how the peak shifts. Or another sensor where graphene oxide is coated, we see the predominant effect is the reduce in the peak intensity rather than the wavelength shift. So these are the modes where chemical sensing can be used, either peak shift, you monitor peak shift, or you monitor the shift in the intensity. So these are the reusable sensors. And another thing which recently we are developing humidity sensor, because humidity sensor, as said, they are available. But for various things where radiations are there, where places are very, very small and our conventional sensor cannot go, you can put sensor in devices, fiber sensor in devices, etc. This is again a sort of a humidity sensor, which we are able to measure from 45 to 95% humidity, because it is based on the tilted grating, tilted FBG, where the peak amplitude peak is changing, and from that peak height one can measure the humidity. And the last part of this topic, my topic is that we are also developing another type of sensor which is based on Raman scattering in optical fiber. Here, no grating is made. This is plain optical fiber, but we use a multimode fiber, not even single mode fiber. We use a multimode fiber. And in fiber, because there are amorphous medium, scattering always takes place. And if your light source which you are putting inside is intense, Raman scattering also takes place. And this is the thing, with all the three types of scattering take place: Rayleigh scattering, Billow scattering, and Raman scattering. And the anti-Stokes part of Raman scattering is temperature sensitive. So this is the anti-Stokes part of Raman scattering which we use for the temperature sensing. And the main thing is we develop, and this advantage of this is a truly distributed sensor, because each and every element of fiber is acting as a sensor. Here, three interleaving ideas are used. You want to locate the hotspot, means where a temperature is rising somewhere. Then this is concept of optical time domain reactivity. This is a very usual concept in internet. Wherever these fibers are there, if you want to know where the fiber is broken, ultimately you use this concept. Then you use for temperature sensing anti-Stokes Raman scattering, and this is a distributed sensing. Now, this Raman scattering fiber, I am is going to skip that. This is a common thing, but dioxide molecules are there, and there is a significant shift from, suppose you launch 15 and 50 nanometer, you get your anti-Stokes at 1457 nanometers. It's quite far away. Then you can put a proper notch filter, etc., and can filter out the Rayleigh scattering part, other scattering part. So you can always focus on the anti-Stokes part, which is temperature sensitive. Stokes are not temperature sensitive, but anti-Stokes, because they are originating from the higher energy levels, so they are temperature sensitive. So this is the thing which you have developed with Raman-based optical sensor. Ultimately, you are seeing that suppose some hot spot is there. Wherever some hot spot will be there will be increased anti-Stokes signal. And you can always, because optical time domain reflectometry you are using, you can always locate the which spot it is coming. And this is a typical anti-stroke signal. You will see as you're increasing temperature, how the signal is. And this is the strength of this signal that gives back as the temperature. And this is a typical principle of optical time domain reflectometry that suppose you take some fiber and your laser is there and say, suppose, for example, some fiber is broken somewhere and all along this thing, the light will be scattered and it will be more, it will be reflected also from somewhere it is broken. So then you can see that from this back scattered signal, you can find out the location of from where it has happened. And instead of splice, if temperature of source is also there, then this is the equivalent situation. Instead of a fire being broken, you have a temperature source there. So now this is a typical setup inside of a Raman-based sensor. You see the diode pump solid-state laser is, and then because Raman signals are very, very weak, okay, 2 minutes only.
Yeah.
Then, okay, Raman signals are weak, so you have to use electric amplifier. So this is the typical inside of this thing. And whatever I am telling, all these three technologies, FPGs or Raman based, these are all commercial firms are now using us for technology transfer and all these things. So we are working out all these things. Now this is the typical specification of a Raman based sensor. Here only thing is the special resolution is 1 meter. That is poorer than the FBGs because FBG you can measure up to say a few centimeter. But then this sensor, if you put say 1 kilometer long sensor, you don't bother. 1 meter is also good enough. So this is complementary to whatever is developed. And this is a typical example where we have used Raman sensor. You know, I told you that Indus 2 source, our here in RRCAD, they have 172-meter ring. And all along the ring, this cable is going on, which give power to dipole cable and to very high current, 1000 ampere current is flowing. And we have to measure temperature. And there is no way one can go inside that small, you cannot put a lot of thermocouples. So this is where we installed our Raman-based sensor. And this is now giving all along the 172-meter ring, the temperature profile. So suppose any place temperature increases, we'll get an alarm. Then we can take corrective action. So this is the last slide. And so after all this thing, I hope I am able to convince, only a few examples I have shown what we did. It is fiber backdating or fiber sensor, distributed fiber sensor or standalone point sensor. There are so many applications, so many fields, oil and gas, pipeline, wind energy, geothermal, avionics, military, shipboarding, homeland security, and infrastructure. Lot of application civil infrastructure especially, huge application potential exists. So this is the last slide, conclusion. So optical fiber sensor is uniquely placed between science and engineering discipline. We are making different type of sensors, LPG, FPG or Raman based, and they are all complementary in scope. And there is a huge scope for these sensor deployment, capital intensive circuit, national security, variety of research installations. And there is excellent opportunity for developing innovative products, patents, or innovative applications, thereby establishing group point of excellence. And most welcome to utilize whatever we developed at RRCAD, FBG or LPG fabrication facility in collaborative research mode, aimed at developing the project. And thank you. And this is the acknowledgement. I acknowledge my colleagues. Thank you.
Thank you, Dr. Dikshit, for a very nice exposition on the work on fiber sensors. So, Joby, how are we handling the questions and how do we get
in the chat window? If the participants have a question, they would put it in the chat window. Then you will have to read that if there is anything in the chat.
Right now, there is no question. So I don't know.
I don't see any question.
No, is this chat window that we are seeing is the same with the participants? I mean,
yes, correct. Chat window is the same for everybody.
Okay, fine. So, Dr. Dikshit, I just wanted to know, have you tested the longevity of these kind of sensors? I mean, with time, does the grating stay or?
Yes. Actually, what problem is that you cannot test for the long time. Only thing is we do accelerated testing. Suppose I have a temperature sensor for destined for 300 days centigrade. What we'll do, we will do accelerated testing in the sense we will put at 500 or 600. And from that, we guess the idea how much it will work. So our that a sensor, say you take a typical type 1 sensor which is operating up to 100, 200, it will work for 10 years, about 10 years,
Okay.
without any problem.
But have you any deployment? I mean, I saw one you deployed in 2017. That is still working fine?
It's still working, yes.
Okay. Okay. That's very good. Right. Okay. All right. Professor Kelsey, any question? Those who are here, if they have any question. Okay. If not, thank you very much, Dr. Dikshit. And thank you for joining here. Okay, we move on to the next talk. We move on to the next talk, which is by Professor Ramakrishna, Anant Ramakrishna from IIT Kanpur, but currently based at CSIO. He's the director of the CSIO. Ananta, are you here?
Yes, I'm here.
Okay, I can see you. Good morning. Yeah.
Good morning, sir.
So, So let me introduce, although he's rather well known, but it's my pleasure and duty to introduce. And I will, just a minute. Yeah. So Professor Ramakrishna is the director, as I said, at the CSIO Chandigarh, on leave from IIT Kanpur, where he's actually a professor for a long time. And, he did his undergraduate graduate studies at IIT Kanpur, then it is PhD from Raman Institute, postdoctoral with at Imperial College with Sir John Pendry, and since 2003 he has been at IIT Kanpur. He has, of course, been recognized very well with prestigious Shantashri Bhatnagar, which he deserved very well. And before that, he got the Sword Jayanti Fellowship and the INSPIRE Young Scientist Medal. So we have an illustrious professor who is going to give us a talk on anisotropic nanostructured metamaterials and their applications. Professor, please go ahead.
So,
you have 25 minutes.
Yes, thank you. So I'm just sharing my presentation. I hope you can see that. Yeah, great.
Yeah.
So thank you, Chairman, and I thank the organizers very much for giving me this opportunity to be with all of you in this wonderful conference. So what I will be talking to you about are certain anisotropic nanostructured metamaterials and certain applications that we developed for them. So this work was all conducted at IIT Kanpur, where I was there till just a few months ago when I have moved to the CSIO at Chandigarh. Now, we all know, metamaterials, they have become very common. Today, these are composite materials with structural units much smaller than the wavelength of radiation. And these display properties not usually found in natural materials. And it is the structure of these materials that actually give them their property. Typically, you are depending on certain resonant properties. And these resonant properties give rise to nice dispersive properties, which is what you utilize for controlling radiation, typically. So one of the nicest definition of a metamaterial came from Roger Walser in 1999, where he said that these should be macroscopic composites. They are man-made, they are three-dimensional typically. They should be three-dimensional, although typically in applications they are more often of lower dimensionalities. And they are periodic because, you want all part of the metamaterial to have the same property. And they should be multifunctional because you want them to produce an optimized combination of two or more responses to excitation. Because if you go to all the way to the trouble of making many kinds of structures, you want it to give you more than whatever an ordinary material gives. You want much more than that. So metamaterials have been designed to, show all kinds of electromagnetic properties. For example, very large dielectric permittivities, permeabilities, zero permittivity, permeabilities, negative numbers, which caused a lot of excitement for about 10 years when people were talking of negative refractive index materials. And typically what you will find is these metamaterials, unless you construct them extremely carefully, they will not be isotropic. They will be anisotropic. But the properties can render extreme anisotropy. When I say extreme, for example, if you take a lithium niobate crystal, your refractive indices in different directions for polarization in different directions may differ by about 1 part in 100 or 1 part in 50 at most. You don't even get that much. But in these metamaterials, you could have anisotropy such that your polarizability in one direction could typically be literally infinite, and in the other direction, it could be 0 or it could be negative, and so on. So this kind of extreme anisotropy is something we have not seen in optics at any time. And these kind of anisotropies can render the indefinite permeability or permittivity tensors. So the material will start having hyperbolic dispersion. I'll come to that thing, and we never know of such materials which have hyperbolic dispersions. So I'll, for sake of time, I'll just skip through certain slides, and I'll just come down to the design of metamaterials which can be highly anisotropic. So if you take the thin wire array, which was the first metamaterial proposed by John Pendry in 1996, what it does is it just orients wires. It could be wires oriented in all the 3 orthogonal directions, which would make it isotropic. These wires, when they are very thin, they are placed in a period which is much smaller than the wavelength. So when an incident electromagnetic radiation is incident on these wires, the radiation does not individually sense these wires. They just sees on an average, there is so much of conducting material in space, and the conducting material is very small. So it is like a dilute metal, but with a very specific thing. It sees continuity only in certain directions. But if it is continuity in all 3 directions, this would be isotropic. And this, for example, if you had 3-dimensionally oriented wires, this system would look like a plasma. But the plasma frequency would be much reduced to what it would normally be, because the wires are not everywhere. They're present everywhere in space. So the effective electron density is very small. And also, since the wires are very thin, these wires have extremely large inductance. So that prevents the currents from changing very rapidly, the induced currents, which is equivalent to thinking about it as that the electrons that constitute the currents have become very sluggish. They don't really move, change. They have a lot of inertia. So it's as if the effective mass of the electrons has become very large for this effective medium. So this array of wires, subwavelength spaced wires, thin wires, looks like an effective medium to radiation, which is a plasma with a plasma frequency which can range from few gigahertz onwards. And that was the big achievement. So, but then typically what happens when you talk of nanostructures is, well, you can create such wire arrays. For example, you can take a nanoporous alumina and electrode deposit silver wires into those. But what happens? You have nanoporous the alumina, the pores are linear. And then when you deposit the wires, you get long wires in one direction, nanowires. But then these are all oriented in one direction only. So the medium is extremely anisotropic, whereby you have metal-like response for polarization along the wires, and perpendicular to the wires, you get a dielectric-like response. So the metal-like response here in the bottom, I have just shown that you can, you just can think of it as a, average dielectric function between the metal fraction of the wires and the dielectric fraction of the nanoporous alumina here. There are some other ways also whereby people have developed oriented metallic wires. For example, they could grow them in solution and orient them with an applied electric field while during the growth process. So there are many multifold ways of producing oriented wire arrays in nanostructured materials. So the other thing that I had mentioned was when you have these, when you think of these dielectric permittivities, which along the orientation of the wires looks like a metal or a plasma, that means it's negative in that direction, the dielectric permittivity, and in directions perpendicular to these plasmas, in these directions, it just looks like a dielectric material. So it is a positive dielectric permittivity. So if you think, for example, what would be the dispersion of a wave in such a medium, it's anisotropic. So the dispersion for a wave propagating in the XZ plane would look like that, where epsilon z and epsilon z as the dielectric permittivities in the corresponding directions. Now what happens is if one of them is negative, let's say along the epsilon z, then this equation changes from an elliptic equation to a hyperbolic equation. The equi-frequency surfaces become hyperbolae compared to the normal ellipses that we have. And what does that mean? It means that if you when you are trying to couple in from air into a medium, let's say you are coming along in the kz plane with a wave coming in like that, the parallel momentum along kx get conserved. So if that is the circle is the dispersion in free space, this wave vector, for example, would be projected onto the hyperbolas in the hyperbolic dispersion for propagation in the medium. And you could have very, very different kind of refractive phenomena. A couple of examples are shown here. And even these are new phenomena. But there are many more implications. For example, if you had an evanescent wave from a source placed very close to the surface, such a kind of a surface, those evanescent waves which are off shell, these momentum vectors are larger than this phase space vector here. Those will be off shell and they would still be able to couple to propagating waves inside the hyperbolic medium. And this is one very big difference. Such hyperbolic media, anisotropic metamaterials, they offer very new possibilities of coupling light out from the near field of sources. Now, on the right-hand side, I have shown another way in which such anisotropies can be realized. You just take a stack of very thin films of, let's say, silver and silica, and if you do an effective medium theory, you would find that one of them, the permittivity along one direction would be negative, another direction would be positive. So there are various ways of realizing such hyperbolic media, and these have been realized in various contexts nowadays. And I will be talking about specifically thin wire anisotropic media, and that too in cylindrical geometries, because then you find that you have waveguides which you can fill with anisotropic media, and very, very interesting novel phenomena become possible in such waveguides. Now, for example, here, let us take a cylindrically symmetric anisotropic waveguide where the dielectric permittivity and permeability can be, in general, theoretically, they can be in, diagonal in the radial coordinates. Then if you consider a wave that goes through, of course, what you do is you just solve the Maxwell's equations, and then you write down solutions, assume propagating solutions inside the waveguide and look for conditions for the propagation constant. What you find is there are possibilities of how solutions can propagate. And to cut a long story short, what happens is you get modes which are described by Bessel functions for the spatial distribution in the radial and azimuthal directions. And you have a propagating wave along the Z, the axis of the fiber. But then these Bessel functions turn out that if you have anisotropy, extreme anisotropy, where the dielectric permittivity, let's say in one direction is positive, in the other direction is negative, the orders of these Bessel functions become imaginary. We are typically used to having imaginary arguments, whereby the Bessel functions would indicate an exponentially decaying function along the radial directions. But an imaginary order means these are functions that keep oscillating, and as you go closer to the origin, where in these there's a reason for that, these functions start oscillating very, very fast. They are actually reminiscent of functions like sine 1 of x, which have an essential singularity at the origin. And this essential singularity is not accidental. Well, the essential singularity was already there in our fiber at the origin, because when you define these radial coordinates, there's already a singularity at the origin. You don't know how to exactly define it. And hence, actually, what we do when we calculate to avoid that essential singularity at the origin, we actually exclude a certain small volume around the origin. We either say that there is a conductor there, in which case this becomes a reasonably homogeneous system if you have a conductor there and outside, or if you can have a dielectric isotropic medium there inside and outside, it will be an inhomogeneous system, but you can solve for it. And we have done that. And it is very important to exclude the origin in all these calculations for avoiding that singularity. So what happened? What is the real properties that we really see with these Bessel modes with imaginary orders is that you will see that, at the top, I have shown what happens in a normal positive index fiber. As the mode number increases, as the mode number M number increases, you will find that the modes increasingly vacate the center of the fiber, and the mode structure moves, the electromagnetic fields move more towards the periphery. And in the extreme case, when the M number becomes very large, these become the whispering gallery modes. But on the other hand, at the bottom, I have got the Bessel these modes described by Bessel functions with imaginary orders. What happens is, as the M number keeps increasing, the modes really do not vacate the center of the fiber. In fact, they start populating more and more, although they are oscillatory near the origin. They start populating more and more. The intensities actually start growing more and more near the center of the fiber, and this has certain physical implications. What actually is the case, which I will not present here for due to the shorter time involved, is that there is a caustic at the center, which actually determines why everything comes to the center. The angular momentum is actually the reason in this particular case. So the question is, how do we realize this kind of an anisotropic system? Well, what you typically do with aluminum to realize nanoporous alumina is you take a sheet of aluminum and you anodize it in an acid bath. And due to, if it is extremely pure and you hit the correct conditions of the anodization voltage and temperature, potential and temperature, the aluminum starts getting converted into aluminum oxide. That's a highly exothermic process. There's a very thin layer of impermeable alumina at the bottom through which the electrons tunnel. And the exothermic energy that is there at the bottom and the partial solubility of the alumina in the acid causes a porous structure to start forming. And these porous structure organize themselves into a hexagonally ordered lattice because the self energy of the interactions, the energy of interactions is minimized in that kind of a lattice, hexagonal lattice structure in 2 dimensions. So what you eventually form are these lattice structures, which are very long, tall, long pores, which are completely nice, parallel and very nicely organized in space. So to actually convert this into the cylindrical geometry, we had to do quite a bit of experimentation. My PhD student in about 2015, he developed these micro aluminum wires. He figured out the right conditions to anodize it such that you are left with an aluminum core at the middle, and then these nanoporous alumina form themselves. And because the geometry was in the cylindrical thing, these pores are radially converging. And here are some of the experimental realizations of that system, where you could actually anodize, and you can see that the nanoporous in these cross-sectional SEM images, the nanoporous alumina forms here. These are cleaved images. This is a cleaved fiber. And these are nanopores which extend from the exterior all the way to the interior, where you have an aluminum core. The aluminum core can completely be etched out using an acid, and you can have a hollow core fiber as well. And here are a couple of examples where you can see that light is actually being transmitted along the fiber, and we could make fibers extending about a few centimeters. And longer can be made, but then to etch out the central aluminum becomes more difficult. But that is what you can do. I request people to switch on the audio. I'm getting some noise.
Mr. Vinay Kumar Sahu, so please mute yourself. Yeah. Okay.
Thank you. So as I mentioned earlier, you can more effectively couple the radiation from near field sources using such hyperbolic medium. So to cut a long story short, when you look at the source, there are fields, two kinds of fields associated with the source. There's a propagating far field component, which is what you see far away from the source. These are propagating waves. And there's a non-propagating evanescent near field component. They consist of, you can think of them when you also as plane waves with very large transverse momenta, so which prevent the propagation in the direction perpendicular to the transverse components. You cannot usually couple these near fields to an optical microscope. That's why you say that there is a limit on the transverse momentum you can use, and that you can detect, and that gives the diffraction limit on what you can measure in a microscope. But you can, for example, take a very tiny tip very close to this near fields, and you can scatter some of these near fields into propagating modes into a fiber. And that's how you do scanning near field microscopy. The light from the small fiber tip is either scattered into an optical propagating mode in the fiber. But the coupling efficiencies are typically very poor, less than about 1 in 10 billion, 10 billion or so. And that's because there is very poor mode mismatch. The near field is very, there's a, your fiber modes are very broad. I mean, they are delocalized over very large areas, whereas the mode that you're trying to couple it to, couple out is localized into a very small volume. So typically what you do is, you try to butt couple it, but it doesn't work because of this mode coupling. So another way you do it is to actually couple it along the edge into the whispering gallery modes of a fiber, because there's a better momentum coupling in the momentum matching or phase matching in that particular case. But what we have done is we say that you can take these fibers of these, which are made out of anisotropic alumina, inside the holes you put in electrodeposit silver or any other plasmonic material. So now these become hyperbolic dispersive, and you can make the nice little tips out of those, or you don't even need to make tips if your only purpose is to couple light from the near source and not localize it. You can just take any of these fibers, cleave it, and put it very close. What happens is that these hyperbolic fibers have modes which practically have no lower cutoff because of the hyperbolic dispersions. So here are examples where you can have effective modes. Just 1 minute, please. Yeah. So you can have very, very nice, high index transverse momentum modes inside these fibers, which can actually propagate in these fibers. The reason is simply because of hyperbolic dispersion. I'm not getting into the mathematical calculations here. And, the amplitude inside the fiber then decays, of course, but it decays very, very slow compared to the evanescent decay. The decay is mostly due to absorption. So it will decay over distances of few wavelengths, but after that you can adiabatically couple it into any other ordinary fiber. So these kind of fiber tips we actually investigated. Without any narrowing also, you get a very good coupling. With narrowing, you get better coupling. These are the cases when we take a fiber and consider what is the light that couples out from a dipole source. These are calculations. And even if you narrow it, the coupling received power at the other side decays in a very similar way, or only the localization in the horizontal position actually improves. So you can actually have micron sized, 1 or 2 micron sized fibers in which you have anodized the outer surface. We can do that. Actually, we have done that in many cases. And you can use them as fiber tips to couple radiation much better from the near sources of many sources. Near fields can be coupled very nicely, and you can also have inhomogeneous fibers or homogeneous fibers. The inhomogeneity of the fiber does not appreciably change the rate of rates and so on. So we have done a very detailed study. So I'll just mainly draw your attention to the table out here, where we have looked at what is the amount of radiation that couples out for various kinds of hyperbolicities and an isotropic fiber. So at a distance of about 2 wavelengths from the tip of the fiber, if you had an isotropic fiber of these similar dimensions, the coupled energies would be of the order of 10 power minus 17, so practically not detectable at all. But if you take a radially hyperbolic fiber, whereby what I mean is that the wires should be radially oriented, as in our alumina-based fibers, your coupling can be, you would have about 10 power minus 6. The amount of, it's about a million, less, about 1 in 10 millionth compared to 1 in 10 billionth for a tapered fiber tip. This is already 1,000 times more efficient. There's now I will, so this is one particular application which we have worked on. There are multiple such applications which can be worked on. So one thing that we have very clearly shown is that such fibers with radial anisotropy, which can be physically realized in aluminum microwires, which have been anodized into alumina and filled with the nanopores filled with silver by electrodeposition. There we can have 1,000 times better coupling for near field coupling of sources or for near field scanning microscope. This is something that we have very clearly determined. Now, there's another context in which we have worked with these kind of anisotropic metamaterials, which is we grow these sculptured thin films of such materials. And this is a well-known field where you can actually grow by deposition at very large oblique angles, made thin films which grow as columns. So instead of getting into the details of those, what I will do is I'll just say that how we have actually grown thin films of silver, and when we grow them on pre-patterned substrates like a periodic grating, these nanocolumnar silver nanocolumns actually preferentially grow only on the ridges of the grating, and in the depths in between there is no growth of such a material. So now there are unique plasmonic properties associated with such thin films. If you can think of this thin film as an effective medium, this effective medium has a metal-like behavior when you consider the direction along the rods and perpendicular to the rods. Again, it's like a dielectric medium. And now you have periodically patterned these, so you have made a grating of an hyperbolic medium effectively. So we have done a lot of studies on this. Yeah, sure. I'll just be finishing almost. Yeah. Thank you. So we have made a lot of such films, and we have determined the dielectric permittivities of these by homogenization methods and so on. And this graph encapsulates that. For example, along the rods, you have a dielectric permittivity, which is spectrally like a plasma, and perpendicular to the rods, you have a positive direction. The unique thing about this is that when you look at the surface plasmon dispersions on such a thing, and if you look at how you can couple to it, suppose you just focus light onto it, and you measure the surface plasmon dispersions, by looking at the transmittance through such things, angle resolved transmittance. What happens is you find that you only couple to one branch. What you're doing, and the other branch, there's barely any other coupling. That's true for any different orders. So what happens? What these films are doing is they are enabling you to couple unidirectionally to plasmons propagating in one particular direction, and that is true with a linear grating. You can choose which side of which direction should the focus light actually couple to, which to plasmons propagating along which direction. Now, when you actually make it two-dimensional, you can actually decide which exact direction at a particular wavelength will the plasmons actually propagate. That is simply a result of the anisotropy. And we have shown, for example, you can change the directions of the silver nanocolumns dynamically by ion beam irradiation and so on. And the more very interesting thing that we have actually done is we have used the anisotropy and we have used the anisotropy of these nanorods and shown that when you take nanodiamonds with nitrogen vacancy centers in it, the output light from these nitrogen vacancy centers will preferentially couple to these silver nanorods, which now act as very nice antennas to emit the light, and you can enhance the emission of light from these things. I mean, we did some very detailed experiments consisting of maybe looking at emission from hundreds of such centers and so on. These results were published earlier, but I will just give the net details. The net details is that you can enhance the emission of light from sources placed in these nano structured gratings. Unfortunately, our nitrogen vacancies were not single, so we could not really look at the photon statistics and determine that there was a reduction in the lifetime because we were getting multiple decays. There was a distribution of lifetimes for different nano diamonds, but we could very clearly show that that there is an enhancement in the emission, but that could not be demonstrated as an equivalent reduction in the lifetime. So we were not successful in showing actually single photon these systems as a device for single photon emission from these nitrogen vacancies. But there's a lot of orientation at the placement of the nanorod diamonds and the orientation to the nanocolumnar dipole axis is actually the determination factor, and the orientation, the control over the orientation which we have actually enables us to think of new designs whereby we can create efficient emitters which emit along certain directions very efficiently. And there you're utilizing a lot of the near field to couple into the system and use the silver nanorods as nice antennas, nano antennas. So that is, sir. So I thank you for your patience, even though I think I must have exceeded the time a little bit. Thank you. I think you are muted.
So thank you very much. There is a question here. And can you hear? There is some. Ramakrishna, can you hear?
Yes, I can.
Okay. So what is the physical meaning of negative and positive permittivity? That is a question. And why metal possess negative permittivity after a certain frequency? That's a very basic question that, student must have asked.
Whenever it's like this, when you take an oscillator and you force it, usually, there's a forced response. So the response, if you are forcing at low frequencies, will be in phase with your forcing it up. But when you have a resonance in such systems, when you force the oscillator at frequencies just above the resonant frequency in a certain band, the response of the resonator is antiphased. That's a natural response of all resonators. So there's a phase jump by pi that happens on all these systems. So with a metal, you do not have a resonance, but you have free electrons. So you're already at you can think of it as the resonance frequency being 0. So you're already at frequencies above the resonance frequency. So within a certain band, which is determined by the density of electrons, which is called the plasma frequency. So from 0 frequency to the plasma frequency, there's electrons nicely move antiphase to the input field and screen out the interior of a metal from the applied electromagnetic field. So this negative response is what is manifested as the negative permittivity, and that happens until a frequency called the plasma frequency. At frequencies above the plasma frequencies, it would be positive dielectric permittivity. So this is what a negative and positive dielectric permittivities are. Now, the reason that a metal has the negative permittivity also, I think I explained, because there are free electrons which nicely screen out the interior of the metal from an applied electromagnetic field.
Okay. Thank you very much. Thank you for a nice
So,
talk.
Amita, just one question here and there.
Yeah.
So, this your hyperbolic fiber, during the fabrication, what are the tolerances one should keep in mind?
See, there are many details I could not present. I will tell you what happens is, you see, the wire thickness, the initial wire thickness that you start off is a very determining factor as to what is the fill fraction of the pores that you get. Because, it's a radial geometry. So if you start with a thick wire, the pores, when they start happening, they happen at a certain distance from each other, depending on the nature of the acid and the nature of the potential applied and the temperature. These are the three determining factors. So when you start etching, they start etching and start going in radially. So as you can see, the distance between the pores starts reducing when you are inside, and they are actually larger when you are outside. But the pore size also actually starts reducing. So the fill fraction is not actually constant. It changes with the rate as a distance of along the radial distance. So almost every fiber that we make is actually inhomogeneous. So the corresponding calculations have to be done, and we have done to get the mode structure, but they are not very significantly different from the case of the homogeneous anisotropic case, which I presented here, the mode structures, etc. But there are certain specific differences as to whether there will be a cutoff or not. So the initial wire thickness is a determining factor, and many times what we do is to get a thinner fiber, and depending on what period we want, we start with the thicker fiber, etch off the alumina, and then continue. Or sometimes we etch the aluminum wire to the thinner dimension and then start the anodization, so we get a different spacing. So those are the real things that we have to do. The handling has to be very, very careful. These are very fragile objects. There's no clad or anything here right now.
Thank you.
Thank you very much. Now we move to the next talk.
Thank you very much.
Thank you.
There's some echo coming.
There is some echo is coming. Professor Joseph Rosen, are you available? Your video, please.
I'm here. Do you hear me?
Yeah, we can hear you. Yeah. Hello, how are you? Thank you.
Yeah. So the next talk is by Professor Joseph Rosen, who is a Benjamin H. Swick Professor of Optoelectronics at Ben Gurion University of the Negev in Israel. And he has been an alumnus of Technion Israel Institute of Technology, getting his post-graduation as well as PhD degrees. He's a fellow of the Optical Society of America as well as of the SPIE. And he has wide research interests, including in holography, image processing, microscopy, diffractive optics, interferometry, pattern recognition, biomedical optics, optical computing, etc. He has more than 200 scientific papers, book chapters, and conference publications. So, and he's going to speak to us about recent developments in optical imaging by coded aperture correlation holography. And he has 3 Indian co-authors, so he's really a friend of India. So welcome, Professor Rosen, and go on with your talk. You have about 25 minutes.
Okay, thank you very much for the nice introduction. And thank you for inviting me to give this talk. I'm going to talk about coded aperture correlation holography. I would like to mention my partners on this project. Vijaya Kumar Anand, Angika Bulbul, Nathanael Chai, and Mani Rai. Here is the outline of my talk. I start with the introduction about coded aperture correlation holography, and then I move to talk about the coach under coherent illumination. Then I go back to incoherent light to talk about depths of field engineering. And I will finish with words about synthetic aperture imaging. So the initial goal of a coach, of a interferenceless coach, was to do three-dimensional imaging with incoherent light and without two-wave interference. So the way we published the first paper about this in Optics Express in 2017, and we see here the optical system. We use spatial light modulator, and on the SLM, three phase masks displayed one by one. The phase masks are designed in a Gershberg-Saxton algorithm. And in the first stage of the imaging, we do a calibration. We create a library of point spread holograms by moving the point source along the z-axis, and for every z location, we record three intensities distribution for the three masks. We see it here, and superpose it in the computer to get a point spread hologram for every location of the point along the z-axis. After the calibration stage, we move to the imaging, and we put the input object somewhere in the range of the z range, and with the same phase mask, we take again three intensity response, superpose them, and get the object hologram, complex valued object hologram. And finally, in the computer, we cross-correlate the hologram, the object hologram, with all the library of the point spread hologram. And with one member of the library, we get the reconstructed image, and we can figure out its Z location. And by that, we can do a three-dimensional imaging. So the next project was in 2019, was to extend this concept to coherent light. And in coherent light, we use 4F system where the SLM is in the Fourier plane. And on the SLM, one by one, we display a two-phase coded phase mask, again, synthesized by a Gershberg-Saxton algorithm, where the constraints on the camera, the response, the point response of this mask is randomly distributed dots over the area of over the plane of the camera. And we take two intensity response, subtract one from the other, and get bipolar hologram, bipolar point spread hologram. This is in the calibration stage, and then in the imaging stage, we have now the two response to the object, and again bipolar object hologram, and finally a cross correlation between the two holograms give us the reconstructed image. We can optimize the number of dots on the camera plane by looking for the maximum SNR and maximum contrast or maximum visibility. And when we have the optimal number of dots, we can also do three-dimensional imaging by multiplexing on the SLM two or more sets of coded phase mask. And we see here two plane imaging, where one point spread hologram it can reconstruct the distant object here in focus, where the gap between the two objects is 10 millimeters, 15 millimeters, and 20 millimeters in three different experiments. And by using the other PSH, the other point spread hologram, we can image in focus the lower object, the closer object to the system. But the next project was to try to do a quantitative phase imaging with COACH, with coded aperture correlation holography. And for that, we added to the 4F system a reference beam tilted with some angle to the object beam. And now we can use only a single phase mask displayed on the SLM, get with one-shot imaging the hologram. Next, we remove the grating from the hologram by filtering out the first diffraction order in the Fourier plane in the computer. Get replication of the phase object, and by cross correlation with the point spread hologram, we get the phase map. In this case, two microspheres in the size of 6 micron, and we compare it to an ordinary holographic system implemented with open aperture on the same Mach-Zehnder interferometer, and we see that our technique has less noise than the ordinary holographic method. And another example of this system with binary object resolution chart with a height of 250 nanometers. And we see here the initial hologram. After filtering, we get the replication of the object. And after cross correlation, we see the phase map of this binary object. And again, we compare it to an ordinary holographic system, and we get less, we see here in the table, less error, mean square error, and a more accurate value of the step of the object. And the last project with the coherent light was to try to do the same quantitative phase imaging, but without reference, by on-axis system without reference and in a single shot. So we take again the same 4F system, but now without the reference, and on the phase, on the Fourier plane, the phase plate is now phase of half pi only in the center of the plane. All the other phases are zero phase. And by doing that, we convert the phase object to a phase contrast image. We take the phase contrast image to the computer and use modified Gershberg-Saxton algorithm that jump from the camera to the object plane by correlation, and in the middle, in the Fourier plane, we multiply with we once multiply with multiply the distribution with the faceplate, and then we divide in the lower branch. We divide with the faceplate, and by few iterations, we get the phase map of the object. And here are the results with two example binary objects of a step of 150 nanometer and 250 nanometer. These are the phase contrast images. And after the iterative algorithm, we get the phase map here. And also we checked what happened without the faceplate. And we see that we don't get the image contrast, and therefore we cannot reconstruct the right phase map. And here another example of a non-binary object, the 6 micron microsphere. And again, we get the phase map. And when we compare it to the previous method, we see that our values in this on-axis system are more accurate. The values of the steps are more accurate, and also the 6 micron, the diameter of the microspheres are more accurate. And here we see the convergence after 10 iterations. Only 10 iterations, the error is less than 10 over minus 3 from the initial error. So the convergence is quite fast. Now we go back to incoherent light. And in this project, we did depth of field engineering. The goal here is to extend the depth of field and also to take several sub-volumes, separated sub-volumes, in this example, 2 separated sub-volumes, and all the objects inside the sub-volumes, we want to see them, to reconstruct them in focus, like as they are located in the same plane. This is our goal. For this goal, we display on the SLM a composition of 3 or product of 3 phase masks, quadratic phase mask or diffractive spherical lens, shown here, and the goal here is to define the location of the sub-volume that we want to image. We use radial quartic phase function, the expression is given here, in order to define the axial lengths of the sub-volumes, and we use, as before, the coded phase mask in order to do the imaging. By the response of the point response of the coded phase mask is again sparse, randomly distributed dots on the camera plane. So this is the composition of the 3 phase masks, and here are the results: direct imaging, regular imaging with a single lens, and we have object distributed in 2 different axial location along the z-axis, and of course we can only see one object in focus by one lens, or to use another lens to see the other object in focus. But when we use the coded aperture correlation holography with the 3 phase mask, we get both object in focus without losing resolution. And another example, again, direct imaging, regular imaging with a single lens, and with the coach, we see both objects in focus. Now the last example, if we want to image 2 separated sub-volumes, we have to multiplex on the SLM 2 sets of phase mask. So the upper set is displayed on the black rings, and the lower set is displayed on the white rings of the SLM. And we added here 2 linear phases with a different sign in order to separate objects that are on the same sight line. We don't want them to cover each other, to overlap, so we added here a linear phase to each set, different linear phase to each set. And now we see the example. Here is direct imaging with a single lens, and both objects are on the same sight line, so they cover each other, overlap. But when we reconstruct with one point spread hologram, we can see only one object from one sub-volume, if we cross-correlate it with the second point spread hologram, we see the other object. And when we use the same CPM for the two sub-volumes, and therefore we have one point spread hologram, we can see both objects, and they are separated because of the linear phases. They are separated and do not cover each other or do not overlap. Okay, this is the this is now the last project that I'm presenting here. I'm going to talk about synthetic aperture, incoherent synthetic aperture imaging. But before that, I mentioned the partial aperture imaging with Coach. When we have a system with full aperture in regular imaging with the lens, direct imaging, we get a nice image. And when we do it with a Coach, we get similar image. But when we use partial aperture with direct imaging, we have here 8 holes or 8 openings distributed along the perimeter of the aperture. And in direct imaging, we get a low resolution image. When we do it with a Coach, the result is much better. So Coach has the property that we can do partial aperture imaging without losing much resolution. So next, we asked ourselves, can we do it in a synthetic aperture mode, which means to, in every given time, to open only 1 or 2 openings and to collect all the images and get the same original resolution. And the answer is yes, we can. So this is the goal of the project of synthetic aperture. We call it synthetic marginal aperture with revolving telescope, SMART. And we want, the goal here is to process light from object over time and from different points of view, from different openings of the aperture, and to get the same resolution as it is a single shot and taken from the full synthetic aperture. So first of all, we cannot do it with a single opening. We must use, in every given time, we must use 2 openings, and we have to use all the possible permutation of 2 openings. So we see here for 8 sub-apertures, 8 openings, we have 28 permutations, and we have to take the images from all these permutations, and the results are seen here. First of all, a single pair. In direct imaging, of course, we don't get much. We get a low resolution image. With Coach, the resolution also poor because we use only a single pair of openings. But when we do it with a SMART, with a incoherent synthetic aperture, and we use all the 28 permutation, we get a high resolution image, and we can compare it to Coach with the same full single shot synthetic aperture, and we see that it's similar. But when we compare it to direct imaging, it's much better than regular imaging with the same aperture. And the last project is to try to do the same incoherent synthetic aperture with a single opening. And we managed to do it. And the trick here is to take one opening, one channel or one sub-aperture in any given time. But before the SLM, we actually split the light to 2 orthogonal polarized beam. One is polarized in the orientation of the SLM, and therefore it is affected and modulated by the SLM. But the vertical orientation is orthogonal to the axis of the SLM and pass without any modulation, pass the SLM without any modulation. Then we combine back the two beams and interfere them between them. And by that, by scanning all the aperture of the SLM, we can get a single channel incoherent synthetic aperture. So here we see the coded phase mask. We take coded phase mask designed by Gershberg-Saxton algorithm. We attach it to a quadratic phase mask, and we block all the, in any given time, we block all the other aperture and open only one channel, one sub-aperture, and get this on the SLM. And after the composition, we collect all the holograms, and we stitch them together to one full hologram, one full aperture hologram. So we see here the hologram, mosaic hologram of a point spread hologram, when we use here 8 times 8 sub-aperture, overall 64 separated channels. We see here the magnitude and the phase of the hologram. So for every channel, we use a phase shifting. So we have actually three shots, and we get complex valued hologram of a point and complex valued hologram of the object, and we cross-correlate them between them and get a high resolution image of the object. Here we see the process if we use one single channel, and we increase the number of channels on the SLM from 1 to 16, 32, and so on, up to 64 subchannels, 8 times 8. And we see that the mean square error and the resolution is improved as we add more and more sub-aperture. And when you compare it to other methods, so we see here the results of a coach with single aperture, poor image, but we have here full 64 channel, and we can calibrate the location of the camera between 0 to the focal length of the lens. And we see that as we move the camera far from the SLM, the resolution is improved, but the efficiency and is reduced, and the noise, the signal to noise ratio is increased. And when we compare it to direct imaging with a single aperture, it's much better. But when we compare it to a full aperture of coach and direct imaging, the results of full aperture direct imaging single shot is better than the results of the synthetic aperture. Okay, so summary. In coherent light, we can adopt the coach from incoherent to coherent light to do 3-dimensional imaging, and we can also do quantitative phase imaging by 2 different methods. And in coherent light, if we integrate 3 phase masks, we can control the depth of field, and we can engineer it to more than imaging of one sub-volume. We can use multiple sub-volumes by multiplexing few sets of these 3 masks. And we can also do synthetic aperture with a 2-channel, 2 openings, or with a single channel, single opening, And this is almost 100 years after the first demonstration of incoherent synthetic aperture by Michelson and Pease in 1921. So now, and they did it by Michelson stellar interferometer, which has every time has two openings working simultaneously. But so 100 years after that, we managed to reduce the number of channels from 2 to 1. Thank you very much.
Thank you, Professor Rosen, for a very nice talk and many techniques that you have developed. There is a question from one of the participants, which I am going to read. You can hear me?
Yes, I hear you.
Okay. So the question is that we already have lensless inline holography existing to image the objects. Those appear to be using lesser optical components. So how do you compare your technique with those existing techniques? This is from Ms. Ekta Prajapati.
First of all, our technique, the coach, is basically for incoherent holography. And when we extend it to coherent light, we managed to do quantitative phase imaging. So these are the main advantages. First of all, it's very useful for incoherent holography, for three-dimensional imaging, and for synthetic aperture. These are the main advantage, and I don't know about other systems that can do that. And in coherent light, our main advantage is that we now extend it to the field of quantitative phase imaging. And the question if the other method can do it in a single shot in an on-axis method and in very fast way. So these are the main advantages of our method.
Okay, thank you. I have just one question. You know, in this synthetic aperture, the smart technique that you had mentioned, you had taken 8 apertures, sub-apertures, and 2 at a time. You had taken 28 combinations. Is it necessary to do all combinations to get full image, or you can do with lesser number of options?
If you are willing to pay in the quality of the image, you can reduce the number of permutations. As much as you take more permutations, the quality of the image is improved.
Okay. Now, okay, fine. I think that in the interest of time, I will not ask more further. If there are no other, Joby, any other? You want to ask. Yeah.
Hi, Professor Rosen. And by the way, I just want to let you thank you for coming. And Professor Karsing also is here listening to your talk. You might have noticed.
Thank you for inviting me.
Yeah, thank you. And just one question, your synthetic aperture technique, you mentioned at the last that the result is not as good as the full imaging. And the main reason, is it because of the stitching problem you will face, or what could be the main reason?
No, the problem is, you mean this image?
Yeah, correct.
The problem is in the distance. You see here that the distance between ZH, between the SLM and the camera, is equal to the focal length of the lens, which means that we keep what is called this is actually the optimal distance. But in the case of synthetic aperture, we have to bring, because of the efficiency of the hologram, we have to move the camera toward the SLM and to reduce the distance between them. So as much as we reduce the distance, the efficiency is improved, but the resolution and the quality goes down. So this is the trade-off. And this is the reason why these images are less good than these images taken from the full distance of ZH equal to the focal length of the lens.
Okay.
Okay.
Thank you.
All right. I think we thank Professor Rosen, and we move on to the next talk, which is now we have two oral talks. The first one is by Mr. Vinay Kumar Sahu from IG Car Kalpakkam, and he's going to speak on plasmonics of silver network for trace detection and manipulation of metallic oxide IR modes. So, Mr. Sahu, you can start your talk.
Yes, sir.
You have about 12 minutes. Okay.
Yes, sir. My slides are visible, sir.
They're coming. They're not yet come. Yeah, now they have come. Yeah. Yeah. You make a full screen mode. Yeah. Okay. Now go ahead.
Good afternoon. Also, the title of my talk is Plasmonic of Silver Nanonets for Trace and Manipulation of Metal Oxide IR Modes. First of all, I would like to thank Icee for this wonderful opportunity to present my work. With that thank you note, I will just proceed to my next slides. The outlines of the talk goes like this. Initial, first I will give a brief introduction. Then as the title of the talk, it is suggesting we are going to see some sort of effect of plasmon on metal oxide. To be very particular, here we are going to show the effect on tin oxides. That is obviously a technologically important material. I will be explaining how it is important. And going to the experimental part, I have shown how we have synthesized the metal oxide, the tin oxides. And as we are talking about the plasmonic substrate or effect of the plasmon, we have chosen two different plasmonic substrate. One is made up of gold nanorods and second one is silver nanonets. Finally, we will be seeing the effect of these two plasmonic substrate on this metal oxide as well as how they are helpful for trace detection. And finally, conclusion. The introduction goes like this. We know that whenever we'll incident electromagnetic light on some metal surface, the conduction rates start, they will show some coherent oscillation and that will result a very strong electric field. And what is helpful for a well-known known as here we can see the equation. This first, this term represent the strong electric field created close to the metal surface. However, this field helps for the Raman enhancement. Apart from that, one more peculiar phenomena we can see what is recently developed that because if strong localized field is created near the metal surface and if you are going away from the metal surface, then a strong electric field gradient can be excited by the molecule what is placed close to the metal surface, and that will give a different phenomena. So if you see the Hamiltonian of a vibrator and as a electric gradient, that will result a very inhomogeneous electromagnetic field. So the Hamiltonian of a vibration spectra of a molecule kept in the homogeneous electromagnetic field can be represented by this equation. Here you can see lots of nonlinear term, like one term, the second term content dou E by dou R. So this term represents the gradient field, means how the electric field is varying with respect to distance. If it is not, we can cancel all the terms and we will only get the first term what represents spectra. However, in the presence of electric field gradient, we cannot ignore them. And the equation further continues, and finally we'll get with the equation I2 by I1, what represents the ratio between the intensity of the IR peak and Raman peak. What I want to tell, when you are having a strong electric field, the intensity peak will be higher than the Raman peak. So you can see the higher intense IR peak as compared to the Raman peak. Then the question is that how we are going to create this electric field gradient. To answer that, there are several experiments. One of the most important experiment people are doing is deep enhancement spectroscopy. During this experiment, generally what people will do, they will bring a tip with the metal, like metal tip to the surface, and here we can see that will create a very strong electric field nearby the substrate. Apart from that, if you in that image they have shown the imaging of the electric field. It's also very strong near to the tip surface. So this is the configuration generally people will follow to get this electric field gradient. So we thought of a different idea, and with more simpler way. Can we just replicate this kind of structure in a more simpler way? So we thought of making some nano gap, because these nano gaps created by the plasma metals are well studied for the search application. Here, just I want to give one example. Here we can see there is one dimer where one and a dimer. Dimer gives a very strong surface enhanced Raman spectroscopy owing to creation of a very strong electric field. So that idea started to create this kind of inhomogeneous electric field. Then what's going to happen if you keep a molecule in this kind of inhomogeneous field? There are so many studies. Here I have presented one work by another group. Here it is a pyrazine. When they kept under this kind of inhomogeneous field under the torch, they could see peak as well as Raman peak, and the intensity of the IR peak found to be higher than the Raman peak. Then the question arises: what's going to happen for the inorganic molecule? Well, it is very less studied topic in this frame of reference. So we have chosen one inorganic molecule, that is tin oxide. What is a very technologically important material with several applications starting from supercapacitor, waveguide, photodetector, photocatalysis, and FET. In our lab itself, we have shown various applications like supercapacitor, waveguide, and catalysis. So basically, it possesses a rutile tetragonal structure with 6 atoms per unit cell. Hence, it shows some 18 vibrational mode. 4 are Raman active. They are A1G, B1G, B2G, and EG. Here, I am showing a typical Raman spectra of tin oxide. Here we can see the A stand for the bigger molecule, bigger crystalline site. What is showing all the Raman allowed modes starting from A1G, E2G, B2G. However, if to the low dimension, all the peak will be replaced by a broad peak. So there are two questions: how this vibration of the tin oxides of the lower dimension and higher dimension are going to behave under a strong inhomogeneous electric field. To answer that, we have synthesized tin oxide of these two dimensions, first on the smaller dimension and with the bigger dimension. Here the growth slide, like how we have grown this sample. It's grown by a very simple chemical route by the addition of ammonium hydroxide to the stannic chloride. We got first that is known as that refers for the smaller dimension, and after annealing to the 800, we got SNO2 S8. What I am referring, because we have annealed the Celsius. After taking XRD and TEM, we could conclude that the initial S1, the particle size is around 2.4 nanometers to the quantum dots, whereas the annealed sample shows some size of 25 nanometer. Here we can see the UV visual plus. Smaller particles are in the quantum confinement region. There is a blue shift in the band gap of 4.2. But the more interesting thing, what we are going to see, is the vibration spectra of the smaller particle as well as the big. Here we can see, as I have already explained, that the smaller particles show a broad, whereas the bigger particle show all the unallowed peak, that is A1G, E2G, A2U, and B2G. However, people had modeled this in different way. Or they will claim that there is a core cell kind of structure for tin oxide. The core contributes the crystalline vibrational mode, whereas the cell stand for the amorphous nature, and they're giving a broad peak. Then how about what if the smaller size particle contain a small core, but because of the lesser we are not able to see the Raman allowed mode. That is a fast challenge, and that we want to see in the plasmonic field. Like, can we enhance the underneath Raman peak by strong plasmonic material? That is the first thing. One more interesting factor we could see here, we can see the A2U mode in the for the bigger particle. Basically, this is a IR active peak. So this indicates there is a breaking of the mutual exclusion principle. Generally, that happens for the nano region. For the nano orders, there is a breaking of the symmetry, and we could see the mode. However, like similarly from the IR spectra also, you can see a EG mode, what is a Raman active mode for the 25 nanometers. So that confirm the breaking of the mutual exclusion principle for the bigger particle. So what's like the how the plasmons field going to affect this vibrational spectra? There are no much study on that. As from our knowledge is concerned, there are only 2 studies, and they were done separately, one on the bigger particle and second one is the smaller particle. They could see a enhanced IR the plasma material like silver, and they claimed that no, in the presence of plasma material, breaking of the mutual exclusion principle is happening. But shown in our material before putting the plasmonic field, the breaking of symmetry has been already happened. And in the second study, they tried peak from the smaller particle. They could predict it theoretically, like this peak correspond to the Raman peak. However, experimental experimental they stopped with a statement that they have to have a very strong plasmonic field to see this kind of behavior. So in inclusive way, what I can tell, we have to have a very strong plasmonic field to see this kind of effect. To explore, we have chosen, as introduction I have told, we have chosen 2 different metal, gold nanorods and silver nanorods, and we'll optimize like which one is the best. So first we created we have some gold nanorods. This is the slide what's representing how we have synthesized the gold nanorods. We have utilized a seed mediated growth, but it's a 2-step process. First we created some seed, and later on the seed was converted into the nanorods. And this is the search spectra of RG6. Here we can see that we could go up to 10 to the minus 12 molar detection of RG6. As I suggested in the title, we are going to talk about.
Yeah.
Sorry, sir.
2 minutes to finish.
Yeah. So silver, gold, and let like we have synthesized silver, and here we can see the nano gap. Like as I have explained in the introduction, we are interested in the nano gap to create a strong electromagnetic field, and here we could get some nano gap. And really nice because in the earlier case we could go up to 10 to 12 molar. However, to go up to 10 to minus 16 molar detection of the RG6. So we have chosen this as the final substrate, and we carried out our final experiment. Here you can see in the presence of silver nanonets, we have taken the Raman spectra of the SNO2 quantum dots, and this is without any silver nanonets, and here we cannot see any Raman allowed mode. However, in the presence of quantum dot, the Raman allowed mode is coming up. So this is one of the first time observation of the Raman allowed mode SARS. This was also cross-checked with the higher Raman spectra, because whenever we will put the higher pressure, the peak will shift, and here we can see the presence of this spectra. And the most interesting thing here, this is the bottom one here is without AG, we cannot see any IR peak. However, in the presence of, you could see a strong IR peak. And I'll just try to remind the equation what we talked in the introduction slide, the I2 by I1, that is the ratio between the Raman intensity of IR peak and Raman peak, what will enhance in the presence of a strong gradient field. So here you could strong gradient field, what in turn enhance the IR peak. So the conclusion goes like this: we have created a very efficient source substrate that could detect up to 10 to the minus 16 molar of RG6, and coming to the metal oxide, for the first time we have seen Raman allowed mode in the quantum dots using the source effect, and very importantly, IR mode enhances for the tin oxide in the presence of inhomogeneous electric field is also shown. And as a conclusive statement, I just want to tell, we have created a torch-like environment using a source substrate. Obviously, here I have given a star mark because star other benefits like spatial resolution and all, but we have created the strong inhomogeneous electric field using the soft substrate. So that is the achievement what I can tell in our work.
Okay.
And
Thank you.
I just want to acknowledge my guide Arindra and our division heads Dr. Sandeep Dhara, T.R. Ravindran for high pressure experiment, Amrita Pandian sir for TM, and my junior Resma TS for all this experiment. And this is some beautiful view from nearby places. Thank you, sir.
Thank you very much for your nice talk. There are no questions here. Are there any questions from the panel that we have here? Okay, thank you. There are no questions. Thank you very much for your talk. You can unshare now. Yeah, the next talk is by Mr. Ramesh Babu. Is he here? Mr. Ramesh Babu?
I do not see him in the list.
Yeah, I don't see him here either. So I think he is not present. Anybody who's going to present the next talk? Ramesh Babu Yathirajula's talk? There's no participant here. Okay, I think we can, Joby, then we can close the session.
Yeah, we can close the session. That's right, sir.
So I would like to thank all the speakers, Professor Dikshit, Professor Ramakrishna, Professor Rosen, and also Mr. Binay Kumar Sahu for their nice talks. And we had a successful session. Thank you very much. Over to Joby now.
Yeah. So thank you, sir. Thank you very much. And thanking everybody once again for this wonderful session. And if we had time, we could interact. As I think Professor Rosen is still here. Professor Kher Singh has left. One of the main problem with the online conferences is that we don't meet. So we can't talk other things. The only thing we could do is that once the session is over, we could linger out for some time and spend for some discussion.
So, Professor Rosen, I just wanted to ask one question. Professor Rosen, are you around?
Moment. Yeah, now I'm here. Okay.
No. So, coming back to that synthetic, that smart thing that you were talking about. So you have taken all the telescopes on the periphery only. I mean, is it by design or so that you have a maximum perception?
I mean, we can do cover full aperture, but if we can save and only move the telescopes around the perimeter, it's more efficient.
So the main advantage that you see is that you just need 2 telescopes and you can do a time averaging and time reconstruction kind of thing.
Yeah, the new method is with a single telescope that scan all the aperture.
Okay.
As a single telescopes. Yeah.
Okay. Now the new one is with single telescope. Okay.
This is our vision.
Yeah. So of course you are assuming that the object does not move in this period. I mean, this is the object remains the stationary and things like that. The things that you're So so you are looking at what kind of time scale in one scan,
It depends. I mean, for every position, we have to take 3 shots. We do phase shifting. We change the phase on the SLM 3 times, and then we move after 3 shots. We move to the next position.
Okay.
I can't estimate it how long it can take.
Yeah. Okay. Yeah. Fine. Yeah. Interesting technique. Yeah. Very nice. Thank you. Thank you very much. Yeah.
Okay. Goodbye.
Goodbye. Thank you. Thank you very much.
Thank you very much for joining. Yeah.
Bye.
Okay, Joby.
Okay. Thank you. Bye. You can close the session. Thank you very much.
Yeah. Right.
Thank you, Ananda.
With this link, I can go to other sessions.
No, you cannot go to other sessions using this link. This will be only for the photonics session.
No, but photonics session other times I can.
All are in this link. Yeah, you can attend all photonics sessions for all the 3 days using this link.
Okay. Fine. Right.
This hall has only one link. This hall has only one link.
Okay.
Yeah, sir. Pal sir is here.
All right. Oh, hi, Dada. Congratulations.
Thank you,
sir.
Yeah.
Thank you.
So
Ramakrishna, I think. Ramakrishna. Hello.
Ananda, you are not audible. We can see you. Yeah, but your voice is not coming. I don't know if it is not muted, but your voice.
This is a problem of WebEx. The other day I was in an Icee meeting. I could not, speak. I mean, my voice was not carrying. So there's some problem with WebEx, I think. Yeah.
Yeah, even Ananda, we cannot hear you, Ananda. But by good, it was good that during your talk there was no problem. But now we
No, no,
can.
Ananda, if you can hear me, I just wanted to tell you that Professor Pal has just been named Maria Yozel Educator Award by SPI for 2021.
Oh,
Yeah.
thank you.
Yeah. Okay.
Okay. Thank you, Ananda. Thank you very much. So we will have the next session starting at 1:30. Yeah. So Professor Pal is here already.
Yeah.
So Joby, so things
Yes.
are okay, no? You can hear me and everything
Yeah,
is
yeah,
fine.
everything is okay, sir. We can
Okay.
hear you very well, and your video is also good. Okay, sir.
Okay.
So you had lunch, it seems.
Sorry.
You had lunch. We still have to lunch. We have to go.
Oh, yeah, I had a quick lunch because Joby's SSA's order was that you log in 1 hour before to check everything is okay. So I ran. Okay, you go ahead. Then we can then again meet at just before
I'll
1:30.
join.
Yeah.
Yeah, 5 minutes. Yeah, 5-10 minutes before 1:30.
Okay.
Yeah.
Thank you.
Thank you, sir. Bye, sir. Hello, Pal, sir. Currently, you are muted, sir.
Yeah. Okay.
Yeah. Okay. I do not see the first speaker, Professor Matteo Chisa, in this list.
Yeah. May I wait for a minute or so for him?
Yes, sir. Let us wait first.
So I have to chair 3 invited talks and 1 contributory talk. That's it, right?
That's correct, sir. That's correct.
Okay, fine. Until 3:30, 3:15, yes. I think.
Yeah, I'm until 3:30. Yeah.
That speaker from contributory is presenter from IIT is from which department?
Yeah, from physics department.
Oh, physics. Okay.
It's my student only.
And I have got CB from Konit.
Yeah, Konit, Tobias Konit.
So I made even from there it was difficult, but now I had made it for something. I typed it and then got a printout for it.
Okay.
He got a big scholarship award yesterday.
Oh, I see. Okay.
German Colloidal Society, a prestigious award. Joby, do you know what is SNTI-S3? Is there a specific name or I don't know what it is. It is tin titanium sulfur 3. Do you know anything about it? No.
Absolutely no, sir. No.
So then I'll just quote it like that only.
I see organizer team post. Is there any message from Professor Matteo? I don't see anything.
No, we have not heard
Okay. Okay.
Say organizers can send a mail or something, email or message to him or WhatsApp, just to tell him that we are ready.
Yeah.
Joby can call Balpreet if you want.
Yeah. He's supposed to give the talk right now. Yeah, I am talking.
Who is?
Joby is talking on the phone. Yeah.
Okay.
I just talked to Balpreet. I just talked to Balpreet, so he's calling.
Okay. Oh, that's what I said. We have some connection with him. This conference is being managed by this guy only. हमारा जो conference organizer है, क्या नाम?
That dreams travel.
Dreams वाला.
But that I do not know, sir. I was
because he has sent me a WhatsApp
okay.
with my photo in the conference. So,
Oh, Then he must be. Yeah.
He must be on there.
He must.
Some snapshot. Hi, Pawan. Is he there?
Hello, Pawan. Yeah, I see your chat, but now you could unmute yourself also for some time. Hello. Hello, Pawan. I can see your text. You can switch on your.
Where can you see?
Also for some time. Till I send one message to Matthias and I send the link right now again. I don't know whether.
Did Valpreet respond anything?
No, not yet, not yet.
Okay. And Joby?
Yes, yes. Hello, Patrick. It seems he and the email which he received, some of the emails went to the junk, so he probably did not get this correct email. So Balpreet just forwarded the message to him and he's just trying to join.
So maybe the link that we are able to click on, that again resend or what? I don't know.
Yeah, it's a one link only. Everybody has one link only.
I think he's coming.
Okay. Yeah, Matthew is here.
I apologize for being late.
Thank you so much. So I understand some miscommunication. So I think we could start. You are okay, or you will be able to share your screen now?
Let me. Yeah, I'll get. Just give me 2 seconds. I'm shoveling around between presentation. Here we go. The one. Let's see if I manage to put it. And yeah, here.
Okay, I think in the meantime, I can start the proceeding. Good afternoon, everybody. And for the second session of the session on photonics and nanophotonics and plasmonics, under the conference ICE 2020, this is the fifth of this ICE conference. 2 of them were held in IIT Bombay and 2 held in IIC Bangalore. And this is the first time it is held at IIT Delhi. Of course, this is a virtual conference for the first time, and because of which number of participants are quite many. And please note that what you see here on the window are not the participants. Participants number.
I'm trying to stop video share. Switch to desktop up now.
Okay, so let me just welcome Professor Vishnu Pal, our chair for this session. And Vishnu Pal is a professor from IIT Delhi before, so he taught us and he spent almost 35 years as faculty at IIT Delhi. After his retirement, he moved to Mahindra Ecole Polytechnic or Mahindra Ecole Central University, Hyderabad now, where he is the Dean of Academics. And for a long time, while being at IIT Delhi, he has been very, very active for various research activities, and also he has been our person to look up to for any international activities, collaborations, conferences, contacts. So he has been a fellow of OSA as well as SPIE and various international and national awards. And most importantly, I'm very, very glad to announce this community about the award he just received, 2021 recipient of SPIE Maria J. Usual Dedicated Award. Thank you very much, and congratulations, sir, from all of us to you. And so with this, I welcome you all and also Professor Pal to chair the session. Thank you.
Okay, Joby, good afternoon. Thanks to everybody of the organizing committee, Anuj in particular, for giving me this opportunity to chair this particular session.
I don't see Matteo now.
Oh, I don't see. I can see you. You are on. He is again not there.
No, Pavan is telling he is not able to hear.
It's already 1:43 p.m.
Yeah. Yeah, Matteo is back here. Hi, Matteo. Good.
Yeah, I was trying to get to run my presentation from the browser, and it didn't work. So
now it's working. It's well. That's good.
Yeah. So
now it's okay.
Yeah. So Professor Pal will start the session. Professor Pal,
okay. Hello, Professor I don't know how to correctly pronounce Matthew Chisa. My name is Vishnu Pal. Actually, I am speaking from Hyderabad. So it's my great pleasure to welcome you for your invited talk, or invite you for the invited talk very soon to start. But as it is customary, just before you start speaking, I would like to briefly introduce you to the audience. So Professor Chisier's research has focused on the creation and implementation of technologies necessary to adapt the current energy system into a more sustainable, competitive, and secure one. The investigation consists in design, and investigate engineered nanomaterials for solar energy conversion and storage systems. Currently, he focuses his research on tackling specific challenges related to the deployment of renewable energy under Arctic conditions through a synthetic and symbiotic approach. Professor Chisa cultivates interdisciplinarity and combined technologies to create optimum solutions while ensuring their harmonious integration in a societal context to achieve sustainable living and well-being of people. He has systematically addressed several major challenges related to solar energy implementation in desert environment at Khalifa University of Science and Technology in Abu Dhabi. The outcome of his research has been pivotal and the realization of photovoltaics projects promising electricity at record low prices, with the power purchase agreement fees reaching as low as 1.79 cents per kilowatt hour. With this introduction, I would request Professor Matteo Chisa to deliver the talk. His title is quite long, so maybe just for the sake of brevity, I'm not repeating the title. It is there on your slide. You please go ahead. Thank you. You have 30 minutes, but actually 20 minutes I will try to give you a buzz. And by 25 minutes, you'll try to please sign off. End the talk, leaving little time for the questions from the audience. Thank you so much.
Many thanks, Professor Paul, and really apologize for being late. It's being in a different part of the world and different time frame makes the whole things extremely complicated sometimes. And you know that I'm right now in Tromsø, where the polar night kicked in. So it's not yet. It's pretty difficult to get sorted out. Anyway.
Incidentally, Matthew, I worked at NTHO, the NTU now in Trondheim for 2 years, 75, 77.
Yeah, that's good. So you know what I'm talking about. Eventually kicks in the time of the year in November where everything is dark. Likely we got the first. But so today what I wanted to share with you is something related to 2D materials. And obviously you're all experts and most probably more expert than I am in the synthesis of 2D material. But I wanted to show you my view and my way of approaching these field of research. And mainly what I've been my presentation, every time you need to just be fluffy and try to present stuff that are probably go far beyond what you would like to say. But from an academic point of view, one of the things that I've really used a lot of time for is develop the atomic force microscope as a tool to interpret and characterize material. And I think this tool really provides with a set of spectacles that are extremely important in order to better understand and utilize 2D material. And I will show you some stuff related to that. So I will start by explaining what the AFM is, not in terms of what the atomic force microscopy is as such, but how it has developed. And here there is a video that obviously grant access. So the AFM, the atomic force microscopy, was presented to the community back in 1986. Okay, and pretty much we all know there is a cantilever with a very sharp ending tip that is brought into proximity with the substrate. And it goes to the proximity of the substrate and it just goes and follow it by thereafter creating small forces that will allow to just get an understanding of it. And it was a further development of the scanning tunneling microscopy that was just limited to conducting sample, while the AFM could treat both conductive and not conductive samples. One of the issue of the first type of experiment rastered the cantilever back and forward on the surface was that for relatively soft samples, the cantilever would affect, probably dislocate the sample or even damage the sample. So people move over to something that is called the dynamic atomic force microscopy, which is an oscillating cantilever, so that the intermittent contact with the sample allows to have a much softer interaction. And hereafter, there are two different main schools that are who have been created, the frequency modulated and the amplitude modulated school. And these two school or these two philosophical approaches just regarding or just very much dependent on the way you feedback onto the system. So either you use the frequency or you use the amplitude. But bottom line, both schools were very successful in developing and finding out both dissipative and conservative process happening in the interaction between the tip and the substrate. But after a while, the acting on one single frequency became, just a limitation. So people realized that there is an exchange of energy between different frequencies while you are interacting it. So it would be very good if we were capable of exciting more than one single frequency. Now, you've seen the example on the video that one way of doing it is to hit very hard substrate. But this way of doing it has the drawback of exciting all the frequency, but on the other hand, possibly damaging the sample, which is something that is a drawback that we try to solve by using the tapping or the dynamic mode. So a different approach is by utilizing an extra frequency to drive or to modulate the dynamic of your atomic force microscope. And what happens is that by using the first mode or the first resonant frequency and the second mode, one can obtain several different observable that allows to enlarge the amount of information that one can take out. Now, the system is slightly more complicated, but thanks to several multiple locking amplifier, one can lock directly on this exciting frequency. So you see that from an approach that took a feedback on either the frequency of the amplitude, we are now converging, and the two schools are converging into what is called the multi-frequency AFM. Now, for frequency AFM, the possibility of exciting a different frequency allows you to get a lot of different contrast and a lot of different maps. Unfortunately, these maps, or fortunately, unfortunately, they contain quite a lot of quite a lot of understanding, quite a lot of information, but you need to interpret this information. And the interpretation of such information is what is important, and we will see what's going to be important in order to really better understand the effect that is on, for example, 2D material or the use of 2D material. Now, one way of doing it is by entrusting the AFM data. And what we are showing here, what I derive the force curve profile between the tip and the sample. And then I utilize directly the signature of that tip sample interaction in order to create a singular or a footprint that just is characteristic to that interaction between tip A and sample A. And this is parameterized, put into a library, and then I can always go back and refer to that as my sample A, okay? So I don't rely any longer to model or to theoretical model to interpret my data, but I use something that is more of a machine-aided approach in order to take it. So the different steps are, I derive the force distance curve. And then once I have the force distance curve, I parameterize it. And the parameterization is a different place of the well. I take the distance of the well and I normalize it at a certain distance, 80% of the force of adhesion, which is the minimum force. And this allows me to have a feature or a set of features that uniquely describe that interaction. So now I put into a database, or I create an artificial neural network model, and I put into a database, and that will go and once for all determine what's going on there. Now, how do we use it to better understand 2D material? Well, look here. Here, for example, before I deep down into 2D material, I'll start with graphite. Okay, graphite, we all know that is considered to be an hydrophobic type of material. But in reality, when we look at it, when we take a contact angle of graphite and we just cleave the graphite and we take a contact angle, we see that the contact angle is around 40 to 50 degrees. Now, after waiting 1 single hour, the contact angle reaches 89, 90 degrees and stabilize there. When I take my force profile, I see what you see in these clocks. So at time t0, I have a force profile that is a very clear van der Waals force profile. And you see that the force of adhesion, so the minimum of this force is circa 1.69 nanonewton, obviously depending on a tip radius of around 4 to 5 nanometer in diameter. When I wait out 1 hour, the force of adhesion is reduces from 1.69 to 1.28. Then I wait 3 hours, 6 hours, and you see that the force of adhesion, so the minimum of the force distance curve, stabilizes to a certain value, but the well start growing. And the well start growing, implying that something is going on into the surface. And this something is going on into the surface, we've realized, and I have other way to prove it by using Fourier transform FTIR analysis. I realized that there is a small layer of water that goes and deposit. Calling just water is probably an underestimation. It's probably water and some organic compounds, but nevertheless, this is what goes and deteriorate the surface and stabilize the surface in such a way that we get the contact angle that we usually report. Now, I've tried to use my approach, so I just normalize or put the full scale, so the signature at different time frame, and then I'm capable now with this approach to decide how long my surface has been exposed into an environment of a certain partial pressure or a certain humidity. And this is something that I've been using consistently. Now here you see a different type of system where I again recognize, I trained my system beforehand, showing that phase 1, what you see on this part of the graph, belongs to one certain material, and then the second phase belongs to another material. And I'm able to decide thereafter what material is what. So I've added to the AFM, thanks to this way of interpreting the force footprint, a way to recognize materials that was not possible before. So now we go further to the use into a material that we've studied quite deeply lately, and that's the reason why I want to show to share with you. And it's a tin titanium trisulfide. Tin titanium trisulfide is a heterostructure, is a misfit material, and practically it's used with a process for which you stoichiometrically put the different type of gases, and you manage to construct different layers of tin sulfide and titanium disulfide in a very organized manner. And you get this very nice heterostructure. And we've done quite a lot of assessment on the different property, both in terms of band gap, by reducing the size of the system, what do you have and what don't you have. And we realized that there are these superposition of both semi-metal and semiconductor property. So we've done quite a lot of characterization, quite a lot of analysis, and just realizing that this is actually very good candidate, especially at a small size with a few layer. You manage to have to go from a indirect semiconductor property to a direct semiconductor property. Now, the issue of this type of stack, the time when we put one layer over to the other layer over to the other layer, we have a way of controlling the process and at least knowing what is layer A versus what is layer B, and also forth. In this kind of process, when we exfoliate and we don't know what is at the top. Do we have at the top tin sulfide or titanium disulfide? And this is the question that we ask ourselves, because when we try to create a device, obviously, if you have a semi-metal material on top, you will have a completely different contact and therefore different properties. They are not just depending on the material itself, but the way this is used into a device. Anyway, here you see from this figure the high resolution TEM, and the high resolution TEM clearly indicate the presence of this layer structure. And on the right hand side, you see all the DFT calculation. And the DFT calculation, actually, to be very frank, we struggled a lot to describe the full system. Well, on one hand, we were thinking, well, the reason for struggling is due to the fact that it's a very complex system, okay? But, we were very good at describing just titanium disulfide and tin sulfide and being able to, in a certain way, to put the different property together. But the electronic band structure and the optical property of the heterostructure was difficult to obtain directly. So we went and did quite a lot of further characterization. So we have a very decent amount of control of what we have. And we also based and compared to the structure made of bulk tin sulfide and bulk titanium disulfide. And there are plenty of very nice property, and we can go back to these later on. That depends on the thickness of the system. But one thing that I wanted to sort of provide evidence of is that now with my AFM, I'm capable of recognizing by going and tipping on it if the layer that I have created and the final layer is titanium sulfide, titanium disulfide, or tin sulfide. And I've done that in different possible ways, but one of the ways is by looking at my DFT calculation and just looking at what is the surface energy that I have on the system. And depending on what or how high the surface is, I can just relate and compare with the force of adhesion that I'm deriving. And here you see, for example, an example of the force profile of titanium disulfide versus the force profile of tin sulfide. And then I use quite a different type of multi-modal atomic force microscopy to get a distribution of these type of interaction. And then I can univocally and extremely precisely decide what is that I'm looking at and what is the final material. Now, as I was telling you before, by using bimodal, I'm capable of actually mapping the full surface and determining what I have on top and mapping this respect directly the force of adhesion of my substrate. And by doing so, I know exactly whether the exfoliation has been very homogeneous, very smooth, or not. Now, I've used my machine learning or machine-aided approach in order to figure out whether I'm capable of doing the same thing. And I've trained my model on bulk tin sulfide and bulk titanium disulfide. And I've used that in order to derive back what I'm having. And I'm relatively successful in finding out from a bulk material what is what. But when I use the heterostructure, then I'm becoming the approach become much more confused. Let's put it like that. And
Matteo,
yeah.
Sorry, Matteo, you have just 5 minutes, please.
Yes, I'm almost done. And I'm trying to land the story on something that is probably of high. So the figure that I showed earlier was high resolution transmission electron microscopy. But as you've seen, you could see the layer structure, but you could not go very precisely and look at what you had. So what we used STEM, scanning tunneling electron microscopy, and then we got a much higher resolution system. And then we see that this structure, you have the alternating layer, but the alternating layer are not perfectly alternating. And I'll show you later on. These are the different plane view of these titanium tin titanium trisulfide, and you see that, for example, in the section B and C of each of the column, you see that there is a form of defect, of naturally occurring defect into the layer. And that seems to explain the reason why my DFT calculation was not able to provide me a one-to-one, let's say one-to-one confirmation of my experimental results. And here we usually, as 2D material interested people, we are limited in finding out that there is this periodicity, but very rarely, from what I understood, we do a very complex analysis of the sample in all the different symmetric or different planes. And this is, in my opinion, a very important step if we really want to better understand the material. And that's what can also merge and combine what are the properties that we can get from density functional theory simulation and the experiment we are getting. And I stop here. Thank you very much for your attention.
Thank you. Thank you, Matteo, for an excellent talk and giving us nuances of using atomic force microscope. The session is now open for questions for the audience.
Yeah, sir, can you please check whether any question is from the chat box, because that's where other audiences will be.
Yeah, but I don't see anything, any chat box message.
Yeah, I don't see. Okay, if that is not there, then other persons in the audience from there.
So can I close the talk now, Joby, if there's no question?
Yes, sir, we can close the session. I close the
talk. Okay, Matteo, for your excellent talk once again. Thank you very much, and wish you a warmer weather at Tromsø.
Thanks.
Thank you. Bye.
Okay, sir.
Thank you. Tusen tack. Matthias, tusen tack.
Tack ska du ha. I'm
Tack ska du ha.
trying
Ja.
to. Okay, here. Stop sharing. Good.
Good. Okay.
Should I share my screen now? I'm Pawan here.
Just a minute, Pawan.
Yeah.
So our next speaker is Dr. Pawan Kumar. Did I meet you ever? I heard a lot about good work. I don't know. I cannot recall.
We probably have met in the passing once or twice, sir. But
Okay. Good to see you. Dr. Pawan Kumar, it's my pleasure to welcome Pawan Kumar for an invited talk at this seminar, at this conference. So Pawan is an associate professor at Icee, Pune. He earned his PhD in physics from JNCSR, Bangalore. Subsequently, he was a postdoc at ICFO Institute, his famous institute in Spain, Barcelona, on photonic sciences, and he also worked as a postdoc at Discovery Park of Purdue University. Since 2010, his research at Icee Pune have been his research group at Icee Pune have been working on optical physics and applications of plasmonic nanostructures and soft matter systems. Specifically, their research question pertain to control of propagation and scattering, localization of light and heat at sub-wavelength scale, and its interaction with soft matter, including colloids and complex fluids. Apart from about or over 70 journal publications, his work done in India has been featured in various media outlets. He has been a recipient of Sonojayanti Fellowship in Physical Science of DST, which is a very prestigious and competitive fellowship for 5 years, INSA Medal for Young Scientists, Nasi Scopus Young Scientist Award, Malhotra Whitefield Foundation Award in Nanoscience, and he is a senior member of Optical Society of America. With this, I would request now Pawan to start his talk. Yeah, you please present, Pawan. You please present and share your slides. So I'm going meet now.
Yeah, sure. So can you see my slides now? Are you able to?
No. I can see you sitting in your office.
Yeah. Okay.
The sharing has not started
He had to do the share. There is an arrow indicating share, no? At the bottom of his screen.
Yeah.
If it does not happen, maybe press that again and come back.
Yeah, it has come. It has come,
right?
Yeah. It has come. Thank you.
Okay,
so I'm going mute.
Yeah. Sure. So first of all, let me thank the organizers, including Professor Joby and Joseph, and also Anuj for kind invitation and also organization. And I also thank Professor Paul for a very nice introduction. In fact, IIT Delhi is a place we all look up to in terms of optics research, and without any doubt, it has inspired a lot of people like me to do good work and also learn a lot of good things. So thank you very much again for the organizers and also Professor Paul for the introduction. So today what I'm going to talk about is something related to hybrid nanophotonics in the context of trapping micron scale and sub-micron scale, and in certain context also the nanoparticles in a fluid. And I'll also briefly touch upon some interesting questions related to how hybrid nanophotonics can be used for directional emission, especially in the context of on-chip photonic applications. So to begin with, all of us are aware of an important area of research relevant to nanophotonics, which is a surface plasmon polaritons. It belongs to a broad kind of a family of waves. It's called as surface electromagnetic waves. And its definition in a kind of a very crude sense can be considered as a coupled oscillation of light and electron charge density waves at a metal fluid or a metal dielectric interface. So you can see in this particular diagram what I am showing. There is a metal and there is now a dielectric medium over the metal. And if you shine an electromagnetic wave and you somehow match the momentum of this particular wave to the surface wave, which is now propagating along the length of this interface, then you end up getting electric field which is tightly confined to the metal dielectric interface. And this electric field decays exponentially. And all of you would be aware of the fact that this is also called as an evanescent wave because it actually decays in an evanescent way, exponentially decaying function. And there's also some component of the electric field which can penetrate into the metal, and this is called as a skin depth, as you probably would be aware of. Now, this particular concept of using external electromagnetic radiation and converting that into a interface oscillation of electric field is one of the important tasks of this surface plasmon polariton optics, where the polariton essentially means that now the light which is incoming as free photons is now converted into some kind of a coupled oscillation of electrons and electromagnetic waves. And that's the reason why it's called as polariton. And if it happens to be coming from electronic charge density oscillation, it's called a surface plasmon polariton. So with this introduction of what surface plasmon polaritons are, one of the interesting questions to ask is, if you actually have this dielectric medium, and this medium happens to be, let's say, a fluid, what are the interesting prospects one actually can create in such a fluid? So one of the important concepts which evolves due to this kind of light matter interaction, especially light metal interaction, is something called as confined electromagnetic fields, or in other terms, it's also called as a hotspot. So if you consider this dotted circle as a sphere, and if you bring another sphere of, let's say, a diameter 100 nanometers, and you bring them so close to each other that they are now separated by a distance which is smaller than the wavelength of light, then you shine electromagnetic radiation on this kind of a junction, you create enormous electric field at this particular junction. And this junction is essentially called as a hotspot. And one of the questions which is of very high interest in the community is to understand how does light, how do molecules interact with such kind of an hotspot? What are the new prospects which actually can bring in such kind of hotspots? Associated with this localized electromagnetic field is two kinds of cross sections. One is the scattering cross section. The other one is so-called the absorption cross section. And these cross sections play a very critical role in understanding how efficiently the light can couple to these materials and scatter or absorb in the particular material. And the power related to this will govern how much of light is converted into heat or how much of light actually is scattered off as outgoing photons. Now, in my own group, we are interested in understanding the interaction between surface electromagnetic waves with soft matter. So the surface electromagnetic waves can, in this particular case, is surface plasmon polariton. And the soft matter, what I'm going to talk mainly would be colloids made of metallic or dielectric in composition. But you can also ask questions such as, what is the nature of colloidal dynamics in the presence of surface plasmon polariton? What is the effect of reducing the dimension? For example, if you have these surface electromagnetic waves in 2 dimensions, and you reduce the dimension to 1 dimension, or into a single dimension, what is the change in the dynamics you will see? And this is partly motivated from questions which are related to soft matter physics problems like swarming of colloidal matter, kind of optical matter, dynamic network formation, and also something which is very interesting, which is called as optically bound matter. And all these interactions happen in a fluid phase. So I'll try to actually take this motivation further and address these questions in specific situations. So one of the important aspects of this kind of interaction, what we have studied is something called as optothermal trapping. The idea is the following. You now actually have a metal film, roughly about 50 nanometers in thickness. This is a gold film, and it is now optically coupled to, let's say, a prism. And now you incident a an optical beam, one second, I think, yeah, there is an optical beam. This undergoes a total internal reflection at the interface. And interestingly, this particular region where this interaction is happening has a fluid which is on top of it. And this particular fluid contains, let's say, metal nanoparticles, in this case, gold nanoparticles, or kind of a bimetallic nanoparticles. This fluid is now set into motion because of an optothermal field, which is not only part of the excitation of the electromagnetic radiation, but also a local heating of the metal in such a situation. This creates a gradient of gradient of the temperature along this particular z-axis, and creates this kind of a convective field in the fluid. And the nanoparticles now are set into motion, and as a function of time, they start actually assembling, or rather trapping, or getting trapped in this particular region. Now, this is purely an evanescent wave configuration. So the amount of power you are utilizing is minimal. So also the interaction is mainly at the interface. So it is mainly at the interface of metal and the fluid. And the nanoparticles actually get assembled in this kind of a optothermal potential. So let me show you the one of the kind of a videos in which we can trap this kind of nanoparticles. What you are going to see is silver nanoparticles which have been trapped on a silver film. In this video, what you're going to see is not an individual nanoparticle, but an aggregate of nanoparticles which already have assembled, and those aggregates actually further form a larger assembly. So as you will see, what you're observing is the evanescent waves which are at the interface creates an optothermal potential, and you see a swarm of nanoparticles which assemble in this particular geometry. And this creates a very interesting situation because now you can utilize this technique further to play around in terms of its in terms of its position as a function of time and space. So you can move this swarm of nanoparticles from one location to another location, all optically. So you are not creating any microfluidic channel. This is an unstructured metal surface, but you're able to transport the particle in the desired fashion by purely manipulating the optical beam, which is creating this optothermal potential. What is further interesting is you actually can switch on and off this optical field, and you can reconfigurably assemble and disassemble the particles of your interest. And this is all happening at a metallic with a metallic nanoparticle assembly in this particular case. Now, what is interesting is the electromagnetic fields which are part of this kind of an assembly. So due to the optothermal fields, you end up getting very interesting hotspots, which I was talking about. You create a hotspot between the metal film and the particle, and you also create a hotspot between the particles. And also you create into the third dimension a kind of a field where there is a film, there is a particle, and also there is particle on top of it. All these situations leads to very kind of an extensive amount of hotspot kind of scenario in such kind of interaction. Now the question is, can you harness these hotspots? Can you utilize this enormous electromagnetic fields which you have in such a kind of situation? And the answer is yes. Now, without going into details, what we have, what I'm going to show you is the final data of something called a single molecule Raman scattering from this kind of dynamic assembly of nanoparticles. So the idea is that you introduce molecules, in this particular case, Nile blue and rhodamin 6G, which are two resonant molecules. And you collect the Raman scattering signature from this assembly of nanoparticles, what you have already created. And you study the fluctuation of the spectral signatures as a function of time. by studying the statistics of this particular fluctuation, you can end up getting a very interesting extreme statistics distribution, which is also called as truncated Pareto distribution, which ascertains the fact that you have been able to detect single molecule spectroscopic signature of either the Nile blue or the rhodomin 6G or a mixed event. But what you can see is that in this particular case, the single molecule signatures are more dominant than the mixed event. And this is all done at a very specific concentration and with a very careful judicial utilization of concentration of nanoparticles and the molecules. So the bottom line is that you would be able to detect single molecule signatures in such kind of dynamic assembly is the main message in this particular slide. Furthermore, you can now not only have single assembly of such kind of metal nanoparticles or optothermal assembly of metal nanoparticles, you actually can now introduce multiple excitations. Now, one of the interesting features of such kind of multiple excitation is the emergence principle. Now, you will expect that the particles do get assembled at the region of interest where the excitation potential is. But what we observe is, in addition to the assembly at the excitation location, you also observe assemblies which form along the length of this particular excitation. In fact, you see that a kind of a remote bridge forming between the excitation potentials. Now, this is the experimental data. What you are now observing is the two elliptical excitation beams, because if you take a Gaussian beam and you take a cross section of the Gaussian beam, it is essentially an ellipse, and that ellipse is what has been projected onto the metal fluid interface. And now, instead of having one excitation, you now have two excitations. Now, let's see what happens if nanoparticles come into this kind of a scenario. You will slowly start seeing the nanoparticles kind of optothermally trapped at the two locations. But in addition to these two excitation regimes, you end up actually getting something like this. So this is a static images, optical images which have been captured. The most interesting feature of this kind of assembly is that you not only find nanoparticles being trapped at the excitation location, but you see a long bridge-like structure between the nanoparticles. This is actually something very interesting because this is spanning over a distance of few hundreds of microns. So conventional optical trapping cannot perform such kind of experiments where you can bridge two traps with a bridge which is as long as almost 1 millimeter. For example, in this particular situation, this is at least 400 to 500 microns in distance. Similarly, you can actually change the configuration, and you will observe that the optothermal potential, what we have created here, creates an assembly of particles here and this particular location. But you also find a very beautiful kind of formation between these two potentials. Furthermore, we can ask, can you actually go ahead and perform this experiment with more number of excitation beams? And the answer is yes. And you'll start seeing some very interesting situations. So here, what I'm showing is three optothermal potentials, in this particular case, created by the green laser, a 532 nanometer frequency doubled Nd:Ag laser. And what you are actually seeing is this excitation potential. In this video, you will see that what happens if you have a gold film and a silver nanoparticle. You will observe something called as dynamic assembly of nanoparticles at this interface. Now, let's see how does this look like. Now, of course, the excitation beam is filtered out. So what you're seeing now is a triangle, and at the vertex of the triangle, you create an optothermal potential. So the nanoparticles start assembling at these potentials. But in addition to these locations of optothermal potentials, you will also see that exactly at the orthocenter of this isosceles triangle, you see an assembly which is formed. This was very surprising because there is no optical excitation here, but there is some kind of an optothermal perturbation which is creating such kind of assemblies in nature. So we further went ahead and did little kind of a detailed analysis of such kind of assembly using cluster tracking and also particle imaging velocimetry. So what you will observe is that the stability of the optothermal potential is very good in this excitation 1, 2, and 3. Whereas at the at the ortho center of this triangle, this is slightly more dynamic kind of an assembly. So there is some kind of a potential which is also formed without the optical excitation being.
And also
This is
for the internet.
this is one of the very interesting prospects what we have come across, and you actually can now extrapolate this concept further to optothermal assemblies around mesostructures. For example, one of the important aspect is that if you have, let's say, this kind of plasmons, there is also a component of heat which creates a very interesting thermal potential. Now, if you consider the electromagnetic field, most of the interaction, at least in non-magnetic materials, is driven by the electric field. So the intensity couples to this heat power density given by this particular equation, where the imaginary part of the dielectric constant of the metal plays a critical role, and omega happens to be the plasma frequencies. So the total power absorbed in such a situation is essentially given by the volume integral of this particular quantity, the heat power density. And the cross section essentially is nothing but the ratio of the total power absorbed to the intensity. Now, this is the major reason why you create this optothermal potential. And the question is, can you utilize this optothermal potential in a slightly more confined way? What we have shown is that you can do that. Here is an example where we take a single crystalline structure. In this particular case, a gold film. And this gold film is excited using excitation beam in an evanescent configuration. And this creates an optothermal potential. And we study the colloidal assembly of the assembly around this kind of gold plate in a fluid which is placed, and the optical configuration is just given by this. What you see here is now a single crystalline gold plate, and these are actually dielectric colloids made of silicon dioxide, roughly around 2.5 to 3 microns in diameter. And what you see is a very interesting crystallization of these dielectric colloids. So you are illuminating this particular colloid through evanescent wave, but what you are now forming is a very, very interesting kind of crystalline colloidal structure. And we study the characteristics of such crystalline colloidal structure, and we extract some very interesting information about the crystal structure. Yes?
Pawan, sorry. You have just about 4 to 5 minutes, please.
Yeah, I'm almost done.
Thank you. Thank you.
So the nature of assembly Voronoi analysis tells you that the coordination number and also the how good is the hexagonal packing in such kind of geometry. In the next 2 to 3 minutes, I'm going to briefly talk about directional emission in using hybrid photonic structures. We have been studying plasmonic nanowire assisted hybrid nanostructures for quite a long time now. We have been looking at these kind of nanowire nanoparticle junctions and also whispering gallery mode structures with the nanowire junctions. And recently we have shown that if you actually create some kind of a structure where you have now a dielectric microsphere, which is whispering gallery mode resonator, can now be coupled to a single silver nanowire, which can facilitate the propagating plasmons. And this is all done through a self-assembled processes, which creates a photonic plasmonic hybrid. Photonic is because of this sphere, and plasmonic is because of the wire. And what is interesting is that you get a very sharp resonance of the whispering gallery modes, which can be utilized for various different studies, including biosensing and other kind of situations also. And you can also utilize it as a directional emitter, which means that by tuning the thickness of the wire, you would be able to direct the light which is fluorescently emitted by the sphere in a very particular direction. So for example, if you take, let's say, a thin wire, the momentum space distribution tells you that it's more isotropic in nature. But as you go to thicker and thicker wire, your light which is emitted from the sphere becomes more directional in nature. So you can actually tune the directionality of the emission, which is very interesting application for optical antennas and other situations. So finally, I'm going to just tell you something which we are still under processing in our lab, where we are working towards a reconfigurable optoplasmonic architectures. So what you'll see in this video is an optically trapped sphere, which can now be rationally moved at any location on a nanowire. So for example, you can see now slowly we are moving the bead along the length of the wire. So you actually can place the resonator at a location which is of your interest. And this is a whispering gallery mode resonator. And this resonator actually can be brought back to any location, and you can now move around and place it at a location of your interest. So you actually can control how this plasmonic structure interacts with the dielectric microsphere structure. So with this, I will conclude the talk. What I've spoken today is about the dynamic assembly of colloids using surface electromagnetic waves. Essentially, is the optothermal trapping, which is of very high interest in soft matter assembly and dynamics. I've also very briefly touched upon directional emission in hybrid photonic structures. Importantly, let me acknowledge a lot of people, especially my current PhD students and MS students and my former postdocs in my lab, and also former PhD students and a lot of master students. Funding comes mainly from Indian kind of resources, especially Department of Science and Technology, and also some international sources like CEFIPRA and US Air Force, and of course Swarna Jayanti from DST. Most importantly, I thank you all for showing up for my talk in this time of pandemic, and I also thank the organizers for this wonderful organization of the event. And thank you very much. I'll be happy to take questions. Thank you.
Thank you, Pawan. Excellent talk. Excellent
Thank
talk.
you.
Excellent talk, and gave a flavor of more things to come from your lab. That's also an excellent news for us. We all look forward for that. So can you take up some question if there is any?
Yeah.
Now?
Sure.
Yeah. In the chat
Sir,
box.
in the chat box, there's a question from Tobias.
Yeah. Which intensities are typically used for optothermal trapping? Can the arrangement also be created by a pattern? Very, very interesting questions. In fact, I have not really discussed anything about using holographic optical tweezers. In fact, that is something which we do in my lab here. So the intensities, the typical intensities, what we utilize is as low as about a milliwatt, about 1 to 2 milliwatt. This is actually the beauty about this whole technique. You don't need to really have a huge power, but this is not a purely optical technique, but it actually has a thermal component to this. So therefore, you will have to utilize some kind of a substrate which can transfer heat into the fluid medium. That is one of the prerequisites. The second question, can the arrangement also be created by a pattern? Yes. For example, you can have two things. One is, of course, you can use holographic optical tweezer. And the other thing is you actually can also utilize DMDs, like digital micromirror displays, which can also create this kind of optical potentials. So there are very interesting scenarios in such kind of interactions. And what I have also not spoken about is I just spoke about large scale assemblies. In my lab, in fact, there is also some recent studies from my lab where we have also been able to assemble few nanoparticles. It can be like a countable number of nanoparticles and create some kind of a metamaterial and other things, but that is still a work in progress. But the potential is quite a lot, because this is all happening in a fluid. So we envisage something which is slightly kind of more small in scale, and also of high interest in, let's say, nanoscale optics and nanofluidics. So there is another question: are controlling the trapping through optical forces? Dr. Umesh asks this. Yeah, actually, it's a very interesting question. I did not go into the detail of the mechanism. It is not a purely an optical trap, but this is actually an optothermal trap. So if you look at the force fields, the force field is of course generated by the Maxwell stress tensor because of the optical potential, but that potential is actually quite weak. What you also have superimposed on top of this optical force field is also a thermal force fields, and these thermal force fields have multiple contributions. One is, of course, thermophoresis. where the particle actually assembles into the region of interest because of the Sorek coefficient. And this coefficient can be either positive or negative. And depending upon the convention, you actually can either have the particle come into the thermal potential or repel from the thermal potential. This very much depends on the local chemistry of that particular structure. And in fact, so much this technique is so kind of powerful that you actually can potentially have the even molecules, single molecules, actually kind of getting into such kind of some kind of a interesting scenario. That's something is something which is quite interesting. So the optical potentials what you create actually has contributions from multiple prospects, including the thermophoresis, and also there is a fluid convection which plays a very critical role. So this is a very kind of interesting situation where there is thermodynamics, where of course there is optics, quite a lot of optics, and also quite a lot of chemistry which you have to understand in order to create such kind of a assembly process, which makes things more interesting for us.
Yeah, it's a very versatile platform that you introduced. Thank you so much, Pavan, for your excellent talk once again. And I wish you all the very best to rise and rise. Okay.
Thank you very much. Thank you very much. Thanks a lot.
Thank you. So we'll now move on to the next talk, which is taking place from Germany. This is an invited talk to be given by Tobias A.F. Koenig, which I happen to be working in Germany for a year once. So I would say, Herr Dr. Tobias A.F. Koenig, and I have the pleasure to introduce very briefly to you Tobias. Tobias is a Freigeist Fellow at Technische Universität Dresden, young investigator and junior group leader at Leibniz Institute for Polymerforschung. Forschung means research in Dresden, Germany. He did postdoctoral research at the University of Beirut, Germany, and also at Georgia Institute of Technology in USA. He has just been awarded. It is very fresh. He got an award, very prestigious award in Germany yesterday, which is called Richard Sigmondi Scholarship. Is given by the German Colloid Society. Congratulations, Tobias. His group's research is dedicated to electromagnetic modeling, fabrication, and characterization of novel functional materials based on unique combination of plasmonic and quantum emitter materials, controlling optical properties of mesostructured assemblies using self-assembly methods in combination with tailored plasmonic building blocks. Okay, the floor is all for you, Tobias, now. Thank you for joining. Once again, congratulations for the latest honor that you received, and good luck.
Thank you very much.
Congratulations, Toby. Toby here. Congratulations, Toby.
Thank you, Professor Joseph. And thank you very much for this kind introduction.
You will have 20 minutes, and I will give a buzz at that time, and then another 5 minutes you can continue. Thank you.
Okay. Do you now see my shared screen?
Yeah. Little bit. Yeah, I think so. It is fine, I think.
Okay. So what will come next, I will guide you through this title, Functional Optical Surface by Colloidal Self-Assembly, stepwise. So why we use colloids? Like on microscopic scale, gold is yellow. When you make it much smaller, gold becomes reddish to this beautiful color. This was also very much or strong connected with the developing of methods like the ultramicroscope, which is today known as dark field microscope. And with this, we can also describe the color because it is the absorption of the complementary color. And with today's methods, we can synthesize such nanoparticles with narrow size and high form stability very much. And this synthesis is even so simple that you can do it on a simple desk which we have done on the so-called Lange Nacht der Wissenschaft in Dresden. They just use chloruric acid and sodium citrate, heat it up, and come to the beautiful color. Furthermore, we're using this also for a plasmonic learning platform, which we're currently pushing forward. And this is actually pushed forward by my student, or former student, Antonia Meyer, which is now studying nanotechnology close to Dresden in Germany. So, where does the color come from? This is due to the oscillation of the free electrons of the metals by time. And you need specific requirements like metal, the electric interface, and the particle must be much smaller as wavelengths of light. I guess you people already know this very much. I also want to highlight that we have simulation techniques in our group, which we can simulate this oscillation of the free electrons versus time, and you see very well here the time scale is in femtoseconds. So what is the benefit now of the assembly? You saw that already in the previous talks. Like plasmons you can use for coloring or sensor, and you can generate hotspots, which we actually saw in the previous talk. You can use this also for enhanced charge transport. Further on, when you're adding more particles to the systems, you come up with particles in a chain. And finally, you can use also lattice systems, when you're including diffraction modes. You can come up with so-called surface lattice resonance, which can show lasing or strong coupling effects. Next, let me focus on the plasmonic coloring effect. Here, let me come back to the introduction slide from 1906 from Zsigmondy, and you see here very well the colloidal solution. You see here also that in transmission you can describe very well the color effect of the red color, and by placing the observer like perpendicular of it, you can derive the color green. We can calculate this very well with simulation methods like meteory. With small particles you come up green, and large particles it becomes yellow, specifically at the absorption. What you observe in transmission is basically the complementary color, and you see that basically here we can say Faraday used in this time synthesis particles between 5 and let me say 20 nanometer particles. You also see like the color change significantly when you approach larger wavelengths. And here I also want to highlight, when you compare these colors with the synthesis colors in our lab, you see very well that you have a color change, especially for large particles. And you can describe it by adding the scattering properties to the system. So the properties are already described very well. It's theory, increasing the particle, it shifts to lower energies. You can fabricate such particles on a macroscopic length scale, just on a simple microscope slide, standard slide, by using isolated particles by polymer shell and carefully withdrawing them from the growing solution, and we come up to this kind of slide. Other benefits, as we have seen, comes with coupling effects. For instance, you can just take a simple particles like here, putting on a substrate, you will induce so-called field enhancement, and you also introduce some symmetry breaking. And this symmetry breaking can be very simply understand. You have so-called bonding mode with field enhancement at the substrate, which is interesting for sensitive to substrates. And you also have the operating anti-bonding mode sensitive to the environment. This thing can be fabricated with the so-called Langmuir blotjet method on macroscopic scale, as you can see here on the photograph. And further on, you can use it also for functional properties by placing it in an electrochromic polymer solution, which is a water-based solution, and applying a voltage. You can introduce oxidation or reduction. which makes you able to tune the plasmonic resonance over a specific wavelength range. Okay, what's next? We're coming to the polymer chains, adding many particles to the system. We're proving you that we can fabricate these even on macroscopic scale. I placed here a photograph on the image on the centimeter scale. With so-called electron loss spectroscopy, we can determine the specific losses at various wavelengths. And you already see a specific pattern in this kind of excitation. And this pattern can be very well described with a particle in the box model, which is known from quantum mechanics. And you see here very well the lower wavelengths and the higher wavelengths modes. And now I'd like to turn your attention especially to the symmetric modes, which we have a few years described in more details, and use these modes, which show less losses, for propagation of energy with a specific kind of damping. And this also can be used for photocatalysis effects. So what else can these structures can be used? Let me come up with an inspiration from nature. And here's a camouflage from an octopus, record from Roger Hanlon labs. And I want to highlight here that the color pigment is mechanically tuned by a muscle. And our challenge is we like to implement this adaptation with colloidal self-assembly. So we're doing this by putting this assembly on a stretching device. And you see already by highlighting this with an arrow, you see the diffraction color. And by applying strength to the system, we have a significant color change. And this color change we show not on a single pixel, we show on macroscopic scale. And what is actually the effect behind it? We call it the functional colloidal lattice. Is actually the interaction of the diffraction mode with your surface plasmon resonance, resulting in a much sharper resonance, which is highlighted here at the first and second diffraction order. And you already can see just by judging from the peak, it has a much higher quality in comparison to a broad plasmonic resonance. Here, some field calculation from us to highlighting the coherent interaction between the particles over a large scale. And further on, because we can stretch these particles, we're stretching in one direction and have a smaller size perpendicular to it, we basically get two modes out of it, one in the X direction and the second in the Y direction. So we can tune these over a broad wavelength range. You can use it, for instance, for a strain sensor, or you can see it before, as you have seen it before, for coloring. So I talked already a lot about the assembly. Let me go next. How does assembly actually works? And here we're using laser interference to produce pillars on silicon substrate, make replicas out of it, like making like molds. And then you can see already how the story goes on. We're placing these particles inside these wells, potential wells, and ending up after index matching layer with our photonic structures. This method is called template-assisted self-assembly for large area, and it's very cost efficiently. And to prove you next how cost efficient it is, I'd like to prove you with a scanning electron microscopy image, and you see basically a lot of dots. And these are all single particles assemblies. Let me also add some scaling bar to this. And this are actually results from my student, and he done it like a few years ago, and with a assembly rate of 80%. And this work was done by Vaibhav Gupta. He's a former student from the Professor Joseph lab, which just recently graduated in November, in end of October, I have to say. And in his PhD, he used this templates. You also see here guiding blade and a guiding meniscus. And he used this in a 3-step process from bulk accumulation to drying state to assembling these particles on macroscopic scale. On this image, you see also an objective, so we can view actually our assembly during the assembly. And this looks like follows. You see here, first of all, the concave meniscus, highlighted by the dashed line. On the lower part, the liquid state, and the upper part, the dried state, and then the particle chain assembly. And this assembly are characterized with scanning electron microscopy, which is shown here. So what can be done with these structures? This is actually done by another student of the Joseph lab, Sagato Sakar, who is now working in my lab as a postdoc. And we currently pushing this, or we have proven in this cooperative work in 2019 that we fabricated these on a titanium oxide layer as a waveguide. We have a 1D colloidal photonic crystal slab. And here's some simulation of us that we can guide actually the energy at the region of interest in the titanium dioxide layer. And this is done for this so-called hybrid plasmonic resonance modes show very low losses. Even so low losses that we can use it also for energy transport. And this energy transport I did not include in this talk. If you're interested, please ask me after the talk. So with this colloidal assembly approach, I showed you that we can assemble isolated particles, so-called, or colloidal molecules, adding 2 particles, even more, coming up to a colloidal polymer, and even up to lattices. So what's next? Like similar like in the previous talk,
पता नहीं इसमें कुछ और ही चल रहा है ICC host विष्णुपाल अनुराग शर्मा
we adding
ये कहीं और टॉक चल रही है
gain materials to the system, and these gain materials are quantum images, and this is done by another student of me, Fabian Goslar. And you remember from the earlier slides?
Miss Neha, please unmute yourself, please.
And this colloidal gain is done by a colloidal to film coupled cavity. You remember from the slides before, the film coupled mode. And you can see already how the story goes on. In this kind of cavities, we adding silver indium sulfide quantum dots. And what does it mean to the system is that we have the very fine resonance highlighted here red with the photoluminescence from the quantum images. And this resulting in a so-called plasmon exciton coupling, also sometimes noticed or related to a Fanny resonance, ending up with a peak splitting. And this peak splitting can be quantified because we have many of these statistically with a specific coupling strength by judging from the distance and by quantizing or fitting the actually peak, we can quantify the loss rate. By these 2 factors, we can determine that we are working in the so-called intermediate coupling regime. And this coupling regimes, or these building blocks, can be used for media material building blocks. So, with the colloidal approach, we can actually create any pattern suits current projects. I specifically choose this pattern. I'll show you in a minute why. We have currently a DFT project where we are studying the coherent energy transference lattice. And as mentioned in the introduction here, we have a big fellowship in our group, the Freigeist Fellowship, where we are currently interested in studying this specifically for optical diode effects. And this optical diode effects, it's hard to describe, but let me describe it with a funny movie, where it actually happens on macroscopic scale. So our challenge is now to make these on a nanometer scale, this two-way mirror. What actually can be fabricated two-way mirror on nanometer scale. So we have to break the symmetry. I take this very briefly. The idea comes from quantum mechanics, and what we actually need is the alternation of gain and loss. And with this, when a photon approaches from one hand side, it will propagate, and when it approaches from the other side, it will be blocked. And this theory is actually not from us. It's already known for some time, and it was fabricated with top-down fabrication methods and have already been proved. Our challenge is to make these with colloidal assembly. And how are we doing this? I come to another student which also recently graduated. It's Max Schnepp. So I proved you already that we can fabricate colloidal assemblies on macroscopic scale. We can do this with metallic materials. We can do this also with quantum materials like quantum dots, just taking the same PDMS stamps I have introduced before, taking the nanoparticle dispersion, pressing the stamp on top, and actually just wait for a couple of hours, and resulting of a grating effect on the macroscopic scale. So you have the two materials. What we do next, we take both of them and put them together. We can describe this on a nanometer scale. We have the two patterns in a specific angle arranged. The metallic bar and the quantum emitters, they are orange, highlight the same velocity, aligned in 50 degrees. And then we're putting these in the fluorescence microscope. And in the crossing points, you actually have a quenching and enhancement and the non-crossing points. So let me go further in detail in the Mouret pattern, which is actually described in the Mouret pattern. And let me also go one step further, because we actually can detach and attach it again at different angle. And as a result, we can study these pattern formation at different angles. And this was further done from Olga Avdineva with the confocal fluorescence microscope. And with this, we can very fabricate a different angle, multi-angles of the Mouret, or different pattern formation due to the Mouret effect. And this is interesting for preventing counterfeit or as shear optical sensor. And this shear optical sensor we also studied in this publication, which is actually recently accepted. And we used for this, as shown here, the same fluorescence microscope, and added to the microscope detection area to distinguish between the left and right polarized light. And we did this with a quarter wave plate and a linear polarizer placed in front of the spectrometer. The results are very astonishing. Let me say first, we have here as reference only the emitter part, which actually shows no CD effect. As next, we're adding metal to the system, which is the blue line. See already a significant effect. And finally, we also used emitter and emitter grating, which are basically two dielectric materials, and have observed a very strong effect. And due to they are only dielectric, or mostly dielectric, we have basically a loss-free chiral material without using a chiral structure. So, and you already can see how this goes on. We are currently working on it to use these kind of patterns formation to prove the parity time symmetry effect. So with this, I'd like to sum up our work. I showed you very much about electromagnetic simulation in our group. I also showed you strong expertise in the colloidal self-assembly on a macroscopic scale. And finally, I showed you much about our optical spectroscopy and surface characterization methods. So this research is very interesting for application, especially the localized field enhancement, which can be now extended to large scale for plasmonic sensor, gas sensor, and even for plasmonic heating. We can fabricate these structures like single plasmonics or fluorescence emitters. We can use them for chiral effects, which actually makes the system to a functional electronic devices for plasmonic enhanced photocatalysis or photovoltaics and energy storage. And finally, the optics can be used for optical and spectroscopic analyzers, like for biophotonics or for 3D photonic crystal printing. With this, I'd like to thank my group, which is actually a photo made before the corona pandemic. And you see here already 3 guys graduated. I'd like to highlight here Vaibhav Gupta and the other 3 guys. And currently I have new students, or like the second generation of my group, which I also want to highlight here, Sagato Sakar and other master students, as well as student assistants. Finally, I'd like to acknowledge cooperation partners in Dresden and beyond. And finally, I also like to acknowledge funding agencies. And finally, I'd like to acknowledge you for your kind attention.
Oh, okay. Thank you so much, Tobias, for an excellent talk and giving us a glimpse of the facilities and expertise that you have in your group. It was really very nice to know. And I think there could be some questions. Would you like to take up the questions?
Yes,
Herr Koning, yeah, okay. So that is
one question from Pavan Kumar.
Yeah. So you can see that.
Very interesting talk. Thank you very much. Can the template assembly be formed on metal substrates or on curved dielectric surfaces? The answer is yes. And actually, we can also get reconnected. We actually just find out we met before on the Faraday discussion 2016 in Glasgow. And currently, as I have shown in my talk, wait a second, I will just go to the slides to highlight the question from him, like here. So this confined assembly I have highlighted here with the dispersion with the quantum dots, but currently we're doing this also with particles, and best working is just we're bringing particles in lines. And yeah, we are not far away to put these also on metal structures. And it would be also happy to get in contact with Professor Kumar, and we can send you on short notice also a sample, which you can further investigate for the photothermal effects. And
is there any more question?
To the second part of his question on curved structures, this is actually not simple.
Yeah. Okay.
Let me say, like, indirectly we're doing this on curved structures by stacking 2 grids, as I have proven you on this slide. So we can attach and detach. So we have not done yet to detach and leave the pattern there. So this is still ongoing research. But I'm pretty sure that we can solve all this challenge in the near future.
That's good. Any more question? We do have a couple of minutes. Okay. If not, Let me thank Herr Koenig for an excellent talk once again and for sparing his time to deliver this talk. I know he has something more to do very soon for more seminars and things like for his professional work. Thank you so much, and auf Wiedersehen.
Thank you very much. Hope to see you soon in person.
Thank you.
Thank you.
Thank you very much for your.
Yeah.
Thank you, guys.
So we now have a oral presentation to be made by Dr. Sherina Joseph from IIT Delhi itself. I understand she is in the physics department. So the title of her presentations is Grating Coupled Surface Plasmon Sensor with Large Penetration Length. Are you ready, Sherina? Dr. Joseph, are you ready? Dr. Sherina Joseph.
We cannot hear.
Huh? She's not here?
Yeah, she's there. She's logged in there. But we cannot have. We are unable to hear any sound.
I can see her name here appearing on the screen. Dr. Serena, sorry. Yeah. Jabil, can you send her a message?
Yes.
Yeah, so we'll wait.
Looks like she's trying, but.
Yeah, I don't know. Yeah, looks like, yes.
She's actually one of the volunteer for this session, so she should be knowing everything to do.
Otherwise, what she can do, she just signs out and then sign in again.
Yeah.
That sometimes works.
Yeah, I think she. Yeah, Sherina, should you please sign out and come back again with the same link?
The transition for the student becomes very easy because they don't have to learn entirely new application. Only the login process changes a bit. Topics are classical physics. In multiple choice questions, I need to select whatever answer I feel.
Swagato is there. Swagato, by chance, will you be able to share?
And sir, I don't have the PPT file with me of Sharina.
I think she has logged in again. Can you try to share the screen?
Yeah, it's coming. I think she is online. Fine. Sharina, can you hear me? Oh, okay.
Joby, where is she right now?
Must be in NRF only. She's a volunteer. All the volunteers are supposed to be in NRF.
Supposed to be here in IIT.
In IIT.
Then why is she having a problem?
No idea, because she should be knowing everything. She has been coordinating even the trial run, everything.
For a split moment, it showed the screen sharing, but then it vanished again.
Correct.
So, Joby, in the meantime, what is this poster session? How do you do that?
In the poster session, the posters have been sent by the students, and that are being sent to the all the PDFs are available. Now, during the session of the poster, the students are requested to be available. If the examiner wants, they will speak for 2 minutes.
Oh, okay.
Examiner, there's a poster award. So there are some, every poster session has been assigned 1 or 2 professors to assess the posters. Otherwise, the posters will be simply displayed one by one by the Icee coordinator. During that time, just one by one. That's what I understand.
Okay.
Otherwise, all the posters are available in PDF. One can go and look at the posters. That is available at the session.
Then, Joby, do you close the session? No.
Yeah, I think we may have no option. I can just.
Because it's almost 5-7 minutes gone.
Yeah, correct. I don't think it will work now. So it does not work so far. It may not work.
Joby sir,
Just 1 more minute. Huh?
Yeah, I think Sharina has also prepared a poster. So, is it possible for her to put her work in poster also?
Yeah, she had a poster also that can be put in the poster tomorrow.
Yes.
Okay, in that sense, we can close the session, sir. That's better.
Okay. Okay, let me then close the session, in which we had 3 excellent talks given, 2 from one from Norway, one from Pune, and one from Germany, and they were really very good talks. So with this, I would like to thank once again Joby, Anurag, and everyone there. Stay safe, and bye-bye.
Thank you, sir. Thank you, Professor Paul. And for this time, once again, congratulate you for this award. And
Oh, that's my pleasure. Thank you.
Okay, okay, Dada.
It's all yours. Okay. Thank you. Thank you.
thank you.
Great.
Thank you, everybody.
Thank you. Bye.
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 अरे अलाउ करना था अच्छा तुम ऐसे ही किए थे allow नहीं करने। तो फिर डोंट टच क्यों नहीं ऐसे हो
Saurabh, hello? Hello?
Yes, ma'am. Abhi,
Hello?
yes, ma'am.
But what actually happened? See, this PPT was it was a heavy file. It was hanging, and I tried in other system. I don't know what happened. So the speaker, even I was able to listen everything, but my speaker was not working. So what is finally decided? It is drop the presentation.
No, yes, you can go for the poster session. So you can make your PPT as a poster and then present it as a poster.
Okay, but it's up. There was some few minutes, and there was a presentation in front, before me. There was a presentation supposed to given by Soumya, no, and my presentation
No, no,
supposed to
no,
start.
no.
Okay.
After Toby's study, you are scheduled.
Yeah, all right, all right. So see, the whole day I was preparing for it, and at that moment, I tried different systems that actually happened. I was sitting there in another for some time, then I dropped my laptop there, and I came here, tried with another system, and all the things.
इसमें
Okay. So now I think it's over, no? I think it will start from 5 o'clock now.
No, no, it's poster session from 3:30.
Okay. So we'll have 2 minutes, no?
Hmm.
Video start.
नहीं फोन पे कॉल करा है इसमें
Yeah, there are two things. तुम लोग जब आएगा तुम लोग बात नहीं कर सकते, हमारे पास अलग लिंक होती है, उस लिंक से हम जाएगा तो तब हम प्रेजेंट कर सकते हैं, हम वी कैन पार्टिसिपेट। तो सर को गुस्सा है ना, सर फोन इसलिए नहीं उठाए क्योंकि ऐसा कुछ पहले से बता देता है, आई शुड चेक इट बिफोर। मैंने तुम्हें बोला था यार, तुम
Ma'am,
लोग
you are
सब
not
गलती से
muted.
आ जाएंगे। अब किसकी गलती? किसी का भी इससे अच्छा घर पे बैठ लेते, तुम घर पे सब कुछ कर देते, वहाँ पे रोज डिस्कशन होती,
Ma'am,
वहीं बैठ लेना चाहिए।
अंचल वगैरह सारे सजल है अरोड़ा है, सुशील कुमार है।
Hello. For participant, no need to share your poster. We will share it from our end. So don't share from your side.
Hello, conference host. Can you please advise the participant how this poster session will go on? Because it's not very clear whether we will share one by one or how it is going to be. Kindly share the process how the poster session will be conducted, because we have already put up our poster files on the website. Thank you.
एक्चुअली इसमें कितने लोग
Hello. Hello, participants. Now you can start sharing your poster. We can start from poster number 46. So one by one, you can share your poster for 1 or 2 minutes, and everyone can ask question in chat box.
Hello, respected hosted sir. You may take the name of the person or number, post number. So if they are absent, we may go ahead. We don't know whether they are coming or not.
Okay, okay. So we are starting with poster number 46.
Yeah, yes, sir. Thank you.
So poster number 46, you can share your poster here.
Okay.
Yeah, hello host. You can also call the name of the person. If they are not present, maybe then we can move ahead.
Okay, actually I have this number wise list, so I don't have names. So I will call by poster number. So poster number 47, you can share if 46 is not here.
46 was Nikita Jain.
Okay.
So she is here, she can make a presentation. This is Shuchi Joshi.
Hello everyone, am I audible?
Yes.
Yes, audible.
Mine is poster number 47. So in this work, we have explored the hexagonal boron nitride material and have seen its potential in deep ultraviolet photo detection. So ultraviolet photo detection, ultraviolet light can be divided into 3 categories depending upon the energy range. Out of this, UVC light is the most energetic one and is referred to as the germicidal irradiation, because of which it has applications, a number of applications. Now, all these applications require state-of-the-art ultraviolet C photodetectors. Two-dimensional layered materials have been proven as the great materials, which can be used for fabricating photodetectors because of their properties like strong light-matter interaction and broad range of band gap. One such material is hexagonal boron nitride, which has ultra-wide band gap of around 6 electron volts and has high absorption coefficient. Also, it has a very high temperature stability. So in this work, we have mechanically exfoliated HPN nanoflakes using a scotch tape and have transferred them onto an oxidized silicon substrate. Using electron beam lithography, we have made the contacts. So finally, we got platinum contacts onto the HPN nanoflake, so that we got the metal semiconductor metal photodetector. And then we did the photo measurements. So firstly, we characterize the HPN nanoflake. So these are various characterization techniques that we used. Using all these techniques, we could infer that the mechanical exfoliation was successful and we got the flakes onto the substrate. Secondly, the thickness of the nanoflake was around 90 nanometer. Then we did the characterization of the device. We saw that the dark current was ultra low, of the order of 10 to the power minus 14 amperes, and we got a substantial increase in the photocurrent at the deep UV wavelength of 205 nanometer. From the repeated switching on and off the incident light, we could see that the current was following the input signal, and we calculated the rise and fall time of the detector. From responsivity, we can see that the device was completely irresponsive up to 250 nanometer wavelength, and it started showing response only in the deep UV region, giving a maximum responsivity of around 5.2 milliampere per watt at deep UV wavelength of 205 nanometer. While doing with temperature measurements, we could see that the current, dark current as well as the photocurrent was found to increase while increasing the temperature from room temperature to 200 degrees Celsius. Also, we see that the photo to dark current ratio, it decreased with temperature, while responsivity was found to increase with temperature. So at 200 degrees Celsius, we saw that responsivity was 32 milliamperes per watt. So with these results, we could see that the detector was stable even at high temperature of 200 degrees Celsius and giving such high responsivity while using the incident power density of only 44.6 microwatt per centimeter square. So our results show that the hexagonal boron nitride has potential for deep UV photo detection, and for it is an ideal material which can be used to fabricate the robust photo detectors. Thank you.
So next is Sneha Sinha, poster number 48, P48.
Good afternoon, everyone. Am I
Audible? You have time limit of 2 minutes, so please complete it fast. We have too many participants,
Yes, sir.
so you can start now.
Okay. In this work, should
Yes, yes.
yes. In this work, what we have done, we have synthesized MOS2 monolayers and using pulse laser deposition method, and we have studied their evolution of band structure with increase in number of monolayers, angle resolved photo emission spectroscopy. In this study, what we found that evolution of the valence band spectra with number of monolayers is dependent on interlayer coupling. So first of all, we used pulse laser deposition method for the deposition of single to few monolayer thick MOS2 films. The various deposition parameters used are provided here. By varying the number of pulses, we got one monolayer, two monolayer, three monolayer, four monolayer, and more than 5 monolayers. The substrate temperature was maintained to be 800 degrees. Oxidized silicon substrates, and the whole deposition was carried out in the background gas using nitrogen. So the measurement, the VBS or valence band spectroscopy measurements were carried out at RRCAT Indore using beamline 3 of the Indus 1 synchrotron. So the next results are that using AFM characterization, we confirmed that the height profile corresponding to the AFM scanning reveals that the synthesis of one mono. By using Raman and PL spectroscopy, we confirmed that the synthesized films have the characteristics E12G and A1G modes that are the characteristic peaks of MOS2, and with increase in number of layers, these bands shift. A1G basically stiffens with increase in number of layers, and E12G mode basically softens with increase in number of monolayers. And further PL results for monolayer MOS2 contains the two excitonic peaks A and B corresponding to the direct emissions, and further this photoluminescence suppresses with increase in number of monolayers. And XPS results further confirms that the ground films are stoichiometric. And this figure 4 represents the valence band spectra that was recorded using angle integration photo emission, where SiO2 as the Fermi valence band maxima at 4.66 eV. 0 is our Fermi energy. As the number of layer increases, the one layer MOS2 shows the molybdenum 4DZ square orbital feature at around 2 eV. With increase in number of layers, this 2 eV features shifts downwards towards the Fermi energy. So the basic reason the role of the orbital coupling basically results in the splitting of valence band, and as we increase the number of layers, this valence band maxima shifts towards the downwards binding energy. So interlayer coupling plays a vital role in deciding the properties of 2D materials or 2D heterojunctions. Using the Kraut's methods that basically employs the valence band spectrum and XPS core studies, we further calculated the valence band offsets and conduction band offsets at the silicon and MOS2 interfaces, and we found that with valence band offset and conduction band offset increases, and the band alignment at the heterojunction was found to be type 1. So in conclusion, what we have done, we have prepared large area and high quality MOS2 thin films using pulse laser deposition method. The evolution of band edge states in MOS2 thin films as a function of number of monolayers was investigated, and it was found that the interlayer coupling is mainly responsible for the shifting of valence band maxima towards Fermi energy, and band gap, or we can say as the number of layer increases, there is a transition from direct to indirect band gap semiconductors. And we are highly thankful to Vinay Gupta sir and Monica ma'am of Delhi University for providing the access to these deposition of the films, and RRCAT for providing the access to the angle resolved photoelectron spectroscopy. Thank you.
So next is poster number 49, G. Pakiraja.
Yes, sir. It's myself. I'm sharing.
So you can start. Please limit your talk to 2 minutes.
Okay.
Because we have too many participants. Okay.
Yes, sir. Yes, sir. No problem.
You can start now.
Yes, I'm sharing it. Is it seen, sir? My PPT.
No, still it's not visible. Yeah, now it's visible. You can start now.
It's visible, sir. Okay. So myself, Dr. Pakiraj, is one of the minor research. Actually, many people are working on ferrite material. They are doing many vast research, but it is a simple work. Like I was working in ferrite. Like ferrite is an example of antiferrite material, and it has high resistivity. Just I was working on M-type hexaferrite, and I was just replacing the FeIN with aluminum. I have done many series with a different element, but here I'm just explaining the replacement of Fe with aluminum. So I had gone for some small characterization like XRD, FTIR, and SEM, VSM, and dielectric also. So we are basically checking the dielectric property as well as magnetic property. What are the changes even in the crystal structure because of aluminum substitution? To make ferrite hexaferrites, I have used one of the common method, Sol-Gel auto-combustion method. It is the simplest method to produce a nano-level material, and I have seen some of the different property, like after substituting the aluminum with replacing the Fe with aluminum. Some of the changes in the particle size also, and dielectric property, especially the dielectric constant decreased, and in case of VSM, saturation magnetization decreased. These are the common expectation from this result, but still I will go for another research, and right now I'm working on some other application oriented one. So thank you this much. Hello.
Hello.
Completed, sir.
So next one is poster number 50, Anamika Ashok. Anamika Ashok.
Yes, sir. Can you hear me?
You can start now.
Okay, sir. Can you see my screen? Hello?
Hello, it's visible. You can start.
Okay. So good evening, everyone. The title of my poster is Ta3C2TX mexene with tunable properties. Mexenes having the general formula Mn plus 1 xntx is a family of 2D transition metal carbides and nitrides, which came into light only in the year 2011. The preparation technique is very simple. It is usually prepared from its 3D max phase precursor having the general formula Mn plus 1 As you can see, M is an early transition metal, X is supposed to be carbon or nitrogen, TX are functional groups like O, OH, F, and N can vary from 1 to 3. And A is an element of group 12 to 16. So, in the typical synthesis process of mixing, the max phase precursor is subject to the method of chemical etching by using fluoride-based etchant. So, in this, in the poster, you can see that I have prepared mixing using two etchants. One is hydrofluoric acid, and other is a combined LIF plus HCl method in which hydrofluoric acid forms in situ. It is subject to etching for a duration of 5 hours and 24 hours respectively, which results in the etching away of the A element. So here the max phase precursor I have used is Ta3Lc2 titanium aluminum carbide, which when it is subject to etching, the aluminum is etched off to give 2D layered structure, as you can see in the SEM analysis, which gives Ti3C2 mixing. And I have carried out several analysis, like the morphology has been analyzed through SEM, and the structural characterization and crystallinity has been studied with the help of X-ray diffraction. And when we talk about mixing, an inherent functionalization occurs because experiment is carried out in an aqueous environment which is rich in many functional groups, and this functional group is analyzed with the help of FTIR. And in the Raman spectrum, I could observe that a significant peak corresponding to titanium dioxide is seen at 150 centimeter inverse, which indicates partial oxidation of the material. And the pristine mixing doesn't show photoluminescence property, but I got photoluminescence, which means it indicates the presence of titanium dioxide. So, to conclude, I can say that I prepared Ta3C2TX mixing by etching Ta3Lc2 max phase, and I have used different concentrations of etchant, that is 48% and 24% HF was used in the etching process, and optimum layer features were obtained for the sample that has been etched using 24% HF for 20 hours. And the partial oxidation formation of TiO2 with significant PL emission from the defect levels of titanium dioxide is observed for 48% HFX sample. And this partial oxidation is suitable for SST switching applications. This means the morphology and the properties, the addition of functional groups, etc., can be tuned by using different types of agents as well as different concentration of the agents used. And I have also tried addition of ammonia as an intercurrent to the sample. And as you can see in the SEMMHD, it removes the TiO2 nanoparticles and better open accordion-like structure of mixin is obtained. Thank you.
Okay, next, poster number 51. Munindra. Okay, we can go to next, poster 52. Pradeep Kumar Kashyap. Pradeep Kumar Kashyap.
Hello.
Hello, Pradeep.
Hello.
You can start.
मुझे शेयर अपनी फाइल कैसे करनी है? ऊपर जाके
Hello.
Hello. Hello.
Hello. You can start now. Pradeep. Okay, we can go to question number 53. I think there is some problem with Pradeep Kumar Kashyap. Internet connection.
हेलो
Hello.
हाँ सर, मैं प्रदीप बोल रहा हूँ.
हाँ. Your slide is still not visible. Hello, Pradeep.
Hello. Hello.
Hello.
Sir Pradeep, can you hear me?
Yeah, you can start now.
Sir, can you see my slides?
No, now it's not visible. Previously, it's visible.
Sir, if you don't mind, may I start after some time?
Okay, no issue. So is next poster 53. Next is poster number P54, Sunil K. Arora.
Yeah, hi, I'm present. I'll share my poster. So, are you able to see the screen?
No, it is still loading. Now it's visible. You can start now.
Yeah. Okay, so I'm Sunil Arora. I belong to Punjab University, Chandigarh, and I'm making a presentation on phonon scattering mechanism investigation in 2D layered MOS2 WS2 heterostructures. So to prepare these heterostructures, we prepare the nanosheets first using the liquid exfoliation method. By using liquid exfoliation method as shown in the experimental detail view graph, you can see that we provide a force to separate the layered material with the help of some solvent and ultrasonic force. And by using this process, it is it is easily possible to produce nanosheets. And once we produce the nanosheet of individual material, that is MOS2 and WS2, which are transition metal dichalcogide materials, we prepare these nanosheets and then we mix them using the using different proportion, 1:1 or 1:2 or 1:3. But here we are presenting a result on the MOS2 WS2 heterostructures, which are prepared by having 1:1 proportion, and we characterize these heterostructures once they are prepared using this mixing solvent mixing method. We study them using X-ray diffraction. We also look at their structure using electron microscopy, and we also study the Raman spectroscopy at room temperature as well as a function of temperature. So from room temperature investigation, first we ensure that the material we are dealing with, it is single to few monolayer nanosheet powder, and then we mix, then we produce the heterostructure. So we get the appropriate Raman peak separation, which is between the in plane and out of plane mode, that is EZ and A1-2Z mode, and their separation gives us what is the layer thickness. And once we produce the heterostructure, then we perform their temperature dependent Raman spectroscopy on the individual nanosheets, constituent nanosheets, as well as on the heterostructure. And what we notice that with increase in temperature, there is a softening of both the phonon modes. And then we model this temperature dependency with the help of a model, analytical model, that takes into account the thermal expansion as well as multi-phonon scattering processes contribution. And what we notice that there are certain non-linearities within the given observed temperature dependence, and that can be explained with the help of multi-phonon scattering processes. And we also notice from the TGA measurement that the heterostructures provide more, has more stability than the individual nanosheets or individual constituent nanosheets. So in conclusion, we prepare these heterostructure using a simple solvent mixing method of nanosheets which are produced by liquid exfoliation. We study their phononic temperature dependence using Raman spectroscopy. We find that the non-linearities can be explained with the help of multi-phonon 3 and 4 phonon scattering processes. And heterostructures are relatively more stable than the constituent materials. Thank you. So if anyone has any query, I can take it up, or you can send me an email or call me later. Thank you.
Okay, next, poster 55. P55. Okay, I think Icee maybe is not there. We can start with poster number 56. Poster number P56. Anju Kumari R.
Hello, good afternoon, sir. Hello.
Hello.
Hello. Hello.
Hello, your voice is coming. Please share your poster.
Hello. Am I audible? Hello. Am I audible?
Yes, you are audible and your poster is also visible. Please start your presentation.
Yeah, good evening all. I'm myself Anju Kumari from Reva University, Bangalore. My topic of presentation is self-rectifying bipolar resistive switching in TiO2, 2D TiO2 nanosheets. As we all know that TiO2 have been extremely studied for the bipolar or the switching properties since that was first reported on this material. But I have in detail studied these properties in the 2D TiO2 nanosheets. So why then this 2D nanosheets we have grown by using an hydrothermal process, and after that we have whatever the powder we obtain with an ethanol. Hello. Ethanol, and we have coated a thin film of TiO2 nanosheets on an FTO substrates, and we have used in silver as a top contact. Then we have done the resistive switching studies by sweeping the current voltage from in the direction of 0 to -1, and again sweeping it back from -1 to 0, and again the positive side from 0 to +1, and again reversing back into 0 to +1 to 0. As we observed here, we saw a very good bipolar switching
both in the positive and negative region. And we also found out that the forward to the reverse current ratio was nearly by one order. You can see here it was 30 milliamp to 3 milliamp. So this our device showed both a bipolar resistive switching along with the rectifying characteristics, which is very good for a device. And then we also studied the retention studies of this device. We found that a device can can retain its state for more than 3,000 seconds, and it was nearly in two order of switching which got, and at the rate voltage of minus 2 0.2 volts. So the rectifying behavior can be attributed to the Schottky contact formed by the near the TiO2 and AC interface, AG interface, and this device can be used as a effective solution to overcome the sneaking current problem which we usually face in crossbar array structures. Thank you.
Is P57.
Hello, sir. Hello.
You can
Hello.
start now. You can start your share your presentation and you can
Okay,
start.
okay, okay, sir. Okay, sir. Sir, is my poster is visible? Hello.
Yeah, it's
Hello.
visible.
Yes, it's visible.
Okay, sir. Good afternoon. I am Swati B. Shashindran, and my topic is optimized temperature for the growth of MOS by single-step chemical vapor deposition. And we know that MOS2 it's a layered transmetal dichalcogenate, and its band gap is 1.2 electron volt for bulk and to 1.8 electron volt for monolayer. And these nanoparticles and it is a layered material, and the layers are connected by weak interval force. So these materials can originate in two directions, that are horizontal and vertical. The horizontal growth is layers are grown in planar direction, whereas in vertical growth the layers are grown standing upright on the substrate, exposing their edges. And coming to this horizontal and vertical MOS2, the horizontal MOS2 is used for optoelectronic application, whereas vertical MOS2 is for sensing application. For vertical MOS2, it has exposed molybdenum and sulfur atoms, so its surface have high chemical activity, and it has high d electron density, so it has strong binding interaction between gas molecules and MOS2. So, and MOS2 is an n-type semiconductor, so it has a negative resistance change on reducing gas such as ethanol and methanol, etc. And there will be a positive resistance change for oxidizing gas such as NO2. I prepare vertical MOS2 by I am concentrating, my application is concentrating on sensors, so I prepare vertical MOS2 by using chemical vapor deposition method, for which I use MO3 and sulfur powder as precursors, and which were in the ratio of 1:6, and the SiSiO2 was used as a substrate, and the temperature is varied from 600 degrees Celsius to 750 degrees Celsius. We need to optimize a low temperature for the growth of vertical MOS2, and characterizations were carried out are Raman spectra and morphology. Raman spectra is is a powerful tool to identify molybdenum disulfide. For molybdenum disulfide, Raman it has two main Raman peak, E12G and A1G. For samples which prepared at a 600 degrees Celsius, 650 degrees Celsius have these two peaks, and 750 degrees Celsius also have this peak, but it has an impurity peak. The sample prepared at a 600 degrees Celsius as well as 650 degrees Celsius was of MOS2. But when we discussing on the thickness of the sample prepared at a 650 degrees Celsius is minimum Raman shift of 23.3 centimeter inverse. This Raman shift is proportional to the number of layers, as for monolayer it is from 118 to 20, and for bulk it is up to 25 centimeter inverse. So our obtained film was of few layered. And and here from Raman spectra we can observe that the A1G peak is more intense than that of E1-2G peak, which indicate that this sample has vertical morphology. From literatures it was understood that Raman spectra with the high intense A1G peak is corresponding to vertical MOS2. And coming to the morphology, we can clearly see in that the morphology is also changes with the change in temperature, and at a 650 degrees Celsius we can obtain vertical structures with the minimum thickness, and the vertical this MOS2 is uniformly grown throughout the substrate. So as a conclusion, we obtained that we optimized the CVD system to produce vertical MOS2, which is very low temperatures compared to other proposed work. So and this vertically grown MOS2 can be used for sensing application, and that's about. Thank you.
Hello.
Hello.
Next, poster 58, Narendra Kaur. Narendra Kaur. Okay. Okay, let's move to poster number 59, Chanchal. Okay, next poster number 60, John Wellington.
Hello everyone, I am John. I am working under Dr. Samresh Das in care department. So I am going to explain to you about the large area low power MOEC2 nanostructure which we have grown on flexible substrate for the SWR infrared detection material. SW infrared detection. So we have actually grown the MOC2 by hydrothermal method using hydrothermal route using sodium molybdate and selenium powder as a precursor in hydrazine hydrate. So we have maintained the pH of the solution up to 12 using NaOH. So after using this, we have sealed the autoclave and temperature was maintained to 180 degrees Celsius for 48 hours. So the end result was the precipitate of MOC2 film, or we can call it as a flower-like nanostructures. And what we found is like we have some oxygen-related defects as we can see in the figure 2, using XID, we have find that some oxygen related defects are coming between MO and selenium. So these defects lead to the ultra high absorption range of the MOC2 from actually from 800 to 2400 nanometer of wavelength. So we have we have spray coated this on ID structure of in PET substrate, and we have measured the wavelength dependent and also strain dependent characteristics of the photodetector, MSM photodetector. So as you are seeing in the figures, we have a PET substrate over which we have a deposited MOSC2 by spray coating, and we have given a strain. We have measured the time response with respect to light incident upon it. So we have receiving a 5.9 seconds of on of turn on TR and off of 2.0 seconds. So we have measured the wavelength dependent response of MOSC2, and we are getting a far response up to 2.4. 2.5 micron of wavelength, and we have done this strain dependent measurement, and a maximum responsivity of 2.75 ampere per watt is coming at 2000 nanometer of incident of 2.475 ampere per watt of 200 nanometer wavelength. And also these photodetector are working up to 500 cycles of bending cycles. So this is my work, and finally to conclude, we have attended a MOSC2 nanostructure based flexible IR photodetector for in room temperature, which is capable of detecting up to 2.4 micron of wavelength. Thank you.
Okay, next one is poster 59, Chanchal. Chanchal, are you here?
Hello. नो एक्चुअली मैं फोन नहीं किया था, वो मेल किया था। फोन करके वो बोल रहा है दूसरा नंबर दे दिया। ओके अभी पता नहीं, मतलब अभी मेरा भी चलेगा एक्चुअली, और मैं अभी रिक्वेस्ट कर रहा हूँ उसको। ठीक है, 1 मिनट में अभी बात करता हूँ, मेरा टाइम आ गया। हाँ
Next poster 62.
Yes, sir.
Mosmi Pramanik.
Yes, sir. Am I audible?
Yes, you can share your content and you can start now.
Hello. 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 Yes, sir.
Your slide is not visible to us.
Is this visible, sir?
Yes, it's visible. You can start now.
Here I have mentioned Motion Pramanik, and National MOS2 nanoflowers for photodetector application. Here I have grown MOS2 nanoflowers by one-step hydrothermal process using molybdenum and by changing the hydrothermal parameter, we were able to change the morphology. As MOS2 have the tunable band gap like 1.9 for single layer and 1.2 for bulk. It can be used as a photodetector and it can be used as photodetector. We studied the XRD, Raman and PL spectroscopy of the MOS2. Here it is the XRD spectra of MOS2. Two peak. One is for one E12G and A1G. E12G is for in plane vibration and A1G is for out of plane. Difference between two peaks is like 22 centimeter, and hence we can say the MOS2 has a few layers like less than 5 layers. Lower intensity of E12G peak compared to A1G peak indicates the MOS2 is sulfur rich, and here is the PL spectra of MOS2. Two peaks at 621 nanometer and 661 nanometer are due to the neutral exciton transition, and the third peak at wavelength 73 nanometer is due to the transition of the charged exciton. Here it is the same image of MOS2. APSM image of MOS2. This is a flower-like morphology and with mean diameter of 0.48 micrometer. And by changing the parameter like hydrothermal parameter like time, we are able to change the morphology. Like this is the flower-like structure, and we got this is the cotton ball-like structure. Here the mean diameter is 1.2 micrometer. And here the conclusion MOS2 and one-step method, and MOS2 analysis nucleate to form both flower-like and cotton ball-like structure depending the process duration. And Raman data reveals the MOS2 are sulfur-rich and nanoseeds are about 4 to 5 layers thick. And the PL spectra indicates the existence of neutral and charged excitons. Thank you.
Poster 59. Chanchal, are you there?
Hello? Hello? Hello?
Where are you? Hello? Hello?
Yes, yes, Chanchal.
Hello? I'm audible?
Yes. Please share your screen.
Okay. Hello? Hello? Hello?
Yes.
Um, can I join in 2 minutes or
Okay, fine. Let's move to next.
Pradeep Kumar Kashyap, are you ready? Pradeep Kumar Kashyap, poster 52.
Hello? Hello?
Pradeep.
Sir, can you hear me?
Yes. Now
Sir,
you are ready to share
yes, sir.
your slide? Or I can share your slide. You can present.
Sir,
Pradeep.
yes, sir. Can you, sir? Hello? 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 Hello?
No, it's not visible to us.
Sir, speak, if you allow, I'm facing the problem here in
Okay,
sharing.
we can do one thing. I am sharing your slide. You can present it. Okay.
Okay, thank you very much, sir. Thank you very much, sir. Sir, shall I?
Yes, you can start.
Thank you very much, sir. Sir, my work is related to the growth of the CVD graphene by the chemical vapor deposition system for the fabrication of the culture device mainly. So graphene is the one layer thick of the layer of the carbon atom in which within the layer different carbon atoms are linked by the sigma bond, and different layers of sigma bond, and the different layers of the carbon atoms are attached to one another by the pi bond. So graphene can be used to have different applications like composite, sensor, transparent electrodes, and conductive inks. In my case, I'm growing as I'm focusing on the mostly on the quality of the graphene. So I'm using the CVD graphene chemical vapor deposition technique for the growth of the graphene. So this is the schematic diagram of the CVD system that we are using in our lab. We are using only two mass flow meter, one mass flow meter for the controlling the gas of the hydrogen through the CVD, and we are using only two mass rotameter for the controlling the gas of the methane and the argon. We are for the growth we have to first anneal the, we take the temperature of the furnace to the 950 degrees Celsius. After that we have to anneal the in the atmosphere of the hydrogen and argon. After that we have to anneal the substrate for the approximately 5 to 10 minutes, and we have for the growth period we have to stop the argon gas, and in the we flow the methane gas. We are using methane gas as the precursor gas for the as a source of the carbon atom for the growth of the graphene. For after the once the growth is complete, for the growth we are maintaining we are growing the graphene for the period of we are flowing the gas for methane gas for a period of 5 to 10 minutes through the CVD furnace. After once the growth part is completed, we cool down the furnace and take the substrate copper foil on which the graphene has grown out for the transfer of the graphene from the substrate to the different other substrates like silicon and the glass substrate. For the transfer mechanism, we are using the wet chemical method, in which we have to first we have to etch the copper substrate from the below, which is below the graphene by the nitric acid. After that, when the copper is dissolved in the nitric acid, so then we have to take a scoop out the graphene on the desired substrate for the further characterization. For the to analyze the quality of the graphene, we have used Raman.
Next, poster 64, Venkit Rao.
Hello, sir. Am I audible? Sir, am I audible, sir?
Yes, please share.
Yeah, thank you, sir. Yeah. Yes, sir, I'm sharing. Sir, is it visible, sir, like my poster?
Yes.
Thank you, sir. Good evening, all. My name is Icee Venkit Rao. Like I'm from Bitsville and Hyderabad campus. So today's topic is fabrication of the broadband photodetector based on WS2 quantum dots and SNS. So here, the research on the development of photodetectors focused on the improving of the responsivity in the particular region of the electromagnetic spectrum. The parallel research was towards increasing the spectral range of the photodetector also done. Till date, many concepts have been reported for increasing the spectral range, which includes the band gap modulation, hybrid structures, discrete distribution, and the contact engineering for the fabrication of the broadband photodetectors. Even though there has been success towards the development of broadband photo detector. The issue that still remains is improving the responsivity and as well as the broadband spectrum. Hence, there is a need to develop broadband photo detector, which not only increases the spectral range but also focus on the improving the responsivity. Here, what we have done is, so we have fabricated the uh, broadband photo detector using SNS, which is P-type, and WS2 quantum dots, which is N-type. And then what exactly we have done is we have dropcasted the WS2 quantum dots and SNS which is quoted on the paper. So when it comes to the experimental section, we have synthesized the SNS using hydrothermal synthesis, and then after synthesizing SNS, we have vacuum filtered the synthesized SNS on cellulose paper, and the next step is and parallelly we have synthesized the WS2 quantum dots also, and these synthesized WS2 quantum dots are dropcasted on the SNS coated paper. So now, and we made like we need to make sure that the WS2 quantum dots are discretely distributed, so that like you will get number of the PN junctions on the substrate, like between SNS and WS2 quantum dots. And then if you see the SEM diagram, like we have done the characterization to confirm the SNS. And if you see the SEM diagrams, you can see the SNS nanobelts, and we have done the XRD, and we have done the XPS analysis and Raman analysis. And it is well matched with the literature. And then what we have done is like we have done the this is the WS2 quantum dot STEM diagram, and from the TEM diagram we can confirm the discretely distributed WS2 quantum dots. And then we have performed the different photo direction experiments like with under UV light and visible light and NIR light. So with the increase of the intensity, so we have observed the increase in the photo current, like, and we have calculated the corresponding responsivity, detectivity, and external quantum efficiency. And then the photo direction mechanism can be easily explained by the band structure. So from the band structure, you can understand how the electrons, like how the Schottky barrier helps in the separation of the photo generated electron hole pairs. Like basically the internal there is a localized electric field between these WS2 quantum dots, which is N-type, and SNS, which is P-type. So due to this internal electric field, the photo generated electron hole pairs gets separated effectively. So and then like these metal contacts also we have taken from SNS. Both the contacts are taken from the SNS to enhance the photo generated charge carriers. So thank you so much. Like any questions? Like
No, thank you.
no.
Next poster is 65, Abhilasha.
So should I stop sharing it? Like
Yes, yes. Please stop.
yeah, yes, sir.
Poster 65, Abhilasha, are you there? Poster 66, Pradeep Kumar.
Yes, sir.
Yeah, please share. Yes, please take 2 minutes, not more than that.
So can you see the slide?
Yes.
Okay. Sir, so, the topic is the sputter deposited 2D amorphous thin film for spintonic application. So basically, the people are introducing the 2D materials in the spintonic devices to make the flexible spintonic devices, and these 2D materials basically replacing the metal oxide based barriers in the MTJs, magnetic tunnel junction. So here in this work, we basically introduced the ultra thin film of MOS2 in the magnetic tunnel junction. So first we basically fabricate the heterostructures by using the MOS2 as a barrier and NAMinium thin film as a top and bottom electrode, which is ferromagnetic shape memory alloy. So to characterize the the heterostructure, we basically do the XID, and we see that the MOS2 phase is present in the hexagonal, and this anion is present in the austenite phase. And this is the FSM micrograph for the MOS2 thin film, which is shows the like structure. For the roughness measurement, we basically do the AFM measurement, and it shows the very low roughness, and it is basically important for the sharp interface. For the thickness of barrier, we basically and we found film thickness is around 6 nanometer. And for elemental and oxidation measurement for MOS2 film, we did the XPS measurement, and it's found in the MO3D and S2P phase. So, and it is the ratio of MO and S is 1 is to 1.99 for MO and S ratio. For band gap measurement, we did the PL measurement, and the band gap is around 1.676 electron volt, which is very close to the monolayer of MOS2. And again, we did the Raman measurement for M film, and the number difference between these two modes, Raman modes, is around 24 centimeter, and which is basically in between the monolayer and the bulk MOS2 thin film. For the magnetic characterization of the ferromagnetic shape memory alloy electrode, we did a magnetic hysteresis loop. We plot for different thickness and the different temperature. So that the saturation magnetization of the enamel film basically it is different for different thickness and different temperature. Okay, so after that we did the electrical and the magnetic transport measurement for the fabricated magnetic convection, and we did IV measurement, and there is a appreciable resistance junction, magnetic tunnel junction, which basically shows the semiconducting nature of the barrier. And junction basically plot conductance and the second derivative of the IV. We found junction is more stable as compared to the room temperature. So this is the schematic of the device, and this is the band diagram of the heterostructure. So in TMR measurement, we basically sweep the magnetic field from -4 test close to the +4 Oersted, and maximum value percent is found for 10 Kelvin, and the TMR ratio basically decrease with temperature, and there is a finite TMR ratio is found for the room temperature also. So the device can be used as room temperature application, and some MOS to basically deposit the MOS at low pressure, and we create the sulfur vacancies. So we basically also find the magnetism in MOS to and this could be attributed to the age vacancies percent thin. So in this measurement, we can also conclude that the MOS2 film basically can be used for the spintonic application or for flexible spintonic devices. Thank you.
Thank you. Next is L. Chandrasekhar.
Hello, sir.
Please share. I can see.
Is my screen is visible, sir?
Yes. Please go ahead.
My poster title is Modeling the Electrostatics of Two-Terminal Boron or Nitrogen Substitution Doped Metal Insulator Graphene Structure. So here we have modeled the individual electron and hole concentration of the boron or nitrogen substitution doped two-terminal structure. So here we have considered the effect of substitutional doping such as shifting Dirac point with the band gap engineering and change in carrier sheet density and quantum capacitance. So this is the structure. This is the two-terminal structure. So here the substitution doped graphene is encapsulated between these two insulators. And after we have considered the top metal gate, and here we have considered the p-type doped silicon as a body. And here figure 2 shows the energy momentum relation of the pristine graphene, and also it is showing the comparison between nitrogen substitution doped graphene and boron substitution doped graphene. So from here we can note down that so when we substitute boron or nitrogen, atoms to the same sublattice points of graphene. So it is not degrading the linear dispersion, and also it preserves the intrinsic properties of graphene. And here we can see that the linear energy momentum relationship is preserved. And also when we doping with nitrogen atom, due to the electron rich behavior of nitrogen atom when compared to carbon atom, it is behaving like n-type doping, and it shifts the Fermi level inside the conduction band, and also it creates band gap in it. Similarly, due to the electron diffusion property of boron when compared to carbon atom, when we substitute in the same sublattice points, it shifts the Fermi level inside the valency band and it behaves like p-type doping. And the corresponding electrical equivalent circuit is shown in figure 2b. And these are the electrostatics such as individual electron and hole concentration with respect to channel potential. And here we obtained the channel potential and switch charge density by solving the Poisson's equation, and the equations obtained through electrical equivalent circuit. We solved these two equations self-consistently to obtain this QSH. And these are the results. So here we can see that from C charge density, so the bipolar gating effect, which is in undoped graphene, is significantly suppressed in the case of nitrogen doped graphene and also in the case of boron doped graphene. Thank you.
Thank you. Thank you. Next is Khadija. Are you there? Poster 68. Okay, then poster 69, Neeraj Goyal. Are you there? Neeraj, are you there?
Yes, sir, I'm there.
Please share.
Just a minute, sir. My screen is visible?
Yes.
Okay. Hi, everyone. I'm Neeraj Goel giving my poster presentation on reduction of NO2 on large area MOSC2 surface. Actually, today we are facing the problem of air pollution everywhere, and 9 out of 10 people are suffering from the poor quality air. And in this poor quality air, NO2 shares a major portion, and this NO2 is emitted particularly from the automobile industries and from the forest fires. And this NO2 not only degrades the environment, it also causes several kinds of communicable and non-communicable diseases to human beings. It also forms the acid rain in the environment and degrades the archaeological sites. So to address these issues, we have formed the NO2 based sensor, and in this device we have grown MOSC2 by using sputtering coupled with the sulfurization process. We have few advantages of using this technique. The first one is it is very easy, and the other one is that we can grow a large area MOSC2 over the whole surface. And the third one is that we can control the thickness of the MOSC2 very easily, because in most of the two-dimensional materials, we are facing the problem of controlling the thickness. But in this technique, by controlling the thickness of the pre-sputtered metallic film, we can control the thickness of the deposited MOSC2 layer. The spectroscopic and microscopic measurement shows that we got a very high crystalline MOSC2 film over the complete surface, and the morphology shows that it is uniform and continuous throughout all the surface. To check the gas sensing ability of the device, we expose our device under NO2 environment, and it NO2 extracts the electron from the MOSC2 surface, which results in increasing its resistance. So by measuring the change in the resistance, we measure the sensitivity, and the device shows quite a good sensitivity of around 40 at 100 ppm. So we have done the measurement at 100 degrees centigrade because at room temperature the ambient oxygens stick on the surface and the number of available active sites will be less. So we have to give some external energy so that the ambient oxygen will be removed and the number of sites will be more, so that more NO2 could absorb onto the surface. So we have done the measurement, and it was found that that MOSC2 works as a perfect candidate for making NO2 gas sensors. Thank you. Thank you very much.
So next poster 70, Sushil Kumar.
Yes, sir. Am I
Sushil Kumar,
audible?
are you here?
Yes, sir.
Yeah, you can share your content and you can start now.
Yes, sir. Can you see my screen, sir?
Yes.
Okay. Good evening, everyone. The title of my poster is Thermoelectric Transport in Noble Metals Monolayers, the first principle study. Noble metals, due to their chemically inert nature, have found several applications in the interconnects in the electronic circuits, as well as catalysts and electrodes. And recently, et al. Have discovered a 2-atom thick gold nanosheet having no bulk atoms. So, in our study, we explore the electron and thermal transport in the noble metals monolayers modeled in graphene-like lattice for AU, AG, CU, and PT elements by simulating a realistic two-probe device. Use the non-equilibrium function approach, and we find the transport property using the Landauer-Buttigieg approach in linear response design. Here we have find the electronic and phononic transmission function for every monolayer, and we can see that each monolayer show metallic character, and both the electronic and phononic transmission functions show a non-ballistic transport behavior. Also, the electronic transmission is enhanced in PT monolayer about the Fermi level, which give rise to a high electronic contribution to the thermal conductance. Also, the kappa EL, which is electronic contribution, varies in a non-linear fashion with the temperature, and while its phononic counterpart varies with initially show an inclined steep and then saturates to a metal specific value. And talking about the phononic contribution, in the PT monolayer, it is found to be least and about 3.7% at room temperature, and for non-zero for zero bias condition, and it can go as high as for the AU monolayer, which is about 66% in at low temperatures. And we also calculate the thermoelectric properties like thermopower S and figure of merit ZT. And for non-zero bias, for zero bias, we don't found any desirable value for S and ZT, but we can tune by external bias, and we can achieve a high thermopower in PT about 1.05 millivolt per Kelvin and a ZT of about unity in the PT monolayer. We also check the anisotropy in the transport properties, and we find that the thermoelectric properties are isotropic along both the armature and zigzag directions. So in summary, we have find the thermoelectric properties for the noble metals monolayers, and we find PT as a potential candidate for thermal generation of electricity as compared to some transition metal dichalcogenides like MOS2, MOSE2, WS2, and WSE2. And thank you.
Thank you. Next is Ashok Kumar. Are you there?
Yes, sir. Good evening, sir.
Yes. Please share. And try to finish in 2 minutes.
Sure, sir. Oh, my site is visual. Slide is.
Not yet.
Hello, now visible?
It's coming actually. Not yet.
Now,
No. Try again. Yes.
now visible.
Not now. Yes, yes. Now you can start.
Yeah, sorry for delay. My topic is in situ growth of the hybrid nanostructure thin film of MO2 MS2 using conventional CVD method. Actually, I have synthesized the MO2 using the precursor of the MO3 and sulfur at the 850 degrees Celsius, and argon flow is my 60 SSM. I have synthesized for because MO2 structure MO2 is a highly stable at high temperature, and it is used for the highly charged capacity in energy devices. We can use it is in also as a gas sensing applications. So I have characterization this MO2 thin film using FESM XRD. I have taken the ADX, AFM, and I measure the IV of that thin film. This is my experimental setup. You have seen this, in which I use the SiO2 substrate. Then I have do the RCA1 cleaning. Then I have deposit that using the thermal CVD that MO2 thin film, and I have deposit the chromium gold contact. And the contact thickness is 200 nanometer, and then I do the IV characterization of that film. So this is my same images which will show that this is the hybrid structure, and I have depicted as a horizontally, means I have put the substrate face down to the both of the MO3 precursors. And this XRD peak confirm that I have the MO2 peak in which and MO3 which is converted into the MO2 and MO2 peak. This is the my AFM image, and I do IV characterization on different temperature. I will take 50 degrees Celsius and 100 degrees Celsius, which will show me that the 800 degrees Celsius the peak 50 degrees to 100 degrees the peak is some peak divert from the zero volt current, and the current is around 10 to the power minus 15 milliampere in this and I have this the application is the NO2 sensing, and in the highly HER highly capacitive energies we can use that. Thank you. Any question? Hello.
Yes, thank you.
Thank you.
Now
Thank
we'll
you.
move to next Nilu Sharma.
Yes,
We are
sir.
running out of time. Please do it quickly.
Yes, sir. Sir, is my screen visible?
Not yet.
Now?
Yes. Please start.
My poster title is Growth and Characterization of SNS2 through Thermal Chemical Vapor Diffusion Method. We have grown the SNS2 crystal using the conventional chemical vapor diffusion method. Till now, only some reports are there of SNS2 growth, and among them, only few are of SNS2 by CVD method. SNS2 is a 2D material, belongs to the transistor metal type chalcogenides family. These have been thoroughly studied as a series of noble semiconductor with an automatic thin layer structure. As we all know that the earlier graphene is used, but due to its zero band gaps, its electron property limits. So here we use nowadays we use the 2D sulfides, which have excellent electronic property due to their band gap, due to their visible band gap and high surface to volume ratio. The figure 1 shows the experimental setup of CVD, and the figure 2 showed the quartz tube in which quartz tube
say, for this we use two precursor SNO2 and sulfur, and this crystal needs very high temperature because the melting point of the tin oxide is very high. So here we use the temperature with 1050 degree Celsius, and the difference between this zone 1 and zone 2 is 16 centimeter in the quartz 2, and the substrate we used here is the silicon dioxide silicon substrate which is 300 nanometer. And for the characterization, the surface and structure morphology was investigated by scanning electron microscopy, and the phases in the crystal is determined by the X-ray diffractometry, and the crystal structure is determined by the atomic force microscope. The figure.
Thank you. We are closing this session because next session is going to start at 5 p.m. Thank you so much.
Hello. Hello. Hello.
Yes. Yes, please.
Participant.
Hello.
Hello, sir.
Am I audible?
Hello.
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 Hello. Hello, Anuj, sir.
Yes, yes. This is Anuj here.
Yes, I am Chaudhary Avinash Bhuyan. My poster ID is 76, and it is not actually showing. Actually, means image is not showing. So that is the problem. I contacted the technical team, but they told to rectify it. But till now, it is not happening. So they told me to shift to tomorrow or today if possible. They will find it out any route, but it is not happening.
Yes, yes. They will move it to tomorrow. So we will find that. We'll move it to tomorrow. And so I'll tell the technical team to move it to tomorrow. So let's move on with the session.
Hello.
Yes. So
yes, sir. Pradeep here.
Please, Pradeep.
हाँ सर, वो मैंने प्रेजेंटेशन दी थी, मगर बाद में मुझे पता नहीं चला कि मेरी प्रेजेंटेशन कंप्लीट हुई कि नहीं हुई, क्योंकि अब दूसरी साइड से आवाज नहीं आ रही थी, तो मुझे पता नहीं चला कि कम्युनिकेशन हुआ कि नहीं हुआ.
Right. So just you can discuss this with Dheeraj in the ICWE team, or I will also tell. So Pradeep, and you can just write a small note to me, both of you and the earlier person also, and we'll take it up. If it wasn't done, then we can actually have it scheduled for tomorrow afternoon. So just send a small email to me, you also and the earlier person also. So now I think we'll move on with because it's 5 o'clock. We'll move on with the session. So we have our invited talks in this evening session, and we have two co-chairs for the session. Professor G.V. Pawan Kumar, he's here. Hi, G.V. Hi, and myself. So both of us will be chairing this session. So we have the speaker also here, Professor Jian Fan Zhu. I see him logged on. Professor Zhu?
Yes. Can you hear me?
Yes, Professor Zhu is also here. So I will introduce the first speaker, Professor Jian Fan Zhu, and Dr. Pawan Kumar will introduce the second speaker, Professor Michael Ganwa. And so I'll just give a brief summary description of Professor Zhu. Somehow we cannot see Professor Zhu. Just 1 second, I think.
I can turn on my video because I see most people, the video is off, so I turn my video off as well.
Yes, Professor Zhu. Yes, we can see you now, and so great to have you here. So I'll just give a brief description of Professor Zhu. And Professor Jian Fan Zhu is a James J. and Carol L. Shuttleworth Professor of Mechanical Engineering at Purdue University with a courtesy appointment in Electrical and Computer Engineering. He obtained his MS and PhD degrees in Mechanical Engineering from University of California, Berkeley, and his current research includes ultra-fast and nanoscale optics and their applications in energy transfer, conversion studies, and nanomanufacturing. He is a recipient of ACME Heat Transfer Memorial Award. He's a fellow of the American Society of Mechanical Engineers SPIE, and the Optical Society of America. He currently serves on the editorial board of Scientific Reports. So today, Professor Jianfang Hu is going to be talking about highly localized electromagnetic fields for emerging applications. So we have Professor Hu here. Yes, so please, we can start from here.
Thank you, Professor Dawan, for your invitation. Let me first try to share. Sharing is going to work. Can anybody see my PowerPoint slide? Does it work now?
Yes, we can see it, I think.
Okay, great.
You just have to put that in the PowerPoint. Be perfect. We can see it.
Great. Okay. Thank you again, Dr. Dawan.
Thanks.
It's my great pleasure to give a talk at the conference, and actually, I was anticipating. I wish I had a chance to visit Delhi again. We couldn't only attend this conference, but unfortunately, that I can't make it. Sure. Anyway, so today I'm going to talk about electromagnetic field for emerging applications. So this outline on my talk is as follows. I will first give a very brief view of this electromagnetic phenomena and nanoscale. Then I will talk about a couple of applications that has been carried out in my group for many years actually. So some of the materials that I talk about are quite old, let's say more than 10 years or even longer. Then I also talked about some very recent work on surface plasmas in 3D materials. Those are probably happening in the last 2 or 3 years. So that it covers quite a bit of the topics that I want to talk about. So basically, we are looking at nanoscale optical antenna, and that is basically shrink the large size centimeter or even larger size antenna to nanometer scale and apply those antenna in the frequency of optical frequency on near infrared wavelengths. And we are trying to deliver light locally to tens of nanometer spots and with high efficiency or high transmission. So these are two criteria. One is localized light spot and also a high transmission, high efficiency. So very briefly, let's see. So very briefly, we probably all know the nanoscale antenna. The simplest one will be, let's say, just a metal bar. When the wavelength is about half of the, or when the length is half of the wavelength or multiple of half of wavelength, then you have hotspots. If you bring two of these antennas together, then there's a gap mode. The gap mode has a larger enhanced field or a larger a more intense hotspot. Then if you change the shape of this rod to something like, let's say in this case, a bow tie, then you have even a higher intensity hotspot. And this was like, we studied this probably more than 20 years ago. And then in this bow tie shape, we call bow tie antenna. And then when electromagnetic wave incident on it, and then you have a hotspot, you can calculate right now using very many commercial softwares, consoles, ANSYS, and so on and so forth. You can calculate the hotspot, which gives you an enhanced electrical field. And then you can also make a kind of a different structure, what we call aperture, that this metal actually wrap around everywhere here. So this becomes an aperture. Then electric field polarized in this direction. You still have a hotspot, but of course you don't have a background electromagnetic field. The light only emerging from this hot gap. So again, you still have a gap mode. You still have a very highly enhanced field. And then there is one more thing that probably less known to the application community at least is the inverse of this basic structures. We say one basic structure is the photon antenna, the is the aperture antenna. But if you inverse it, by inverse we mean that if you have this, let's say this yellow region is gold and this white region is air. If you inverse it, you get something like this. If you inverse this structure, A, you get D. And the inverse structure is based on so-called magnetic principle. And this principle says that if you have a complementary or inverse structure, then you inverse electrical and magnetic field. So in this case, we are localizing electrical field by the oscillating current, or by the accumulated charges. And here you have oscillating current that give you a concentrated magnetic hotspot. The magnetic hotspot because of the oscillating current, of course. Then you have a magnetic hotspot near the neck, near the bridge region, and same as here. So the magnetic field can be confined and enhanced as well, and this has its own applications. So you can design these structures just like you design cosmologic structures. You can enhance the magnetic field by hundreds of times, field square by hundreds of times. So that's very, very similar to how we design the electrical hotspots. So the application, let's say, since you can localize the field, when you localize electric field, this oscillating current, of course, oscillating current in this direction, and accumulated charges acting as electric radiation source. They emit radiation. Basically, the radiation shine it, then emit it to the other side, and you can use it to enhance transmission or enhance absorption, enhance transmission or emission. So this has been demonstrated in our work. Again, that's probably more than 10 years old. It can be designed in the so-called single band infrared focal plane array. So each of these match with a pixel in the infrared camera, and then you can enhance the absorption at a given wavelength. Say here is 9 micrometers. You can have a enhanced transmission at that wavelength only. And this is for IR focal plane array. You can also design this in the dual band. So dual band IR focal plane array is commercially available. Of course, it's usually one wavelength at about 5-6 micron. The other is about 9-10 micron. So you can design the transmission bands using a hybrid structure like this, and then you have a dual band enhanced focal plane array. So so now the complementary flow type structure, and then or the complementary type of antenna, you have oscillating current. Actually, this current absorbs electromagnetic radiation. It does not really enhance the transmission. Actually, it does the opposite. It enhances absorption. So this can be designed to make it a so-called perfect absorber. This kind of perfect absorber can be tuned to any wavelengths you want. Let's say you can change the dimension, and you can make absorption happening at a desired wavelength. For example, around 4, or 5, or 3.5, and so on and so forth. It's a very simple two-dimensional design. It is quite intuitive to the angle of incidence by this design, and again, this is because of the oscillating current, and this material used is actually gold. So we know if you have just a plain gold film, it is perfect. It's really perfect reflection at the infrared wavelengths, right? So when the wavelength is greater than 1 or 2 micrometer, the gold is going to be a reflector. But here you can make it as a perfect absorber. You can absorb all the radiation in the 3-layer structure like this. So now you can further make one structure that is has a hybrid antenna and a complementary antenna. So you have at the top of it is like you have a bridge connecting the two metal pieces, and that is the complementary structure. And at the bottom you have sharp tips, and that is a normal, we call it multi antenna. So in this case, you can tune the dimension. You can have the electromagnetic field both enhanced the specific wavelengths. Okay, and this is the fabricate structure. Look from the with the FIB, and the top view, side view. You can see what it look like. You can, of course, we can carry out all the simulation, but we can also do the experiments. The experiment basically you can map the electrical field, that is the so-called near field scanning optical microscope can do. You can map out all the hotspots of the electric field, but then you rotate the polarization direction. You can use electrical field to map the magnetic field because of the Beveridge principle. Basically, you can also use this same structure to map out the magnetic field, and this is some of the calculations and showing that the experiment and also the simulation are really close to each other. So so again, this is one application for doing both. So I was just switch to some of the manufacturing side. We use this the hotspot to as a light source or energy source to write things in photoresist. And this is a long process. We first just use, let's say, antennas put somewhere here, and then a photoresist. And then the light just shines through, and then we want to imprint the structures on the photoresist. So this is we use a aperture because we want to block all the light. So we only have a hotspot, and because of this near field, the photoresist surface has to be really close to this aperture surface. And this is what this is the mask we made, and this is the printed results. And you can print a dot with the photoresist as small as actually less than 50 nanometer. This is 50 nanometer step, and this was you can print an array of dots. And this was, I think, it's 2004, 2006. So this is really long time ago. So this is the first demonstration of using this kind of structure to print. And then you can put on the AFM. You can put the antenna at the tip of AFM on the upper right figure, and then you can write lines, tens of nanometer lines. And then one of the challenge of doing such a writing is this is certainly very slow. AFM can only write, let's say, tens of micrometer per second, and that's a single spot writing. So we are figuring out how to make the parallel writing. So suppose forget these details for a bit. Suppose I have two surfaces, one surface here, one surface here. Suppose I can put many of these antennas on one surface, shine a light on it. I can write many dots simultaneously. The catch is that you have to make these two surfaces very close to each other, very parallel to each other. So we're talking about nanometer size gap, and they cannot touch. So the one of the solution or engineering solution to that is we try to control the gap size. Actually, this is a very challenging task. So we have a collaboration with the team at MIT to carry out this task. So we developed something called interference spatial phase imaging, interferometry spatial phase imaging, or SPI. And this is a double this chirp grading, 2D grading as a diffraction mask to generate interference fringes on the other on the right side. This is experimental photo, and that fringe propagating into different direction when the distance change, and this gives us a very high sensitive measurement up to about 0.2 nanometers gap sensing. So this allows us. This is a fabricated grading structures, and then this is the antennas that I talked about. This is array of dots, and then with that we can carry out parallel writing with 1000 as this is as far as we pushed. Well, 40 nanometer line with 1000 dots to write in parallel. So the next thing, or actually this is still something that we are working on, is in the data storage area, and this is so in the data storage area, this is the roadmap for ASTC, Advanced Storage Technology Consortium, and there's a newer technology called HAMR, heat assisted magnetic recording, which is going to be at this as we speak. This device has already been made, and is maybe we will soon have a hard drive based on this technology. So what this is this is a hybrid. You have a laser, you have magnetic writing port. The laser is to raise the temperature of the recording media for easier writing. I think I'm running short on time. I will just skip some of the details of how it works. Basically, what it requires is that you have an optical spot, very small as the write bit, maybe about 50 nanometer also. So we have been seeing this antenna, of course, the optical antenna is a good candidate for localize the light to a hot spot, to a small spot. I guess it tens of nanometers. So within this tens of nanometer, the read and write code can write to the letter, write to the bit of information. So this possibly can be the largest application of plasmonics. Of course, we know plasmonics has been studied many years already, and if it's implemented in a hard drive, of course, it has impact to our technology, right? So what it is, this is a hard drive in reverse. This is the hard drive, and this is the light coming from the bottom, and you have a antenna kind of structure, and this is diamond-like carbon coating, and there's an air gap. We know during operation of a hard drive, this is very close. This is the read-write head, and this is the hard drive surface. The gap is actually nobody knows exactly what it is. Let's say it's on the order of 2 nanometers, and everything else, the coating is 1 nanometer, and the films are on the order of single nanometers. So you can have a antenna that provides the necessary heat. And this is the cross section of this antenna. This is from Hitachi. And this is a simulation. This is the miniature scanning optical microscope. And this is the measurement. This is the measurement. This is the enlarged image of the measurement. And this is again 40 nanometers. And this is a magnetic footprint. This is the recording footprint. And there's a lot of design goes into that. There's two issues on the thermal stability, and of course it has to have some kind of optical function of this NFT. So we have done a lot of work. I think this is again carried out in more than 10 years already so far. So this is study the materials, how to select the material, how to design this antenna. Try to skip this as well. And then a very recent effort in our case is to carry out so-called inverse design or topology optimization for this antenna. So this is also derived from this project. Let's say in the hard drive you want to write a bit. This bit is usually a rectangle shape on the hard drive. It's curved a little bit because of the curvature. The bit is arranged around the hard drive, but if you look closely, it's close to a rectangle. So you want to heat a spot. The heated spot can only be a rectangle shape. You don't want to heat a larger spot, otherwise you are going to have crosstalk. So basically, we want to design an antenna that gives us a heated spot with a rectangle shape. So we solve for inverse problem. We say what kind of source, what kind of electromagnetic source that can give us a rectangular heated spot. And the source turned out to be something like this. And then we do another inverse design, say what kind of antenna can give us an absorption profile in the material like this. So the inverse design basically is an optimization problem. Actually, it is quite challenging because of the plasmonic properties of the material often generate singularities. So, but I will skip this again. At the end is that the computer will run, you program the code, the computer will, the algorithm will generate what kind of structure can give you the best performance. So at the end, what we are generating is something like this. This is not a bow-tie shape or any shape that we usually will think about. This is a shape of this antenna that can give us the best result. And this is the what computer is doing. The first, it just take a blank film, and then it will evolve by iterations. Then eventually it come up with something like this. Okay, so so this is of course this can have many other use if you want to have a hotspot which has a different shape or different even polarization, different different features that you can use this inverse design to see if it make sense for you. So the lastly, I want to quickly talk about the plasmonic in 2D materials. I'll start with black phosphorus and tellurium. Those are the single element material. Of course, black phosphorus was really a hot topic. Like 6 years ago, tellurium is something like 2 or 3 years ago. We are fortunate that I have collaborators at Purdue who are the pioneers of these materials. And the blast forest, of course, is van der Waals materials. It has just like it has armchair zigzag direction. Tellurium is even more complicated. It has a twisted structure along the chain. So it has it still has stacked layers, but it has within each planar layer it has chain-like structures. So we have built this BP and MOS2 single layer MOS2 and type heterojunction like a diode. You see this characteristic of a diode can turn it on. And that was again this is about four years ago we did this work. Then we'll come back to talk about this antenna plasmonics. You can design this antenna to enhance the absorption in black phosphorus to make it an infrared detector. And this is the array of antenna that is made in this device. And we have done the test and we see the enhanced absorption along this direction where the light is polarized along this direction. So this is demonstrated work that we can use for 1.50 nanometer wavelengths. Of course, antenna can be designed for other wavelengths, IR wavelengths. So this is mainly to deal with the IR detector. The other is to enhance its polarization sensitivity or polarization discrimination. So this we use this aperture. So the other structure. So again, there's a design, there's calculation, there's experiments. It can be done. So then the next material I want to talk about is protocol insulator, because this is has been studied widely in the physics community. It has a bulk of the material is insulator. The surface of the material is called topological surface state TSS. It has a so-called spin momentum locked surface state. Means that the current will only go to one direction if it is irradiated by a certain circularly polarized light. So its band structure look like this. It has in the surface state has a graphene-like band structure, but it is the two branches are different, not symmetric. One responds to one spin, the other responds to the other spin. So that's the difference. And the one of the applications we are exploring is the at infrared. At infrared, the material is insulating. It doesn't mean that the bulk of the material does not absorb light at all. Only the surface responds to the light. It is circular polarization sensitive again, and you can develop some kind of a plasmonic device based on that property. And these two are near field scanning optical measurements. And on the left is the wavelength is longer shorter than the band gap wavelengths. So the material becomes as a bulk metallic. So you see fringes of plasmons just as you see it on gold films. There's no difference between this and that metal. But when you shine on the infrared, then you see the fringes is very similar to graphene. So this kind of fringe is much smaller than the wavelengths of light. Wavelengths like 10 micrometer. This fringe is like less than 100 nanometers. So you can it is so the wavelength is much compressed in the material. As I said, one of the unique is the spin momentum locking. So you have a certain polarized light shining on it. It will drive the current going into one direction only. And if you reverse it, it will go the other direction. So this is what we use to explore a so-called thermoelectric transport. The second is the photo detection. So the two things that we are doing, we have done. So this is a demonstration. That's it. The different lines represent different bias state. Backgate. So we apply backgate, and then this different number here representing different state of polarization, 45, 25, 25, and these are either left or right circular polarized light, and everything in between is linear or elliptically polarized light. You see the clear oscillation of this produced current under this bias. So you have two knobs. You can change the polarization. You can change the bias state. I'm sorry, backgate. Bias state. So what this is the gate. This is the photo current. So what we are seeing is actually you can modulate the photo current by the backgate greatly. This one line is used by, let's say, right or left circular polarized light. when you have a pure circular polarized light, you can generate current, but also you can use biasgate to tune this current. Tune this current in a very large range, and this is the red line is what we are looking at. So if we plot this line and we calculate so-called feedback coefficient, then you will see that this sigma 1, let's say sigma 1 is right polarized light, sigma minus 1 is left polarized light. So at the same bias voltage, and the response is very, very different. And you can make the change of these the coefficient when you change bias gate. So sorry, back it. When you but just one more word is that when you use a negative gate voltage, you are pushing this Fermi level down to the valence band. When you apply a positive voltage, you are pushing it close to the conduction band. When you push it closer to the conduction band, the difference gets smaller because of you have other electrons that evolve in the transition. So with that, I think I run out of time. Then thank Professor Dawn for the invitation, and thank the funding agencies and many students, graduates, postdocs, and collaborators. By the way, many of my students come from India. Actually, we have a lot of graduates and they make great contribution to the work that I connected here. Thank you very much. I'll be happy to answer any questions if I have time.
Thanks, Professor Zhu, for a wonderful talk. And your talk, spanning different areas from plasmonic nano antennas to topological insulators. So wonderful talk. So we have time for just a couple of questions. Are there any questions? Anyone? Is there any question? So I just have one, basic question, maintaining the gap, like you were talking about 2 nanometers. And so how precisely you can do that, especially when you're writing for the memory application?
We actually we don't have in my lab. I don't have a way to measure that. This number is given from the industrial consortium, and actually one of my former students, actually many of my former students in this data storage company, and they did this metrology work, but of course they won't be able to tell me their exact numbers, how they did it and even like that. But in the ballpark is that this so-called air bearing calculation. They designed this. Go back. They designed the shape of this chip in a way that they can calculate the lifting force and everything like that, and then that calculation they can estimate the gap between the two surfaces, and this is called air bearing, like bearing with air. It's all air in the middle. This is a big effort actually, and this effort is led by a professor at UC Berkeley called David Boji, and he is the world leading expert in this air bearing type of design and calculation and the work, and all the industry all over the world uses it actually to this calculation.
That's great. Well, thanks. So just excellent work. And that was it. I think now we can move on. So Professor GB, Pavan Kumar is the session co-chair, and he will take over from here, and he will introduce our next speaker, Professor G. Pavan Kumar.
Thank you, Professor Ramraj. Thank you very much. It's my pleasure to introduce the next speaker from France, Professor Mikhail Khanwa, who is going to speak to us about plasmonic biochips. A very brief introduction to Professor Khanwa, who is the Director of Research at CNRS and also Associate Professor at the University of Sherbrooke. He is currently the director of the International Research Laboratory for Nanotechnologies and Nanosystems at Sherbrooke, Quebec in Canada. And he got his education in École Normale Supérieure and holds aggregation of applied physics. And he has also been associated with the Institute of Optics Institute Graduate School in France. And his area of expertise and past experience has been in hybrid materials and their application in photonics, initially on polymer materials, including sol gel, doped chromophores, and also plasmonic biochips, waveguides, and many other interesting systems. He also has a very deep connection to plasmonic systems in the context of biophotonics, and he has done some very interesting work in this particular direction too. He has also spent some time at Creole in US and Duke University also again in US. And in 2014, he joined LN2, and he has been leading these optical systems and bioapplication activities. He has co-authored more than 125 publications, and he has very interesting work under his belt, and including 2 patents and various different lectures across the world. With this introduction, let me ask Professor Mikhail Khanwa to give his talk on plasmonic biochips. Professor Khanwa.
Okay, I've got the sound back. Sorry. Fichier ouvrir.
You can share your screen. Yeah.
That's what I was trying to do. Oh. The share screen button.
Yeah, the second one you will have to.
Yes.
There's one more in the.
Do you see it now?
Not yet. Not yet. There is something which has been loaded.
Vidéo invitée. Vous partagez votre.
Yeah.
You have it now?
Not yet?
No, not yet.
It's a big file. Because I tried uploading it before, but it would have stopped the previous speaker. That's ridiculous. I go back one. Don't have it. Escape. You have it now?
No.
No, we don't see it.
When I tested it, I had 2 screens and it was working, and now I only have 1 screen on my portable computer, and it seems not.
This is share.
Yeah. Are you sure I have all the right to share? Because I have half of my pale gray.
So when you press share, like the third button, right? When you press, you see you see it on Windows, right?
The only thing I can share is my window meeting, and that's what I was doing, and you didn't have it. So,
from the desktop, you cannot share the desktop, or you don't see any other window when you press share.
When I press
you
share,
need to share the application.
the only share that's not pale gray is this one, and on this one, I was thinking you would have my presentation. Partager ma fenêtre. Partager. This. You know what, Anu?
Yeah, please, if you could.
I'm going to try to send it directly to you.
Yes, that'll be great. If you just Gmail me, and then I'll put it up.
Sorry for that. Big file. If I stop this. I'm sorry. Okay. Are you sure I'm trying to send the message, but are you sure you gave me the control?
And Dheeraj or anybody from the ICEE team?
Because I don't understand why those half of the buttons are pale gray instead of black. I'm going to try to do it another way. Yes. I made it, I turned it into a PDF. There won't be any animation, but that's it. Maybe it has a better chance of work.
Yeah, it's almost loading, I think. It's halfway through.
Okay, I'm sorry for that.
This is great. I think this will be quicker than the email.
Yeah, well, the email, it wasn't being, the file was too large.
Right. I think this is almost done. Yes.
So you have it now?
You can see it, yes.
Okay, good. Well, so I thought thank you very much for giving me the opportunity to speak about that, and I'm very sorry not to be there, that's for sure.
No, this is great. Thanks, Michael. Appreciate it. Please.
I really hope we have the opportunity to come and discuss stuff. science and collaboration and all sorts of things. But today I'll be talking about plasmonic biochip. And the thing I want to stress today is how we can nano-enhance the plasmonic biochip properties. I have a very strong back noise. It's better now. So how we can nano-enhance the sensitivity, specificity, and imaging, and probably many more application and properties by doing some proper nano and microstructuring of the biochip. And this work was done was started in France, as mentioned earlier, and pursued in Canada, Quebec. So, okay. So just a word to say that we are very open to collaboration. It's an international lab. It's in Sherbrooke. It's close to Montreal and Quebec. And it has a very nice clean room facility. And it's open on many different teams: energy, electronics, photonics, packaging. And we try to think about how our new science is going to impact society also. And this is a team mostly of professors that participate in the talk I'm giving today. We usually work on plasmonic imaging instrumentation, application, and nanoplasmonic. And today the focus will be on nanoplasmonic, how we can advance field to profit application by using it into proper instruments. And that's basically the outline. I'm going to go quickly, we're late. Let's say just a few words about the classical plasmonic sensing, while stating basically that it does a very, very good job, but of course, end user always want a little more, and that's how we got involved in nanostructuration. And this was many years ago, and part of it was in fact done at Duke and together with Anuj. Nice memories here. Enhanced performances. I'll give example about SPA biosensing, CERS characterization, and structural imaging. And I hope we have some time left for questions. So very basically, because we probably all know that plasmonic sensing is about coupling light on a gold film, and the coupling condition, usually done through angle and wavelength, are going to change if the local dielectric on top is modified. And this is an example of resonance shift. If you add a 10 nanometer biological layer, and basically you can record the change in angles, the change in reflectivity, or the change in wavelength. And what I just want to remind is this type of sensitivity curve where the reflective, for example, is going to increase with thickness. And you can see here, if you can see a few percent, you can measure a few nanometer. And basically, in optics, it's not very difficult to measure a fraction of a percent difference. And you can basically, this is a very, very simple system. You take a 50 nanometer film gold, and you've got a sub-nanometric sensor in thickness of what is getting deposed and leaves the surface, and you can make this real time, which allows you to study biomolecular interactions. So this is a PDF film, so you're not seeing the movie. It's a PowerPoint version. This would be an animation. You can put this into an optical system. This view field was 5 by 5 square millimeter, and you can follow the evolution of the surface for hours if you want. This movie was a couple of minutes, and basically you will have put, for example, a single-stranded DNA sequence under each of those spots, and what you're seeing is what you're sending on it is binding more or less, sometimes not binding in some of the holes, sometimes binding a lot. And what you get from each of those points is a signal as a function of time, while the targets are going above and going under. So this is for the very quick introduction. And I want to mention you can, of course, build a different type of instrument. If you're doing imaging, you're measuring, for example, the reflectivity, but as I mentioned, it can be angle, it can be wavelength as a function anyway of space and time, but you also can use many different parameters. The coupling angle, of course, theta, wavelength lambda, direction of propagation, and this as a function of temperature, material you're using, etc. And we've built over the time very different materials, and there was this paper now nearly, well, more than 10 years ago by Omola, Piliarik and Omola, about where's the propagating sense plasma with thin film reaching their limits. So the limit was quite low, as you can see. It can sense 10 to minus 7 unit optical index unit. But still, this could be not enough for application where you have a very low number of targets and people basically want more. And that's when we came, well, in fact, we came into the business about just before that date. But our data point with thin film was this one. And that's why we started going from here to here. So basically, our analysis at that time was most 90% of the real sensing was performed using thin films. There was quite a community using nanoparticles in solution or sometimes deposited on the surface to actually do some sensing. So in here you had the propagated plasmon surface mode. In here you had a localized plasmon mode. And we believed that we could couple both and get the best of both worlds. So we started using this type of structure, basically a film on top of which we had nanoridges or nanoparticles. And typical dimension are here, about, for example, diameter, period, thickness of the film and of the particles. These type of samples, as you all know, are particularly costly to fabricate. So it's best if we can run a couple simulation beforehand, and that's exactly the type of thing we were doing in Duke in those days. But together also with Anuj, we sometimes got frustrated with some of the capabilities of the commercial softwares, and we basically end up developing our own in collaboration with colleagues at the Optic Institute, and this one is based basically in combining Fourier model methods with finite element method, and it is basically, well, you can find more in this paper and the other one, but it allows a very accurate and fast simulation, or relatively fast simulation, for any type of metallodielectric nanostructures. And we can adapt many things, and we can study what will be the effect of fabrication if the corners are not straight but are rounded, if these walls are tilted, etc., etc. And we can play with all sorts of materials. So it's a very convenient tool now, and we can run it before actually fabricating the samples. So what we saw studying this type of structure was effectively that if you start with, on one hand, a surface propagating plasmon, and on the other hand, some localized surface plasmon, what you can get is a coupling between both of those modes. So here will be the normal surface localized propagating surface plasmon. Here's the localized surface plasmon. And if you use an harmonic coupling equation between those two, you will find those what we call hybrid modes here, which are exactly the one you can see you obtain when you calculate the spectral reflectivity of this kind of sample. And what you see up there here is also the grating effect due to the periodicity of the sample. So harmonic coupling, one unique free parameter, and very nice agreement between theoretical and numerical and experimental data. So we went off fabricating the samples. Here again, a trade-off between quality, time, and cost. And this is something you've got to study because each fabrication technique is going to have its to modify the sample in a certain way, which is proper to the technique. So we basically, when you want initial proof of concept, we go with e-beam lithography. If we want the sample to be usable by the biosensing community, of course, you have to think about a much larger amount of substrate to be at disposition of the end user. And you've got to think of, are the structure fabricable in UV anneal or soft or hard UV anneal using nanoimprint technologies? And what are going to be the induced typical defect and what are going to be the impact? And again, we can study them both numerically and experimentally. So that's an example of what we did. So now what I'm going to, in the next few graphs, I want to convince you of the many advantages of this type of structure. And first thing, we were using SPRE, so the surface plasma resonance sensor, same configurations that I initially showed you. And well, basically it works. I'll show you in the next view graph, you're not gaining a lot if you're using the whole surface of the sample. But you can start playing tricks also. For this application, what we did was it was a work we performed with Oriba, Jobin Yvon, and we basically started building an apparatus where we could do the parallel acquisition of the whole biochip on one image. You know exactly which spot is lighting up and which is not. And you can go and direct your source measurement exactly at the spot you're interested on these spots you're interested. And you can actually quantify here and get the biomolecule, the fingerprint, if you can say so, of the target you've acquired to avoid false positive signals. So this is something we did, and it works very beautifully for both. I'm just going to give some quantitative data just after. So one thing about SPRE, as I mentioned, if you nanostructure the sample, but you actually put some target everywhere, you're not going to gain that much unless you go to very, very small samples and typical size, you're not going to gain that much. And you're going to gain by the fact that you're acquiring also more targets. Where it comes more interesting is if you are forcing, because you've localized your probes, for example, chemically, or because you've immersed this into another dielectric and you don't have the possibility of deposition of the targets. But basically, if this is the response of the surface to a coverage by the targets on everywhere, these are going to be the normalized response if the targets only go on top, on the side, or on the bottom of the structure. And basically what you can see here, so after you're going to introduce how much signal can I get from one single molecule that's being captured, and how much is this going to differ if you go in those different places. So sometimes you can get a bigger signal, but because you're using more molecules. And in fact, what we can see here is if you're using just the molecules that goes on the top of your nanocylinder, you can get near an order of magnitude efficiency compared to those molecules that are going to bind in between the nanopillars. And that's is very interesting because if you're working with low concentration target, you're not going to cover your biosensing, your substrate surface anyway, so might as well capture the molecule where the sensing is going to be the strongest. And in fact, the sensing is going to be the strongest where the electric field is going to be the most enhanced. And this is a correlation you can see on the right-hand side, where we plotted this enhancement factor together with the average field on this precise location, varying the size of the structures. And this was done quite some time ago. More recently, what we showed was the effective impact of on the SERS signal. So, well, this is just if you use flat gold with no SERS or piece of glass. What people usually conventionally use is going to be this type of structure with nanoparticles on top of a glass substrate. And if you use this type of structure, you can gain another factor order of magnitude in the intensity of your signal. And I would say furthermore, this can be optimized using many different parameters. But one of these parameters, remember, this mode is due to the coupling of the propagating mode and the localized mode, which means that if we tune the angle of the sample, we can actually tune the mode and the energy within those modes. And for example, if you go onto these structures that are the field repartition, if you shine the beams of light from the top of the sample, if you go to an angle of 34 degrees, this is the type of electric field relative enhancement you're going to have, which in turn on the signal is going to bring you from here to here. And remember, this was already an order of magnitude enhancement compared to just the nanoparticle alone. So it's a very interesting extra enhancement of the signal you get. So now another thing people are interested sometime in biosensing is the capability of the surface plasmon, because the field is localized in the immediate vicinity of the metal. Well, basically, if you look at a sample at cells on a bright field, what you're going to see, for example, is this type of feature. It's not the best photo, but I liked it because here you see this cell, and this one is probably going under. Well, on this image, which is the SPA image, you actually see the cell which is under, and you don't even see the cell that's above, because you're localizing your interaction. You really get a slice of what's just above the gold surface. So that's interesting, and but this is a problem with biosensing, because propagating plasmons that normally people use, the propagating plasmon are associated to propagation length typically of tens of at least 10 micron. So this is going to totally blur your image, as we'll see just later. Should have probably put it here. So basically what we put our sample, sorry, I'm using my pencil. This would be easier. We put our sample in the focal point of our microscope objectives, and we're going to gain a little resolution this way, but the limitation, as I just mentioned, is going to come from the limited resolution. Move on a little more quickly. Is going to be due to the blurring because of the propagation effect. So this is what you would see in bright field. So of course you can see below, as I just showed you, just localized interaction, but the blurring effect in the direction of propagation. So you've got your optical resolution on the side, but you've got your propagation effect, which is going to blur the image in one direction. So can we do better? Yes, of course. And using different type of material, you can play on the sensitivity and the propagation length. But as you can see, unfortunately, most of the curves are here. People usually use gold, 15 nanometer. And this is a typical, with near infrared or red wavelength. This is typically the place where people are working. So if you want to go down in propagation length, you're losing sensitivity, which is a trade-off that people are not always ready to do. If you do the calculation with an array, which is typical dimension, particle size 200 nanometer, periodicity 400, and you look at what is happening with the propagation length as a function of height, relative height of both, you can see typically the data points for thin film would be here, 0 height for the structure, and typically 15 nanometer for the film. what you want to go, if you want to diminish the propagation length, is anywhere away from this point. You can look at the penetration depth, which is very important if you're actually wanting to sense within a given thickness. You can look at the contrast, the surface sensitivity, and the bulk sensitivity. And basically, what you end up is a compromise between those high sensitivity and this strong attenuation lengths that you want to go down. And the details on the paper, I'm not going to get in more into it, but basically the stars are the data points I'm going to show you just here. If you go with a thin sample, you are going to go along this line. If you just diminish the thickness of the sample, if you use nanostructure, you can keep the contrast and therefore probably, and certainly in some cases, the sensitivity, while decreasing by an order of magnitude the attenuation length to bring it to your optical resolution anyway, where you're going to be limited. So this is very interesting, and it's exactly still the same samples that are using for SPRI or CERS measurements. And that's what it's going to do. So basically, you've got a thin film part, nanostructured part, 1 degrading, 2 degrading. So you can go from here to here. It doesn't show as good on the screen as it shows in real life. Maybe you should have put a slice, but details are in this paper, and it gives you more contrast in the 2 degradings than the unstructured film, and this we can use afterwards in some biosensing experiment. And I think I'll just give you one example of what can be done using this different configuration. And this is an example of an experiment where we look at the endothelial cell monolayer integrity as we are going to inject some kind of perturbator. And this has application in health, for example, in sepsis. You need basically your film layers, your cell layers to be impermeable, and you don't want a gap to be opening. You could, for example, drown in your own fluids if this is happening in your lungs. So you want to be able to study what's happening here. So we would like to devise an early warning sensor, biosensor. And here is you're going to have a biocomponents that is composed of a cell. We inject the perturbator and want to see what happens. Are gaps going to form? Are gaps going to stay? How large are those gaps? Well, if you use a classical, and this you do it just at the level of the interaction, at the level of the metal. So you really see the start of it, not what's happening on top of the arrangement. So if you use an unstructured film, these are the kind of data you can get as a function of this was the concentration of the perturbator. If you use a nanostructured sample, well, you get in more detail and you actually get into the information you wanted to acquire. So this was more recent work, and we got much involved in realizing biocomponents that could be used in conjunction using nano-microstructured biochips that could be used in conjunction with instrumental system. I think, yes, I want just to summarize the message here. Well, sorry, the last figures is not on this version. I want to stress the importance of metal nanoparticles on metal film type of structure. At this point, we only have found advantages to it. To increase, well, it keeps the spectral dispersion of the propagating mode, which was an interesting part that we were using for the SPRI system. It further enhanced the local field modes, and this is typically what you need for application using a nonlinear effect such as CERS. And it has a smaller propagation length, which means that the coupling goes at a smaller distance, but it allows for a sub-micrometer structural imaging, which allows us to go into bioapplication at the scale of cells and not only at the scale of molecules. So we find this structure of great interest, not only for the biosensing field, but that's where we are using it. And we want to master them with better comprehension of what the defects are going to be induced by different type of fabrication techniques, because no way we can use e-beam fabricated sample in production for this type of if we need basically many substrates for the end users. But it's very interesting doing all the engineering of the evanescent and propagating characteristics to allow proper imaging, but in a more general way, field enhancements. So on that, I will thank you for your attention and take any question. And I thank also all the different partners that actually worked recently on those type of application and the funding institutions. And you for your attention. And I'd be open for any questions if there is still some time left.
Yeah, Anuj, is there time for questions? Quick question.
I think we have, because we have a break going on, so we can have like one or two questions, please.
Yeah,
there was something just behind, and we had kind of started late.
Is there any question? So I have a question. So very interesting talk. In fact, it's very interesting to couple localized and the propagating plasmon mode on a single platform. I'm just also wondering, is there room for coupling, for example, localized plasmon from one metal and propagating plasmon from another metal? Would you see the bandwidth and the fidelity changing with that? Because you can then, for example, silver response function is very good as a particle. Of course, biocompatibility is an issue. Whereas gold is very robust in terms of biological applications. Do you want to comment on this combination of two different metals? It would be nice to know more about it.
Yes. Well, the answer is yes for the coupling, definitely. We've looked into it for different applications, not only biosensing, but we also heavily involved nowadays in thermoplasmonics. What is happening at the femtosecond time scale, nanoscale? How is the heat moving along into particles, in between two particles, within a particle, with the particle and the metal beneath? And of course, you want to you want to be able to excite one particle and not the other one. And an easy way to do it is to change metal, because you're going to change the spectral feature. So you're going to have this type of, the coupling works, the answer is yes. What we've done with silver, usually we put the silver underneath. And at some point we were using, even the thin film was using a bimetal, silver and metal. But because of the chemical properties of gold and silver, when you're just studying the plasmonics, basically we can do whatever we want.
Whatever you want, that's right.
When we do the sensing, the guys we work with like that we finish by gold.
Gold, you're right, that's correct, yeah.
But yes, there's a lot of very interesting things to do within the material community, and that's something we involve nowadays.
So, is there also an optimum thickness of the metals film what you use for your work? Because if you shrink your metal to thinner kind of films, your heat propagation capability will be much better. Whereas if you use a 50 nanometer thick metal, then your propagating plasmon becomes better. So, is there a trade-off or something?
There are trade-offs, but My short answer now is every problem has its own trade-off solution.
Yeah.
So depending what is the biological problem, what is the physical process you want to show, to demonstrate, we're going to use different type of parameters. What are the wavelength we have to use because of the system requirement? You know, when we do for example, in the thermoplasmonics, we use a femtosecond large band OPS system. You can't go at 800. Well, you have to avoid this wavelength. You move on the side, and the thicknesses depending how much you want to probe. Because the cut in something I didn't probably emphasize enough was. You change the propagation length, which we easily see for the characterization, but you also change a lot the penetration depth.
Penetration depth, yes.
So you're probing at different lengths. And depending if you're probing, a small molecule or the thickness of a cell layer, well, you're not interested in the same thing. If your probe is big enough, if your probe starts getting big, so this is something people had sometimes a difficulty when they were using just the nanoparticles with very short penetration depth. They were actually functionalizing them and not seeing the binding, but it wasn't. The chemistry was working fine. It's just the event was happening too far from the surface. So this is also something you can tune using all the parameters, including metal and wavelength. And the mode, when you were tilting the angles.
Tilting the angle, and
was also some way.
Very interesting. So, are there any other questions?
Just Michael, one brief question I had was your NIL. Obviously you'll have more chips, faster production rate than e-beam, but in terms of the quality, any deterioration in your NIL samples for the same dimensions? Like if you obviously
same dimensions, the 200, 400 are not that demanding. If you want to go low, this is going to be another issue. We had a lot of waste at the beginning. At some point, it was kind of better and sufficient for some application. Again, it was a matter of you can choose the structural parameters so that the defects that are going to happen. For example, your walls are not going to be as straight using nil technology than using e-beam. But this can be taken into effect when you're doing the simulation and deciding what structural parameter you're going to use.
So you could the same kind of performance. You could still get similar performance.
Sorry?
You could still get similar performance if you design it properly.
When you go for it, you can.
Thanks.
But it's when you're not using them in production, it's sometimes easier and more reliable to stick to the e-beam.
Sure.
Especially nowadays, as the e-beam technology has, you can light up large surfaces, and sometimes the samples when you use them are totally reusable. In the lab, you can use the same sample for weeks, months, sometimes.
Oh, great. So you don't have to go for NILs. I think that answers. Yes, please.
We want to go for it. We've tried it, and we would definitely do it within industrial partners when it has to go. We haven't started it when it has to go to market.
Great. I think that answers the question very well. So thank you so much, Michael, for your wonderful talk, and thank you, Professor Zhu, for your wonderful talk, and thanks to Professor G.V. Pavan Kumar for co-chairing the session. And I think that brings the session to a close. It's really great to see Professor Zhu and Professor Canva after a long time. live.
Yeah.
It's a phone call, and so this is great to see after a long time. We were expecting you'll be here live in Delhi, but even after moving the conference, it actually is a virtual conference. But this is better than nothing, and really glad to have you here. So thanks to everybody for being present in the session. So that ends this session over here. Thanks.
Thank you.
Thank you. Thanks.
Thank you.
Good evening.